Are we good to start in 1 minute?
Yeah.
All right. All right, so welcome to the third and last day of DISC. So it's my great pleasure to introduce our third keynote speaker, Stephanie Gill from Harvard. So her work is at the intersection of robotics, distributed computing, and more recently, human-computer interaction. And so she's previously been affiliated with the University of Arizona and also been a visiting professor at Stanford. Although she's fairly junior, she's already collected a very impressive array of awards and fellowships, including a Sloan Research Fellowship and an NSF Career Award. I've been a big fan of her work for years now, so I'm really, really happy she decided to accept our invitation to give a keynote. So I'm really looking forward to it.
Thanks, Dan, for that introduction, and thank you all for being here today. I'm really excited to be here. It's been wonderful to be part of this community. It's my first DISC as well, so I'm excited to tell you a little bit about the work that we're doing in multi-robot systems. Thank you. The work that we're doing in multi-robot systems, looking at problems that will definitely be familiar to you, but from a different lens. So thank you very much to Dan for the invitation and the organizers. Okay, so we think a lot about multi-robot networks. And so just to give a little bit of context, these networks are characterized by a few things: controlled mobility, sensing, so these are agents that can sense their environment, they can sense each other. They have onboard intelligence, so they have compute capabilities. We're mostly looking at distributed systems here, and communication. So this is the setting that we're looking at. And what I'm going to talk about today is our work that is on the theoretical side, but also a lot of practical applications that I'm going to be talking about. So excited to share that part of the work. So just to put a little bit of context in terms of the types of systems that motivate a lot of the problems that we look at. So when we think of multi-robot systems, we should be thinking about systems like this. For example, autonomous vehicles, fleets of autonomous vehicles that might be driving down a road or a highway, delivery drones that might have to coordinate in order to be able to deliver packages across, say, a city. And search and rescue robots that might be working with humans in order to be able to respond to, say, a developing disaster. However, their coordination algorithms are vulnerable. And that is a major difficulty, especially as we start putting these systems out into the real world. And this is not new news. This is something that we've known, especially this community. So what do we do in this case? Because this question is not just of theoretical interest, it's very applicable, especially now as we start to see cyber-physical systems go out into the real world around us. So I'm going to talk about multi-robot systems and cyber-physical systems in this talk somewhat interchangeably, because multi-robot systems are just an example of cyber-physical systems. So this has been on the radar now of different governments across the world, also industry. As cyber-physical systems go out into the world around us, the question of their resilience and the vulnerability of their algorithms is really important and really critical. So when I talk about the resilience of a multi-robot system, I'm specifically referring to the following. When agents need to perform some objective, they need to coordinate, and I'm going to call how well they're able to coordinate, I'm going to call that their performance. And then the degree to which they can attain this performance, even in the face of an attack, I'm going to refer to that as the resilience of the system. And so what we strive to do is characterize and mitigate the impact of untrustworthy agents. So agents that might not be collaborating, and I'll give a little bit more specific definitions of the types of untrustworthy agents that we're thinking of. But in general, we want to be able to categorize and also mitigate their effect on the coordination, especially in real-world contexts. So when I say real-world context, I'm specifically thinking of the following types of networks. So imagine here I have multiple agents. These can be drones, these can be different kinds of robots. And I'm just going to abstract this as a graph, and I'll go into more detail in a minute. But the types of networks that we are looking at when I say real-world networks are those where there's the possibility of malicious agents or malicious data in the system. In today's talk, I'm mostly going to have examples of this almost in all of the work that I'll discuss. Possibly dynamic networks where the nodes are mobile, directed networks, and highly heterogeneous connectivity. So these are different characterizations of networks in the real world. I won't talk about all of these at the same time, but I'll talk about different examples of these throughout the talk. Okay, so what does this look like in practice? Just to give an example of what consensus might look like in these systems, take the example of, say, connected vehicles on a road. Now, their true potential and how this really has the chance to change the way we think about transportation is through coordination. So for example, this is traffic intersection management. So you can imagine that if agents can come to a consensus, say on heading, on velocity, then we can start to think about how to manage intersections, perhaps even without traffic lights. And this is one of the objectives that's been really investigated recently on this topic as we start seeing autonomous vehicles, connected vehicles on the roads. Okay, so what about an attack on consensus? What does that look like in this case? So take the case of vehicles that are driving down a road network. On the left, you're going to see a schematic. On the right, you'll see a plot of what this might look like. So on the left here, what you see is a heading direction. So this in the middle is the true average. So this is the heading that these vehicles would like to agree on. And the black lines there are indicating the heading directions of the individual legitimate agents in the system. So this is just to give a motivating example. Now imagine that there's an attack on this heading direction. So perhaps you have an agent or even Sybil agents that are adding some other inputs to that consensus. Well, what could happen in this case? If the legitimate agents have no way of understanding that this is happening, then this can create many difficulties. One, perhaps not even allow for convergence to a value or convergence to the wrong value. So in general, we wish to do the following. We want to quantify the performance. So in other words, how far are we from nominal? In these cases, we want to bound this deviation under an attack, and we want to learn or mitigate the effect of this attack over time. So generally, these are the types of problems that we're thinking of. Okay, so a classical result that you are very familiar with, but I want to put up here again because it's going to be important for what I'm talking about today, is that we cannot achieve consensus in the case that we have specific requirements on the network connectivity or the number of malicious agents in our network. And this is something that is known, and this has been arrived to, this result has been arrived at from many different directions. So here I've included a few works from the control literature that have arrived at the same result, perhaps from different approaches. So this is a big limitation as we put these systems out into the real world. So the question is, what do we do about this? How do we get around this if we want to put these systems out into the real world? Because being able to guarantee that no more than 1/3 of the agents is malicious, or that you have certain connectivity levels out in the real world is difficult. So there are different approaches to security, and I'm going to bucket these into two kind of coarse categories. One is graph structure based, And so these are a lot of the techniques that this community is very familiar with. However, this can lead to practical limitations like the one that I just mentioned. On the other side, there's physicality-based approaches. So this is where you have something additional in the network that you might be able to use to help you solve this security problem. So for example, it could be hardware, it could be using other aspects of the physicality of the network. I'm going to talk about both of these, and I'm going to talk about work that we have in both of these areas, but I'm going to start actually with the physicality-based approaches. So what do I mean by that? I want to give a little bit more context here. So the idea is that for these systems, particularly cyber-physical systems or multi-robot systems, you often have agents that are interacting physically with an environment and with each other. And they have ways of sensing, as I mentioned, the environment through onboard sensors. They also have a way of communicating that information with each other and sharing that information. And this leads to a key idea, which is, can we exploit this additional information to help us address this really challenging problem of resilience in real systems, real networks, in the real world? So this invites us to revisit the question of resilience, and in particular, take an approach through the lens of quantitative trust, which means, what if I could quantify the trustworthiness of different agents in my network by using some of these ideas from the physicality of the system? And so today I'll talk about a particular type of quantitative trust called stochastic values of trust for consensus. And I'm going to talk about that first. And I'll look at different graph types. So undirected graphs, I'll start with that, then directed graphs. And then I'm going to talk about some actual implementations of this in some of the work that we've done. And then I'll also talk about network measures of robustness and some of the work that we're doing in that area as well. Okay, so I'll start here with this idea of what is the stochastic value of trust and how can we use that in consensus. So I'm going to talk about the distributed consensus problem in the context that we approach and what we look at. So this is, imagine that we just have a graph. So we have vertices, edges, and you have neighborhoods. So this is all very standard. But we're interested in distributed consensus. So each agent additionally has some value. In this case, it could even be a scalar. And we're just taking a weighted average of all the agents' values over time. And as a reminder, those weights are dictating the influence of other neighbors on the updates of a particular agent I. And we're in the synchronous setting, and we do not consider the availability of keys, security keys. Okay, so why is that? I'll just mention a few things about this. There are a few reasons. One is we want to make sure that even if a malicious agent were to be able to access a network, we still want to be able to mitigate their behavior, their impact on the network. So that's the first reason that we make that assumption. The second one is because we're thinking of also very futuristic cyber-physical systems where you might have these highly mobile, highly dynamic systems. And so something like having a key server, centralized authentication, we can't necessarily assume that this is going to be applicable. And so we want to just be able to address even this difficult case. Okay, so some examples just to kind of have a few ideas in your mind of what kinds of, what we're trying to converge on. So you might have agents that say are distributed through an environment. They might be trying to converge on a temperature, average temperature, a map of the environment, a heading direction, or a velocity. For example, in the case that I mentioned with the like smart and connected vehicles or autonomous vehicles. And we wish to understand properties of convergence and also deviation. So deviation meaning if I don't have malicious agents, I have some nominal convergence point. If I do have malicious agents, what happens? That's what we mean there by deviation. And we're going to be, in this context, thinking about a certain type of attack, the Sybil attack. And just to be specific about what we mean here, So assume that we have some graph, and that graph has now two sets of nodes, the malicious agents and the legitimate agents. And specifically, legitimate agents are those agents that follow the distributed consensus protocol, and malicious agents are everyone else. And we assume that these sets are not going to change over time. So a malicious agent will always be malicious, a legitimate agent will always be legitimate. All transmissions are synchronous and uniform across receivers. So we're thinking of a broadcast model, all agents receive the same message. And the sets themselves are also static over time, but they are unknown. And so this is the general context that we'll be working in, the general setting. And again, here's the subgraph of malicious agents and the subgraph induced over the legitimate agents. Okay, so the question that we ask in a lot of the work that we do is, what if we had extra information that the network could exploit? And this is through the quantitative measure of trust. So imagine that we have these alpha values, alpha ij values, that capture the likelihood that a link in your network is trustworthy. And so here, instead of just sending values like xi, xj, now you have a tuple. You have the value plus an alpha value, the x value plus an alpha value, where that alpha value is in the range of 0 to 1. So you can imagine 0, meaning very likely that this link is not trustworthy, and 1, meaning it's very likely that this link is trustworthy. And of course, these are stochastic. We don't know these exactly. However, we assume that we have bounds on their expectation. So in expectation, the alpha values will be close to 0, in particular by this epsilon m term and this epsilon l term, which essentially gives you the noise in these observations. So we'll use this concept as a broad abstraction. I won't go into what or how those alpha values are derived, but I will go into some practical examples of this a little bit later. So for now, let's just work within this abstraction. And using this, we want to define a new resilient consensus protocol, which is very similar to the previous distributed consensus protocol, but now these weights are a function of the alpha values. So that's the main difference. And the important observation here is that the resilience of the consensus protocol can be characterized by understanding the properties of this sequence of alphas. So that's the main objective here. And so some of the assumptions are that the graph is sufficiently connected. And what that means is if we remove the malicious agents, the graph over the legitimate agents is still connected. The alpha values, we assume that they're conditionally independent, conditioned on whether the agent is malicious or not. They're independent over time. And the malicious agent or the malicious trust values are distinct. And that's basically what's being captured by this expectation term. So it's saying that in expectation, I can tell the difference between when an agent is malicious or not. And then there's another, the last assumption here is that we allow agents to observe the network over some time t0 before we start consensus. And we characterize the properties of the performance with respect to that t0, but it's arbitrary. And the idea is that under this, in this context, we're interested in seeking stronger performance guarantees than what we could in, say, a classical consensus setting without stochastic observations of trust. And so to understand what exactly we're targeting, I want to look at the nominal, or I want to bring up the nominal weights for consensus. So if we had a way to understand which agents were malicious and which agents were not, then I would like to assign all legitimate agents a weight, a nominal weight, like this wij bar. And then the consensus error term, which is now the actual consensus dynamic at time t after allowing the agents to observe the network for some t0 time steps. And then this is the true average. So this is what I would like to converge to, where now those weights are derived using the nominal weights there. And that difference is the error term. So this is the actual consensus dynamic. This is the nominal case where I don't have malicious agents because essentially I'm using this nominal weight matrix here. And this is a value that we want to understand and observe over time. And so, given that, we want to find actual weights that are a function of these alphas and some time t0, such that I have the following holding, and I want to walk through exactly what is happening here. So this is the error term that I defined on the previous slide. This is just the error in the legitimate node values. And this is the deviation. This is what the malicious agents can induce in the system, in the consensus. And then here's a given probability of error. And so what I would like is that if I imagine I'm looking at this sequence of errors over time, and I take the maximum over all the legitimate agents, then I want this error to be bounded, basically, with some failure probability that I'm interested in. And I would like for that deviation to be finite. So looking back at that graphical interpretation of consensus, if on the left-hand side, or on the y-axis here, I have the values of the different agents, the green are the legitimate agents, the red is the malicious agent value. If I don't use resilience consensus, I don't have these weights here, what I end up getting is some deviation that's produced by the fact that there are malicious agents in the network. What we'd like is something that looks more like this. We want to be able to use resilient weights such that the converged value of the consensus is closer to the true average over time. So that's the problem that we'd like to address by using the resilient consensus protocol. And so, okay, how do we actually understand, how do we achieve these resilient weights? We define a new observation history beta, which is just going to be a running sum of all of the alpha values that I've collected over time, but shifted by 1/2. And the reason that we shift by 1/2 is because we want to be able to look at that beta value if it's positive or if it's negative. So that's the only reason for shifting. And so here, this is what intuitively that beta sequence might look like for a legitimate agent over time. In the beginning, there's going to be a lot of misclassification. So essentially, beta tending towards positive infinity means very likely you can trust this agent, it's trustworthy. And a malicious agent will have a beta value or a beta sequence that looks more like this. And so that's the intuition. Now, we'd like to use this to actually define a trusted neighborhood. So we say that we can trust agents whose beta values are greater than 0. And agents whose beta values are less than 0, we're not going to deem them trustworthy. And so here on the right, I've defined a weights axis. And this is what this looks like. So I'm going to use this definition of a trusted neighborhood that's based on my alpha observations over time. And I'm going to say if my beta is positive, I'm going to basically give it a positive weight here. If it's negative, I'm going to give it a 0 weight. And that's how I'm going to choose these weights to include those alpha values. And so just as an example, looking at the legitimate agent case, what this would look like is that if at time 0, that beta value is less than 0, I would set the weight to 0. In the next time step, if that beta value is positive, then I give it a positive weight, and I continue doing that over time. And in the beginning, I'll have a lot of misclassifications, but over time, we expect this to tend to the nominal weight value for legitimate agents. Okay, so that's just a little bit of intuition here. And so now we have, again, looking at this problem, each agent has access to a tuple, and we use this protocol to update its value over time. In matrix form, so this is just the same protocol, but I want to define a little bit of notation here. So I'm going to separate out artificially the dynamics of the legitimate values and the malicious agent values. And so this is the consensus dynamic. Just to kind of define some of this notation, which I'm going to say these are then the legitimate node weights, so the weights that legitimate agents assign to other legitimate agents. And this is the malicious node weight. So this is the weights that legitimate agents will assign to malicious agents. And then for the malicious agent dynamics, we don't know how they're adjusting their weights or how they're updating their dynamics, their protocols, so we just say that this is unknown. And that's what those matrices are indicating there. Okay, so what does this actually look like? We care about the dynamics, we care about what's happening with the legitimate agent values over time. So if we write that out, and one thing to point out is that these values of WL and WM are used just for the analysis. So the actual protocol wouldn't know which values are, or which agents are malicious or legitimate, but for the sake of analysis and understanding what's actually happening here, we write out the dynamics of the legitimate agents over time. And importantly, this can be separated into two terms. The first is the term of how the legitimate agents are contributing. So how other legitimate agents in the network are contributing to this value here for any particular legitimate agent. And then this is the malicious agent value here. And so what we want to be able to show is that the classification error, the misclassification error is essentially decreasing exponentially over time as I receive more and more of these observations. And then we want to be able to show that both of these terms independently converge to a finite limit. And if we can do that, then that means we can bound the influence of malicious agents on this dynamic over time. And so this is the misclassification of legitimate nodes. So these are the times that a legitimate node was misclassified as malicious. And these are the misclassifications of malicious nodes. So these are the times that malicious nodes were misclassified as legitimate. And so overall, this gives us the error in our, this gives us the error. And then there's the T0, which is the amount of time that I'm allowed to observe the network. And I'm interested in understanding, as I change that T0, how does that affect my consensus? And just as a reminder, the T0 means this is the amount of time that I'm able to observe the network and collect alpha values and compute betas before starting the consensus protocol. Okay, so this is the first result that we're able to show within this setting, which is to say that if we do have these beta values, which is just essentially a shifted sum of all of the alpha values, and we have some noise term epsilon, then we have the following holding, which is to say that the probability of a misclassification of legitimate nodes as malicious and vice versa, the misclassification of legitimate nodes as malicious, is decaying exponentially in time. And the key idea here, and the reason that this holds, is because we're essentially applying the Chernoff-Hofting inequality using the bounds on the expected value of the alphas. And so that's really important. That turns out to be a very important property of these alpha values. And an important corollary of this is that failures or misclassifications occur only finitely often in the limit. So I'm looking always at the asymptotic case, which means that I can bound the influence of malicious agents. And that's really important, and that's basically what leads to the key result here, which is to say that in the case that I'm using the resilient consensus protocol, where my weights are defined using these alpha values that have the properties that on bounded expectation, the resilient consensus protocol converges almost surely. And importantly, this is independent of the number of malicious agents in the network. And so, and the deviation is also something that we characterize. Okay, so this is important because this is a departure from the classical results in consensus. And the reason that this is we can do this is because we have additional information in the network. So what does this look like in practice? So this is the case of flocking, where agents, say, are trying to converge on a particular value, say heading. And this is what this is what it looks like numerically. So essentially here you have a plot of the values over time of your legitimate agents in green. You have a spoofed node, or by spoofed node, I mean like a Sybil agent. And we are still able to converge, all the legitimate agents shown in black here are still able to converge close or much closer to the true average than if we did not use the resilient consensus protocol. And then this is a study on the effect of the time t0. So how long we're able to observe the network. And so if this is the malicious agent input and we have a t0 of 0, meaning you start consensus immediately, you don't allow observation of the network, then you can have a large deviation from the true average, which is this black dotted line. Whereas if you increase t0, so you allow the agents to observe the network for longer before starting consensus, then we can drive that deviation from the nominal convergence point arbitrarily smaller. And that's what this is showing here. Okay, so I want to quickly revisit the assumption that malicious agents are always malicious. And the reason that that's important is because we're expecting this sequence of betas to essentially diverge over time and become easier to classify over time as I get more observations. But if I change the assumption that these malicious agents are always malicious, then I get a situation where this no longer holds. So imagine that now my malicious agents can attack with some probability, PM. And by attack, it means they're just not going to follow the consensus protocol with probability PM. And they will follow the consensus protocol with probability 1 minus PM. So what happens here is that now the expectation of that beta value for legitimate agents will still be the same. It will still look like this over time. But for the malicious agent's case, it now depends on that value of PM. So if PM is 0, so attack probability is 0, you essentially get the legitimate agent case. If the attack probability is 1, then you get the case that we've been discussing up until now, which is this extreme here, and that's favorable for classification over time. But if you can change that PM value, then you can essentially have anything within this cone, and that makes it very difficult for classification. For example, how do you choose a classification threshold in this case? In the past, in the previous work that I was just mentioning, that classification threshold was 0, but now it's not so clear what that classification threshold should be. And so that's the main crux of this problem. And so what we do, just at a high level idea, is to choose the largest beta value that I've seen up until now, use that as a reference, and then using that, define a time varying threshold. So I won't go into the details of that. I'll point to this paper here, which is a recent paper. It'll be presented in CDC later this year. But the idea is that we can still achieve almost short convergence in this case, and we can bound the deviation, even in this time varying case. However, I must say that the time varying case is still very tricky, and we haven't addressed it fully. So it's definitely something to continue thinking about. Okay, so going back to the real-world cyber-physical networks, I want to look at the case of directed networks now to understand how this changes things. So before, in the undirected case, we had some number of malicious agents, and they could appear anywhere in the network, and that didn't matter to us. But now, in the directed case, we're looking at this situation where malicious agents can either be in neighbors, so they're upstream of, say, some value, some node 3 here, or they can be out neighbors, so they're downstream of this node here. And that makes a difference in the following reason, because in the directed graph case, for downstream neighbors, we have alpha values. We have stochastic observations of trust, but for upstream neighbors of a malicious agent, we do not. And so you would think that maybe that's not a problem because I can still, using the results that I just mentioned previously, I can still remove this edge. However, if you look at the agent values over time, so this is the consensus dynamics over time, and I have a true average here, I still get a deviation. And this is true no matter what T0 is. You can make T0 as large as you want. I will always have that deviation. So what's happening here? Why is that happening? Well, the reason is because this agent here cannot understand, cannot learn that this is a malicious agent. And this is, again, just using direct observations. And so there's leakage. What leakage means is that some of the information, the legitimate data is actually leaking out of this malicious agent here, because many times this agent, in many different algorithms, this agent will try to balance the information that it's sending over the network. And so if it cannot properly balance that information, then it can lead to problems such as leakage. And so this is important in many distributed algorithms, certainly consensus, but also many others. So it just motivates the idea that we need to be able to learn, the out neighbors as well as the in neighbors. And that's an asymmetry that comes up in the case of directed graphs. And so that's some work that we've looked at here, where now you have, say, some agent I that would like to understand the trustworthiness of some other agent Q, which could be anywhere in the network. It could be an in neighbor, an out neighbor, or anywhere else. But there's an asymmetry where now this agent has trust values for upstream neighbors or in neighbors, but does not have those for any out neighbors. And in general, you have now these very asymmetric information flows where some information flows are legitimate, going through mostly legitimate agents, and some can be malicious. And importantly, we don't know which situation we're in at any given time. And so here, the assumptions are the same as in the undirected case, but we have to add one additional assumption to the connectivity, which is to enforce that all malicious agents should be observable by at least one legitimate agent in the network. So at least one legitimate agent in the network should have alpha values for every malicious agent. If we don't have that, then we're not sure that this will actually hold. So for now, let's just assume that we have that. And so now, some notation here, I'm going to introduce this indicator variable, which is 1 if Q is legitimate, and is 0 if Q is not a legitimate agent. So that's for some arbitrary Q in the network. And then we define this concept of converging to a true opinion as the following. So if I hold opinion values for every agent in the network, and importantly, opinion values are not the same as alpha values, and every agent can have those in the network. And we want this opinion to converge to the true legitimacy, whether or not an agent is legitimate over time. And so what we want to do is we want to derive an algorithm for learning these opinions, and we want it to be such that these opinions are available for every agent, and that these opinions converge almost surely for any Q in my entire graph. So these are legitimate or malicious agents. And malicious agents here can send arbitrary opinions in the range of 0 to 1. So they can absolutely manipulate their opinions and broadcast these. Okay, so in this case, here's the learning protocol that we're going to use. We're going to fix some arbitrary Q, and we're going to learn agent I's opinion. And then here, we're still going to use these aggregate trust values, the same beta values that we used in the previous undirected case. And we're going to define a trusted in neighborhood the same way that we did before. That if this beta value is greater than 0, then it's in the trusted neighborhood. And then now here's how I'm going to define my opinions. If I happen to have an alpha value for Q, which happens if Q is an in neighbor of I in this case, then I'm just going to use those alpha values to determine my opinion. I'm going to set it the same as I would have in the undirected case. However, if Q is an out neighbor, so now I is not directly observing Q, does not have an alpha value for Q, then I'm just going to use an average of my trusted in neighbors' opinions for Q. And so that's the protocol that I'm going to follow in order to essentially design these opinion variables that are now defined for every agent I in the network, every legitimate agent I. And so what we're able to show here is that for all Q, for all agents in my set, I will converge almost surely to the true opinion of Q, no matter where Q is in my network, after some finite but random time, Tmax. And so the reason this holds is that for the undirected case, we were able to show that this is true for the undirected case, and that was the first result that I had mentioned. And that because this happens, we know it happens after some finite but random time Tf. And the idea is that after that time Tf, where now the directly observing agents have learned the true opinion for all of the malicious agents, then the opinion dynamics become essentially equivalent to the Markov chain where the absorbing states are the true opinions. And then we characterize this new Tmax, which is essentially the additional time that we need for all of the out neighbors to also learn the true legitimacy of any Q in the graph. And so that can be characterized in terms of graph properties, such as the maximum in degree and the diameter of the graph. So this is actually a result that we have put out on arXiv, but haven't actually published that part yet. Okay, so what does this look like in practice? So here's a numerical study. So we look at different types of graphs, different levels of connectivity. And what we're able to show is that essentially the convergence of the opinion to the true value over time. And importantly, we're in the case where the number of malicious agents can be much higher even than the number of legitimate agents in the network because we have these additional alpha values. And then in terms of other topologies, we have also looked at dynamic topologies. And so I won't go into detail, but I just wanted to point out that this is a question that we're interested in and we have studied, but I won't go into too much detail on this. So we've looked at this problem of using stochastic observations of trust in many contexts, many different distributed coordination algorithms that these systems might have. For example, consensus, also resilient distributed optimization, and hypothesis testing in order to do distributed event detection. The main idea here is that using the stochastic trust observations, these alpha values, for weighting the inputs of different agents in the system can lead to provable resilience in cases that are very difficult to handle otherwise if you don't have such observations. And so I want to talk a little bit about what this looks like in practice, because this is not just in theory, this is actually something that we have implemented and looked at in practice. And so this will also give some ideas of what these alpha values might actually be, where they might come from. So here's one practical example, and this is the case of detecting Sybil attacks through wireless channels. So imagine on the left here, you have a legitimate network. On the right here, you have a Sybil attack where you have one physical malicious adversarial agent that's essentially spawning identities in the network that don't actually exist. So these are Sybil identities. And if you just look at the values that are being transmitted by those Sybil entities, you can't tell that this is happening. The values are distinct, the IDs are distinct. But if you have some additional information from the physicality of the network, the fact that these values are actually being transmitted over wireless signals, then now you have an additional piece of information that can give you a clue as to whether the agent is actually unique or not. So in this case, this is an angle of arrival profile. So this is actually the power profile of a wireless signal that's arriving at different agents over time. And for legitimate agents that are not Sybil entities, you can see that they qualitatively look pretty distinct from each other. But for Sybil entities, they look very similar to within noise. And so that's the main idea here. And again, we're in the case where transmissions are all uniform. We're in a broadcast model here. So this is what this looks like in hardware. So here I have a malicious agent. I have a legitimate server as well as some legitimate clients here. So this is my physical network. This malicious agent is spawning a cluster of Sybil entities here. And this is what those angle of arrival profiles look like. From here, I derive an alpha value that essentially captures or measures the similarity between these profiles. So this is just to give you an idea of what this might look like in practice, where those alphas, one example of where those alphas might come from. And so these are actual measurements, and we were able to show that indeed an alpha value can be computed from these measurements, such that for each link, we have a certain property on the expectation of the alpha values. And this is that key property that we needed for our results in the resilient consensus case. And so this is what it looks like in practice. So this is just a histogram of empirical data of alpha values collected in the case of a Sybil attack. And you see that similarly to what was predicted by the theory, we do have this concentration of alpha values around these extremes of the spectrum, which helps with the classification problem. Okay, so I want to just show a little bit of what this looks like in practice. So I'm going to give a practical example, and I'm going to show what this looks like in an actual implementation. So as an example that I'm going to use, we look at the case of traffic estimation. So the idea is that you have several agents that are driving on a road network, and they're estimating whether or not that road network is congested. So they're sending values of whether, like 0 or 1, whether the traffic, the road is congested to a fusion center, and the fusion center is returning a response about whether that segment is indeed congested. And so this is what it looks like in an actual experimental setting. So you have several agents, several robots, and you have Sybil identities, which are these more faded agents. So this is an actual Sybil attack that we launched in the laboratory. Safely, it's all within a controlled setting. But essentially, there's a server up here or a fusion center up here in the corner that's also collecting these wireless signatures of all of the transmissions in the network over time. And this is what they look like in the case of this experiment. And again, here's the histogram that shows the alpha value on the x-axis and the frequency on the y-axis. And so what you see is that here, we also have the case that these alpha values are very concentrated towards the ends of this spectrum. So this is, again, this essential requirement, which we show in practice and in theory. And so this is what it looks like. Basically, all of these agents are simultaneously detecting whether or not a segment is congested. Congested means there's more than one agent on a particular road network. And this is the ground truth of whether a road segment is congested or not. And this is the estimation. So the oblivious fusion center doesn't have access to these alpha values, and it's just returning a value that is being reported. Even so, for example, even wherever a Sybil agent appears on the network, it thinks that this is a congested road network. And then if you have the alpha values, then you see that there's a large gap in performance. We're able to recover a lot of the performance of the distributed traffic estimation case when we have alpha values. So a quick summary of the stochastic trust framework. So this is a general framework. I talked about one example, which is using wireless channels to be able to extract these alpha values. So that's one example, and it shows the power of being able to think about resilient consensus in this way. But the question of more examples of alpha values is still open, and so that's a general problem. However, there's this important characteristic that I want to be able to point out again, which is that in expectation, they should be distinguishable from an attack, no attack case. And importantly, this concept provides a bridge between theory and practice. So now I want to just talk a little bit about network measures of robustness, because it's not always the case that you have these alpha values. So what do you do in this case? How can we use some of the graph structure-based concepts of resilience in a robotics system? And so I'm just going to put up here, so here's a graph, and particular concepts of connectivity that we use that come up a lot in robotics applications are, for example, this R reachability. And so intuitively, I'll describe it as follows. If I take some set of nodes, I'm going to call that A, and I look at how many external connections from that set A some node VI has within the set A, then the number of external connections tells you the R reachability. So in this case, in this example, this node would be 2 reachable. And then if you look at all the possible sets A that you can construct, then and you look at what that R is, then that's the R robustness. And importantly, for these concepts of connectivity, it's been shown that different forms of consensus, such as median consensus or the WMSR approach, can be achieved. So this is no longer average consensus, but essentially what you're doing is throwing out the extreme values in order to still arrive at some form of consensus. So here, we do definitely have limitations now on connectivity and the number of malicious agents that we can tolerate. But we want to understand what we can do in this case. So why these properties are important, of course, you all are very familiar with properties of resilience and connectivity, but I want to show you in practice what this looks like. So here's a group of robots, and they essentially are connected via a disk graph. So assuming that they're within some distance from each other, we have an edge. And then this is what the graph looks like that's induced over these agents. And I have one malicious agent in the network. So if these agents are trying to achieve consensus on heading, meaning they're all trying to achieve the same heading direction as they move through space, what you will see is this malicious agent right here can essentially cooperate in the consensus protocol. And then when the topology reaches a critical point, so it's very weak right here, the malicious agent can stage an attack and essentially confuse the consensus algorithm and create a break in this network. So this is what this might look like in practice in a multi-robot system. So this is something that we would like to be able to avoid, and we do have some work on being able to maintain resilient I would say robust connectivity as agents move through the environment. Some of the challenges here are because sometimes the environment will create a trade-off with being able to maintain these formations in your multi-robot system. And so we have some work that I'll just point to here. But the point that I'd like to make is that we do need these graph topological, essentially resilient or robust properties to hold. However, it's not always possible because we don't always have graphs that are very nicely connected, very robustly connected. In fact, many of the graphs that we're looking at in the multi-robot space might look more like this. So here you have agents that are distributed over an environment. They might be locally very nicely connected, but sparsely connected globally. And so what do we do in this case? We know that we cannot achieve global consensus in the case that, say, we don't have alpha values and we're just relying on network structure. But a question that we ask here is, can we still aim for some form of local consensus in these networks? And so now this is the highly heterogeneous connectivity case. This is the last case that I'll talk about today. And I want to just point out a few of the ideas that we're looking at in this space. So here, community consensus is something that we are essentially looking at now, which is to say that we want all agents within a particular community, let's call this V1 and V2, to be able to agree on a value. And we assume that there does exist some malicious agents FI in each cluster, or in each part of the graph here, each community. And we wish to characterize the conditions under which we can still achieve local consensus in these different communities. And importantly, agents are only aware of their neighbors. They're not aware of which community they're a part of or which community their neighbors are a part of. So this is important, it turns out to be important because now we have a balance between how connected a community is within itself and how connected that community is outside to other communities. And so Ki is the maximum number of neighbors that a single node will have in another distinct community. So Fi is the number of malicious agents in some community I, Ki is the number of external edges in some community I. And so this concept of community consensus is actually fragile. And there are different ways that it can fail. So one is that the legitimate agents are overwhelmed locally, and so they can converge to whatever values the malicious agents are inputting, or they are fragmented within a community, and so they converge to different values within the community. And so this is the case where they can be overwhelmed locally, and essentially there's the degree condition that's being violated here, where this agent, we're looking at this one in this example here, is overwhelmed by malicious data that's coming from malicious agents within its community and other communities. But in this case, for community consensus, even legitimate agents that are in a different community are going to create a challenge for this community being able to actually converge locally. And then this is the case now where a malicious agent or even just another community or agents or edges to other communities will violate the robustness condition. Okay, so I don't want to go into too much detail here. The point that I'm trying to make, and I'd like to have you take away from this, is that the concept of even community consensus, if you don't know what the communities are, is difficult to come about. And for a particular case of median consensus, where now I'm taking essentially a weighted average of my own value plus the median value of my neighbors. In this case, we are able to characterize sufficient conditions over which you can actually achieve median consensus based on the number of malicious agents within each community and the number of edges going out of the community. And importantly, this community consensus concept allows us to tolerate more malicious agents. More malicious agents. And the reason is because we have Fi malicious agents per community and not globally. But importantly, we're not achieving or even aiming for global consensus in this case. So we're not violating the classical resilience results. Okay, so just to kind of make a distinction, in global consensus, all agents are agreeing to the same network value, and the requirements on connectivity are very restrictive, especially in these sparsely connected, highly heterogeneous connectivity cases. And so that's why we sought a different form of consensus, community consensus, where agents only within a particular community have to agree on a value. And this is still not trivially achievable, but we can tolerate more malicious agents in the overall network by looking at the problem this way. And in the multi-robot setting, there are many places or many cases where you do need to converge locally and perhaps not globally, like, for example, measuring the temperature of different rooms in an environment, etc. Okay, so I'll just conclude now by saying that multi-agent cyber-physical systems bring many challenges to the space of resilience. And we need to consider the presence of different aspects like malicious agents, dynamic networks, highly heterogeneous connectivity networks, and formalizing this notion of trust that uses the physicality, for example, allows for new mathematical models and also new resilience frameworks that we might be able to use in these settings. So a few open questions that I'd just like to leave with the audience in the things that are pertinent to, say, many of the multi-robot systems that we are interested in are characterization of more general forms of alpha. So I gave one example of wireless trust values. We're interested in looking at more. Proving resilience for highly dynamic networks. So in this case, you should think of, in your mind, the example of the agents, the autonomous vehicles going through intersections or merging onto, say, the on-ramp of a highway. They have to be able to make decisions. They have to be able to reach consensus in a highly dynamic way. How do you do that with malicious agents? This is very difficult. So we're not looking at the asymptotic case here anymore. We're looking at the finite time case. So how do you deal with convergence? How do you deal with characterization of deviation? In today's talk, I talked purely about the synchronous case, but as was rightly brought up yesterday in a lot of the talks, the asynchronous case is really important. It's very practical. So how do we deal with that? As of right now, we were looking mostly at how to deal with larger numbers of malicious agents, but we haven't dealt with the asynchronous case yet. And also the time-varying legitimate and malicious agent sets. I alluded to the fact that this is a very challenging problem, and it's also connected to the highly dynamic network case. But essentially, you have, what if your sets of agents can change over time? And that could be the case of strategic malicious agents. It could be the case of just agents going in and out of the network very quickly and having to still reach consensus so that you can have a lot of practical applications. Okay, and then I'll just put up a few acknowledgements to the students in my group, my collaborators, and also sponsors. So much of the work that was talked about today, I'll just highlight a few of the students that did most of the work on those problems. And with that, I will just leave up this last conclusion slide.
So thank you very much for the talk. So actually, I'll start with maybe a couple of questions. So one is regarding these trust values. So how should one think about the way these are generated? So is it like packet dropping? Is it like I know you try to ping pong and see if you get the same value? Like what would be the more sort of physical interpretation of the alpha value?
Yeah, that's a great question. So essentially, you can think of the alpha value as some way of cross-validating information that you're getting. So in the Sybil attack case, an agent is saying that it's a unique agent, it has its unique value, its unique ID. And if you're just looking at the values to make a determination of its legitimacy, it's very difficult to understand that a Sybil attack is actually occurring. And so in this case, we're looking at, say, the wireless transmission to understand their uniqueness. And so you have a way of cross-validating the claim that the agent is unique. And that's how you should think of the alpha values, as some way to sense something in the network that will give you a clue as to whether the agent is, the value or the data that's being transmitted is actually legitimate.
And maybe a follow-up on that is like, I mean, one of your earlier theorems essentially gave, in some sense, a sufficient condition for some notion of convergence. But to what extent is it? I mean, is there any result saying, okay, like under this or that distribution on the alphas, there's nothing you can do, or like, so is there kind of a converse of that?
Yeah, that's a really great question. So we have looked at this question of the distribution of the alphas. As of right now, the most mild assumption is the bound on the expectation.
Yeah.
There you're not making any assumptions about the distribution. But if you do have information about the distribution, then you can make stronger claims. Like, for example, you can have convergence rates. So yeah, it's definitely valuable. If you know something, even just bounds on the variance is stronger than having just bounds in the expectation, and you can utilize these for faster convergence and convergence rates.
All right. So thanks for answering sort of my curiosity. So I'll take your questions from the room now.
Thanks, Dan.
data detectors, modules that give us this information of who's talking.
Yeah.
Can the same sort of abstractions be built here? And also, related question is, once you have these modules, do you think you can have modular design of these protocols? For example, it seems like in the community, if we agree on the location, then you can agree on the direction that you go as a community. So
Yeah.
you can build one.
Yep, that's a really great point. So I think one of the key aspects and elements of the alpha values is that they capture orthogonal information that's not already present in, say, just the value that's being transmitted. And that's maybe one key difference, is that you have extra information that you're bringing into the coordination algorithm. Now, the question of whether we can think of that as a new method for fault detection and then layer on some new algorithmic approaches, I think there's a lot of, that's a really interesting idea. And there's probably a lot of work that can be done in that direction. So yeah, it's an interesting point.
Nice talk. So you mentioned this 2023 papers on the transactions where you maintain the R robust property as the robots move. Is that a guarantee? I mean, are you making some assumptions to prove that property?
I see. Okay, yeah, the control barrier function ones, the video that I showed, but I didn't talk into too much detail. Yeah, so the main problem there is you're trying to maintain a resilient formation as the agents are moving through an environment, which is actually, and we're actually using the algebraic connectivity of the graph to lower bound the R robustness. And so you can compute that in a distributed way, and you can do this with a multi-robot system. The main difficulty is if you're in free space and the agents can move anywhere, then you can do this fairly easily. But if you now have restricted environments, you have environments that have obstacles, you have environments that have hallways, then there becomes a trade-off between the formation that you can keep and the resilience of your network and the mobility of your network. And so that creates an inherent tension. And so the point of that paper and what we looked at there was understanding when the environment will force these trades-offs. So being able to identify parts of the environment that maybe you cannot traverse while still maintaining resilient topologies. Yeah.
So here is the coordination somehow mobile, or it's still very local room for operating the facility?
Yeah. So you mean for the consensus part? Yeah. Yeah, so that's a good question. So there for the consensus part, we're just using previous work, the WMSR, which is a separate paper. And then, yeah, so that there is a centralized aspect, which is the global path planning aspect that you do need to understand. Yeah, so you're doing some local information gathering to understand locally what the topology of the network is, but you also need to have some global information about the path.
Yeah, this is related to the question that came up yesterday. It's how to do federated learning with malicious participant, and it seems like this alpha approach could be one of the ways to face it, right?
Yeah. Actually, we were very interested in the federated learning application, and we started looking at that. But then we realized that even for the distributed optimization case, there was some major obstacles that we had to figure out how to resolve first. And so that led to some of the work that we did in resilient distributed optimization. And I think now that we have a few preliminary key results in that area, we're very interested in looking at the federated learning case. So I agree, there's a natural bridge there.
Hi, well, thanks for the talk. One technique that's used in many consensus protocols is sharing suspicions. So if I have an alpha value on J and someone else also does, that can boost information about failures. Has that been, have you taken account of that? Is that part of any of the?
Yes. Yes, so that's a great question. So we have thought about that. We've thought about essentially third-party information. So you're sharing opinions with other agents, and we've looked at the case of using that to speed up your ability to classify who you can trust and who you can't, or who you believe to be malicious and who you believe to be legitimate. And we do have a paper on that with a collaborator from this community, actually. And the paper is called Crowd Vetting. And so we've looked at that. And essentially, you're using third-party information to try to make decisions faster or classifications faster. But I still think there's a lot we can do in that area. So we're just really scratching the surface there.
All right, so let's thank Stephanie again. And now we move into our versions of sort of robots systems. So we move straight to the next short session on robots on the plane.
So the first talk will be about robots playing tag by Nicolas Bonichon, Arnaud Castet, Cyril Gravoy, and Nicolas and Cyril will give the talk.
Hello. Okay. So today we will play to the free stack problem in IL1. So let's start. So the context is the following. A robot is in charge to wake up a set of robots following given the following rules. Is that to wake up a robot, you need to meet the robot. You need to be at the same point. And once other robots are awake, they can awake all the team. So the goal is to wake up efficiently the team and to minimize the make span. So the robots are constrained to move in some planes. So let's consider the Euclidean plane, and they also move at a constant velocity. So it means that what we want to do is to minimize also the distance to wake up the last robots. Okay, and also what we would like is to have a schedule which is efficient to compute. So let's try a demo. Okay. So should look to this. Yes. So you start. And okay, it freeze. Okay. So let's. Okay. It move. Okay. Anyway. Okay, I have a classical slides in case. Okay, so again, you want to wake up this set of sleeping robots, and the orange one is the active one. Okay, so here is an optimal solution. You go here and here, and okay. So again, what we want to minimize is a length to the last robot. Okay, here is another example where you can see that it looks much more closer. Okay, so where comes this problem from? So this is a problem due to the main Mitchell and Rook, and this is a famous 35 problems. And today there is about 100 references to this problem. Okay, so let's try to formalize a little bit the problem. So the input is a set of robots. So we have n sleeping robots, and one is the source, which is the active robot. And the goal is to produce this tree on the left. That is the schedule to wake up all the robots. Okay? So the wake up tree is this binary tree. and we want to minimize the depth of this tree. Okay, so in this example, this is the green path. Okay, so there are many variants for this problem. You can change the matrix. You can constrain the robots to move along the edges in a graph. You can play this game in 3D or whatever you want. Okay, as I said, this is maybe not surprising that the problem is NP-hard for many variants, and this is also NP complete in 3D for L2, and there are many others works that show that essentially whatever the variant is, it's NP complete, except one which is in 2 dimensions when the metric is L1. Okay, good. The positive ties are approximation result, and mainly this result due to Mitchell is a 1 plus epsilon approximation, whatever the dimension is and whatever the metric LP is. And they gave a nice algorithm based on approach coming from the Traveller-Sellman problem. You subdivide the grid in small pieces, and at the very end, what we have to solve is the problem in a small square of a given size epsilon, and try to show that you can solve the problem in a constant time. Okay, so this constant actually depends on the dimension, on the norm, and what we have to see is that this algorithm works only if the epsilon is quite small. Okay, and due to this factor here, this is a very huge constant. Okay? So maybe let's make a comparison with the FPT problem and the TSP problem. Okay, what is interesting in the FPT problem is that if you look the distance to the farthest robots, obviously you need this time to wake up the robot. Okay, so if the distance is r, you need a depth of at least r. And the interesting point is that you can always build a tree of depth no more than a constant time r. And this constant depends obviously on the norm or the dimension, but this is an absolute constant. Okay, but obviously the two problems differ a lot, because in the free stack problem we are interested in the depth of the tree, whereas in the TSP is the total weight of the edges. So this is not more constant. Okay, it depends on the number of robots. So in the free stack problem, interesting point is that the depth does not depend on the number of nodes. Okay, so currently the best bounds about this constant. So the goal is really to catch the smallest possible constant here. Okay, so for L2 this is no more than currently this is no more than 10. Good. And again, this constant play an important role when you use approximation scheme. So our contribution is the following: we consider the Manhattan distance, okay, and the two-dimensional problem. So what it means is we restrict the moves to be horizontal or vertical. Makes sense in warehouse problem. And the main contribution of the paper is that the wake-up constant, the smallest constant you can achieve to wake up a set of robots at distance r is 5r. This 5 is optimal one. And it implies that for L2 you can do 7 dots. Okay. Clearly, this is we have also a generic algorithm that shows that we can achieve this 5 with a linear algorithm. So we can construct in linear algorithm a wake-up tree of depth at most 5. And this is more general because I will not detail because the full version is 50 pages. And actually, whatever the constant, you can always construct in linear time tree. So it applies to L1, L2, or whatever you want. And we also show that whatever the norm you consider, you can really bound by some absolute constant. And the constant actually depends on the golden ratio, on the pi of the norm, which correspond to half the circumference of the norm. Okay, so this is 2Ds, it corresponds to the usual pi. Okay, anyway, so I will concentrate now my talk in this 5. Where comes this 5? So first, we'll show that you cannot beat this 5, because if you look at the right, okay, so I will, this is a ball of radius 1, which corresponds in L1 to a square. And if we put 4 robots, and we start at the middle, you see that you need 1 step to wake up somebody. And at this point, you are two robots awake, and 3 robots to wake. So you need two legs, in a sense, to wake up the last robot. So you need to pay 1 plus twice this diagonal. And in L1, this diagonal is equal as length 2. Okay? And the same argument applies to L2, and you can show that you need to have 1 plus 2 square root of 2. That seems clear. Actually, this is slightly more general, because if you take an arbitrary norm, which can be defined as a symmetric convex, and in convex set theory, there is a natural parameter which is defined by this crazy formula, and it just corresponds to half the perimeter of the largest n-squared parallelogram in the unit ball. Okay, and what happens is that you can generalize the lower bound and show that whatever the norm, you always have to pay a wake-up constant to be at least 1 plus these two legs. Okay? Good. So now I will concentrate my attention on the upper bound. Where is this time comes from? Okay. And the strategy really depends on the number of robots in the densest square. Okay. So we split. So this is the ball of radius 1 in L1, and we split in 4 smaller squares, and we look the densest square. So let's call N0 the number of robots in this. Okay? And what strategy is try to wake up this square, go back to the center, and then in parallel wake up the 3 other squares. Okay. So to make this clearer, maybe you can consider the case where N0 is 1. Okay, this is very simple case. So you go to wake up somebody. In time 1, you go back, it's time 2. Now you are 2 robots awake. Everybody choose 1 square. So in time 3, you can wake up the 2 others. On the last one, you can wake up as you want, because the distance between 2 points in the ball is at most 2. So it's 3 plus 2, it's 5. It's fine, it's very easy. As you will see, it's when N0 change, you need another approach to prove that it's 5. And when we'll see in a moment, when N0 is 7, you will see it's completely different. Okay, good. So for large N0, not large N0, but okay, for larger than 1, we proceed with 3 key lemmas. Okay. So the first lemma say that if we have at most 5 robots, we can wake up these robots in at most time 2. Okay? And we will use a lot this. Okay? So intuitively, this 2 is very nice, because in 2 steps you wake up everybody in the square, 3 steps you go back, and then you can in parallel wake up the other squares again in time at most 2. So it gives 5. Okay? Unfortunately, it does not work when we have 6 robots. And it looks crazy, but if the points are like this, you need more than 2.1. That's okay. That makes life much more difficult. So what we can use in another key lemma that say that if we have 6 robots, we can wake up and go back to the origin in at most 3 times. That's good. Unfortunately, it doesn't work for 7. Okay, but we will see. So when we have more points, we consider the triangle. Okay, and if we have a triangle of size length d, we can wake up everybody in 2 times, times 2d. Okay, and this is very complicated proof that use some recursions, and we split this triangle in 4 smaller triangles and so on, and we have 13 cases. That's okay, very complicated. So let's assume we have these 3 lemmas, and I will try to convince that now it works perfectly. Okay, so if we put all together, we have the following strategy. So if the tensor square is 1, okay, you win, it's easy. 5. Now it's n0 is 2, 3, 4, 5. We use this lemma that wake up the square in times 2, go back is times 3, and because n0 is at least 2, it means we have 3 robots in the middle that are awake, and it's good because we have 3 remaining squares to wake up, and it's okay. We can do in 2 steps more, so it's 5. So now if n0 is 6, 7, 8, 9, 10. We use this lemma to wake up and together at the origin and try to wake up the other squares. Okay, but it's a little bit. There are some subtleties because. So let's consider the case just for illustration. What's happening when you have 7 robots in a square? So you first use a lemma that wake up 6 robots in time 3 with the go back. Okay, so it means that when you are here, you have 7 robots awake. 1 is left, is not awake, and you have at most 7 robots in all this. Okay, so it means that one awake robot will wake up the last robot here. And now you have the other robots can split, and in parallel they will use 2 robots to wake up a square, and it's fine because it's 7, so we can use the lemma with 5 robots each, and we will catch we wake up all the robots in time 5. Okay, good. But it works on up to 10. So at 11, we do differently. Okay, at 11, what we are sure is that one of the triangle must contain 6 robots or more. What we do now, we recurse in this small triangle, wake up everybody, go back, and because we have 6 robots or more, with the start it's 7, we can wake up the 7 small triangles in parallel, and we are safe. Okay. Okay, the proof is very ugly in a sense because what we do basically we try to make a proof for each n up to 41. Okay, so that's but it works at the end. So we to be sure that we got all the cases, we make a program to see what's happening recursively. So this is the application of the lemma for the triangle. When you have all this recursion, so you go to the tandest triangle and make recursively stuff. Okay, good. So I will now finish with some conclusion on open problems. So we have shown that the optimal constant is 5 for L1. And for every norm is something between, 1 plus half of the perimeter of the largest parallelogram inscribed in the unit disk. And this is no more than absolute constant 9. We also show that in linear time we can construct such a solution. Interesting point is that the algorithm that shows that we can linear get this 5 is not the same as in the proof. The proof does not lead to a linear algorithm. It's an n-square algorithm. But because we know that it's 5, we can plot this pi in another algorithm and get the linear time. So the linear time algorithm is not does not come from the proof. I'd like to finish with some problems. So obviously, what's happening about the constant for the plane, for the Euclidean distance. We know that it has to be 1 plus 2 square root of 2, which is 3.8. And recently, the 7 has been improved to be to 4.6. And we know that when n is large enough, the conjecture has to be true. It has to be 1 plus 2 square root of 2. But it seems very, very complicated. Already, if you have only 8 sleeping robots, we don't know if the conjecture is true, if you can wake up everybody in the 1 plus 2 square root of 2. It seems to be crazy, but it's still a long way to fill the range 8 to 280. Okay, good. And we think that maybe it could be true that the real conjecture is that the worst case is when you have 4 robots to wake up. Looks crazy, but it seems to be true at least for 5 on for L1 on the perhaps L2. Okay, so thank you.
Thank you. We have time for a quick question.
Yes. Generalize to it crucially depends on the fact that you can scale, so it has to be a norm in a sense. So not so clear. I don't know. The problem when you look graph on weighted graphs, it looks very differently. So for surface, I don't know. It's a good question.
Any other questions? Right, thank you. Next speaker. Okay. So next we'll hear a talk about dispersion of robots by Yuichi Sudo, Masahiro Shibata, Junya Nakamura, Yongkwan Kim, and Toshimitsu Masuzawa, and Yuichi will give the talk.
Yes, thank you. Hello, good morning, everybody. This is Spain, so I should say hola. I am Yuichi Sudo from Hosei University, Tokyo, Japan. This is a joint work with Masahiro Shibata, Junya Nakamura, Yongkwan Kim, and Toshimitsu Masuzawa. Today, I'm going to talk about our recent results on dispersion problem about mobile robots. Okay, first, let me introduce mobile robots or mobile agents that we can refer interchangeably sometimes. And in this talk, we call them mobile robots. Okay, mobile robots are computational entities that autonomously migrate from node to node on graphs. And these robots can communicate with each other if and only if they are co-located. And their goal is to solve a common task or problem. And this pattern problem was introduced Augustine and Moses Jr. in 2018. This problem is very simple. Initially, K robots are arbitrarily positioned at nodes of a simple, undirected, and connected graph with n nodes. And the number of robots, K, is at most the number of nodes, n. The goal here, the goal of this problem is to ensure that all robots are located at distinct nodes. In other words, we want to ensure that the system eventually reaches a configuration where each node contains at most one robot. Okay? And the computational model, each node on a graph anonymous. I mean, the nodes do not have any identifier, IDs. But edges are uniquely labeled at each node. We call them port numbers. The domain of port numbers is the integers from 0 to the degree of that node minus 1. And the robots are labeled with unique IDs. And they can communicate when they are collocated, and they can recognize the incoming port. The incoming port is like this. Look at this figure. When this robot comes from the node on right to the middle upper node, then this node realizes that, yeah, I've come to this node via port 3. That way, its incoming port equal to 3. Okay, and we consider synchronous executions. In each time step, all robots execute the following 2 actions synchronously. The first action is communication and compute. The robots communicate with the co-located robots, update their memory, and compute the next destination. Then, in the second action is move actions. They move to the destination neighbor or stay. Okay. And we consider 2 settings for the dispersion problem. The first one is a rooted setting. This is a special version of the dispersion problem where all robots are collocated initially. Okay? And in the general setting, we do not make any such assumption. And there are many algorithms in the literature for dispersion problem. And many parameters appear in time complexity and space complexities, such as the number of nodes n, the number of robots k, the maximum degree delta, and the diameter d. Yeah, of course, these are the standard notation, but okay, look at this parameter mk. This is the maximum number of edges of any induced subgraph with k nodes. Here, k is the number of robots, like this. Please notice that this parameter mk equals k squared in the worst case, even in a sparse graph when k is small. That is, k equals order square root n. Okay? And we have, dispersion algorithms are classified into 2 types. DFS-based types and BFS-based types. BFS-based algorithms are faster than DFS-based algorithms when both diameter and maximum degrees are small. However, generally much slower than DFS-based algorithms in the worst case, especially either diameter or maximum degrees is large. Okay? So we, in this talk, we focus on DFS-based algorithms here. Oh, sorry, it doesn't work. Okay. And for simplicity, we assume the maximum degree is not super polynomial in K here to parameterize complexity thoroughly by the number of robots K. Then we can simply illustrate time complexities and the space complexities of dispersion algorithms, DFS-based algorithms. And in the rooted setting, simple DFS can solve the dispersion problem quickly with a small space. And a series of studies aimed at reducing overhead in time and space complexities in the general setting. And ultimately, Karani and Sharma achieved zero overhead in the general setting. I like this paper very much, a very nice algorithm. But this is an open question. It is possible to break the order k squared running time barrier. And we answer in this study, in this paper, yes, it's possible. We present 3 algorithms. First, we present the first algorithm in the rooted setting that breaks order k squared barrier in the running time. This algorithm is space optimal and near time optimal. Okay. And second, we present a space optimal and near time optimal algorithm in the general setting. Then we show that time optimal algorithm can be obtained if a linear space per robot is available. Okay, before presenting our algorithms, let me explain a simple DFS algorithm in the rooted setting introduced by Augustine and Modest Jr. in 2018. This algorithm serves as the foundation for the all DFS-based algorithms in the literature. This algorithm is very simple. Initially, all robots are collocated at the starting node S by the definition of the rooted setting. And the goal is to settle those k robots to arbitrary k nodes. Robots settle at nodes are called settlers, and unsettled robots are called explorers. Okay? And the settlers never move once they settle. Okay? Settlers remain stationary, acting as local memory, like whiteboards. And each time the explorers find an empty node, they settle one robot at that node. Here, an empty node means represents a node without settler. Okay? And this is a suit code. Okay? First, this algorithm settles one robot at the starting node S. And then, as long as explorers still exist, explorers invoke this subroutine function probe. Okay? And this, And this function finds an empty neighbor of the current node if it exists. And if an empty neighbor is found, then all explorers move to that empty node and settle one robot at that node and record the incoming port on the settler's memory as a parent pointer. And if no empty neighbor is found, all explorers go back to the parent node by the recorded port. We can easily observe that this simple DFS algorithm can solve this Persian problem. So how to implement this function, some module probe? This function finds an empty neighbor if it exists. This function has been implemented in a very naive way in the literature. That is, all explorers jointly visit each neighbor of the current nodes one by one to find an empty node. So each instance of probe requires a linear time, theta of k time. Since there are at most k minus 1 non-empty neighbors, an empty node can be found in order k time if it exists. So it requires theta k time. So we require k squared time in total because probe is invoked at most 2k minus 2 times. Okay? So may you have a natural question, why do all explorers move together? They could visit neighboring nodes in parallel. But simple parallel search doesn't work. I mean, it doesn't improve the running time. If we search empty node in parallel, simply the explorers finish this function probe in order of k over the number of remaining explorers time, right? And the number of remaining explorers decrease from k minus 1 to 1. So it seems that probe function in total requires sum from I equals to 1 to k minus 1 or the k over I. So yeah, it seems, yeah, we can see a harmonic function, harmonic number. So it results k times log k improvement. But unfortunately, it's not correct. This function probe may be invoked to k minus q to k minus 2 times in the worst case, not k minus 1 times. So no harmonic number appears in this time complexity. Actually, we have a worst case scenario where we require k squared time in total for this algorithm. So we need a clever way to implement probe with in parallel. Yeah, the key idea of our algorithm is to help each other. I mean, okay, or when this explorer now invokes this submodule probe, and he wants to find an empty node, and then he moves to some neighbor, and if he finds a non-empty node, then a cetera must exist there. Okay, so then he says, "Hi, cetera, please join us." Then this cetera joins this function probe. Okay, then these two robots visit to other nodes, and if both of the two nodes are not empty, then other two robots newly joined this probe function, okay? So at each repetition, the number of robots engaging in this function probe became doubled until an empty node is found. So this function finishes in order log k time. And when we finish this function, we can let the helping ceteras go home at the end of probe. So no problem. So we can achieve this function that finds an empty node in log k time. So yeah, we invoke this function at most 2k minus 2 times, so we can achieve order k log k time algorithm in total. Yeah, so yeah, we can break the order k squared barrier in the running time. This algorithm is space optimal and near time optimal. Yeah, this is the second result. This algorithm works for the general setting where the robots are located arbitrarily. Yeah, due to time constraints, let me skip how to combine this algorithm, our algorithm, and the existing general algorithm, general setting algorithm. Yeah, but anyway, it works. If you are interested, please read our paper. Okay. And the third one is also for the rooted setting. If linear space is available, each cetera can remember all non-empty neighbors. Then we can show that running time is linear by detailed analysis. Yeah, we can't show the data analysis here due to time constraints, but roughly speaking, analysis is like this. With linear number of bits per robot, we can modify the first algorithm so that the explorers invocate probe not 2k minus 2 times in the worst case, exactly k minus 1 times. It invokes probe if and only if they visit an empty node. And this function requires only order log k minus log the number of remaining explorers time. Thus, the total running time is blah, 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 and we can use Starling's formula. Then we achieve linear running time. Okay. And this is summary of our result. And one of the most interesting open question regarding this problem is that all our algorithm, inherently require the synchronous environment. Okay, but some existing algorithm, for example, this one works in asynchronous environment. So. Question is there a little of k-square time algorithm that works in the asynchronous environment? Okay, that's it. Gracias.
Thank you. Any questions? So among all these algorithms, if the graph is planar,
Okay.
sorry,
Question.
go ahead. So if the graph is planar, do you know which of these algorithms is the best one to use?
Sorry, when?
If the graph is planar.
Planar.
Yep.
Oh. I'm not sure, but when the graph is planar, generally the maximum, not maximum degree, but on average, the degree is so small and the number of edges, the graph is sparse. So then, sorry, but even so, even graph is sparse, but existing algorithms depends on, sorry, very slow, sorry.
It's okay.
Yeah, this parameter, mk, and this parameter is still k squared, even a sparse graph. And so, even for the spanner graph, maybe our algorithm was the best for the synchronous setting.
Do you have a question?
So in the case where, so I'm interested in the assumption that communication is only possible when agents are co-located on the same node. So which one of the assumptions is critical to avoid this behavior of agents actually kind of fluctuating back and forth between nodes? Especially, I guess, probably some of the memory assumptions. Can you maybe talk a little bit more about that?
Sorry, you mentioned about the assumption. The robots can communicate with agents only if they are collocated.
Yeah.
And then, sorry, the question is?
How do you avoid the fluctuation? So agents making a decision of where to go next and then having to backtrack.
Sorry, I don't know about the fluctuation. Sorry.
Okay. Yeah. So it's from the fact that they can't communicate. So they have this communication only when they're at the same node. And so do you ever get into a situation, or I guess which assumption, if you were to relax it, would you get into a situation that agents might choose a different node to explore and then have to possibly backtrack? I guess, for example, if you were to have severe limitations on memory, etc.
So you say if we relax assumption, so that for example, the robots can communicate with neighboring the robots on the neighboring node, yeah, then we can easily decrease the running time. Yeah, but sorry, even for this problem, okay.
Yeah, okay, that makes sense. We can talk about it more coffee break.
Okay, thank you.
Thanks.
Okay, so let's thank the speaker again.
Thank you.
Right. Now we move from dispersion to gathering. Next talk is by Fabian Frey and Koichi Wada, and Fabian will give the talk.
Okay, let me try to keep on time. If I'm right, I have minus 15 minutes. But, okay. All right. So, yes, I will talk about distinct gathering on the round robin. I should speak in the microphone. And this has been a long-standing open problem for something called autonomous mobile robots. So, very briefly, what are autonomous mobile robots? Well, there are robots, and this means they sense their environment in some way. And then they run an algorithm to decide what to do. They are mobile, so they move in some space, and the default is the Euclidean plane. And they are autonomous, so they don't have any central authority that tells them what to do. And they are very simplistic. So now this is a long list. Sorry, there's a delay. There's a long list of properties, but essentially it just means they're very simple. So they operate in something called look, compute, move cycles, which will be explained on the next slide. They are oblivious, so no memory. They are silent, so no communication between them. They're anonymous. They all look the same internally and externally. They all run the same algorithm. They are all uniform, so for all n's, all robot numbers, they do the same thing. They are punctiform, so just points in the Euclidean plane. Transparent, so there are no visual obstructions when they look around, and they're crash resilient, so they can cross paths without any problems. Okay, what is a look, compute, move cycle? When a robot is activated, and I will talk about this later, they first observe all the robot positions, and then this happens relative to some local map, which I also explain on the next slide. Then they compute where they would like to move to deterministically, and they choose the trajectory they move on. And after they have moved to the target, they forget everything because they're oblivious. And there's something that makes things more complicated. They are often assumed to be non-rigid, which means that maybe the target is not reached. Okay, what are the local maps of the robots? The only guarantee that we have for all the robots is that the maps are Cartesian. So we have orthogonal axes, and the unit for both axes is the same, which means that we can recognize angles and relative distances. They are invariant. But all of the following may change: the unit length, or the orientation, rotation of the axis, or chirality, and the origin. All of those things may change between robots, and may even change between different cycles, between different look operations. Sometimes we have something called consistency, which means it doesn't really change, or self-consistency, which means at least for one robot it doesn't change. Okay, and non-rigid movement means that an adversary can stop the movement at any point as long as some minimum movement has happened, because otherwise, of course, adversary could just stop everything immediately. But the delta is unknown. And there is a scheduler which activates the robots, initiating those LCMs, look, compute, move cycles. And the two fundamental schedulers are fully synchronous, where all robots are activated at the same time, and round robin, where they're activated in the same order forever. And the fundamental task that we want to solve is gathering, so all robots need to meet in a single location. Which one is not important, and converging is not enough. They really need to be in the same spot. Distinct gathering means that we have the guarantee that when the robots start out, they have distinct locations. And if we don't have this promise, then we call it self-stabilizing gathering. Then, yeah, you might have collocation in the initial configuration. And what are results? In the case of rendezvous, as it is called, for n equal 2, it's very easy to gather. If we have round robin, we just target the opposite location that we see, and we will immediately gather. And for f-sync, we target the midpoint. We will gather immediately if everything is rigid, but we can assume that everything is rigid because they will get closer and closer, and at some point they will be as close, well, so close that the minimum movement distance covers everything. And yes, for n equal 2, self-stabilizing and distinct is the same. All right, and for n at least 3, it is easy for fully synchronous because we can just target the center of gravity. I will just keep it at that. That is an easy algorithm. But it's impossible for round robin. And why is it impossible? To meet at one location, they first must reduce everything to 2 locations. And once they have 2 locations, we can just assign what we have shown here. So we have 2 locations with rotated maps by 180 degrees. And one robot moves over here because it has to move to an opposite location eventually together. But now we can just activate the robots in a way such that always an accompanied robot is activated, and then they never meet. Okay, so it's possible for fully synchronous, impossible for round robin under self-stabilizing, but what happens for distinct gathering? This was the open problem. And for distinct gathering under round robin, it's possible for 2. That's trivial, but this figure has been open for a long time, and it was thought to be impossible for all the time, but actually it is indeed possible for n equal 3, but then possible there for more than 3 robots, which is quite surprising. Why is this surprising? Because gathering more robots seems to be harder in general, and in particular when we have an algorithm for 4 or more robots, that it must work for any activation order, and at some point we must have 3 points because we need to eventually gather, and the robots move one by one. So we have to go to 3 locations at some point. And then it seems like we could apply the impossibility proof for 3 robots, but actually it is possible. Why is it possible? Essentially because more robots can help. We can encode more information in the geometric shape, and the robots can in some sense learn something about the activation order they're in while they have more than 3 locations, and then transition to 3-point locations under very specific circumstances. Yeah. Okay, I need to take care of the time. So I guess I'll skip this. Just show the impossibility proof here. It's also almost the same as before. We go to a 2-point location at some point, and then the robots just exchange positions forever. And now it's a bit more complicated because also this robot might move to a 3rd location, but then we know that this robot here will move also to a 3rd location, and we will be back to a 3-point location. So we go from 2-point to 3-point again, and this is impossible if we eventually want to gather. Okay, sorry, I have to really be aware of the time here. And very short, why is it possible for 4 robots, or what's the basic idea? There's a somewhat complicated algorithm with 9 phases. The first 3 phases guarantee that we get one unique triangle that looks like this. So it has a right angle and it's isosceles. And then the idea is that this robot at the vertex moves down to the baseline, to the midpoint. And once it's at the midpoint, then the outer robots can move to the center. And the crucial invariant that we have so that this works is that when this robot moves to this midpoint here, this robot will move last. So I have written it here. If we have this midpoint configuration, we know that all the outer robots will be activated before this one is activated again. And then we get a gathering very easily in the case of rigid movement. And last point, why is it rigid movement eventually without loss of generality? if we have failure and of rigidity and some robot is stopped prematurely, then we get into this phase 7 or 8, and we get some asymmetric configuration. And in this case, we go back to some previous phases by just, again, finding a right isosceles triangle. But in this time, the isosceles triangle is smaller, and so each time the diameter is halved or decreased by at least this minimum movement distance, delta, and so eventually everything will be rigid. So that's the main idea of the algorithm. And one open problem that is remaining, in this case n = 3, which is very interesting, is whether actually some consistency or even just self-consistency for the unit might be sufficient to solve the problem. And this is not proved yet, and my conjecture is that the answer is yes. And it seems to be quite complicated. And also this seems to have been the major reason why this problem remained open for a long time, because the implicit assumption was that self-consistency cannot really help for collaboration. So if one robot just is consistent with itself, this doesn't really help. But apparently it seems that actually it's true. So maybe if you're just self-consistent, even if we disagree, it's still, we can collaborate. Okay. All right, this was it.
Great, thank you. Since this one went a little bit over time, maybe we'll take the questions in the coffee break, and the next speaker could come up.
Yes.
Remember to stop sharing as well. So next we have another brief announcement on circle formation. This is by Katerina Filetti, Debasish Patanayak, and Gokarna Sharma, and Katerina will give the talk.
Okay. Okay, hello everyone. I'm Caterina Filetti from the University of Milan. This is the joint work with Debasish Patanayak, Gokarna Sharma, and we propose an optimal algorithm for the uniform circle formation problem for a particular model of robots. So let's introduce our model. As before, they are punctual, they can move on the Euclidean plane, homogeneous, autonomous, identical, anonymous, they act through the look, compute, move cycles. They don't know how many they are disoriented, asynchronous, collision intolerant, and opaque. So in case of a collinearity, they obstruct the visibility of each other. So R times for robots. We assume that they are luminous, so they have a constant size light, which can be used both as the communication means, but also as a persistent storage. Okay, so we have a swarm of n robots in distant positions, and we want to form a regular polygon. This is our problem. And for the synchronous setting, there exists constant time and constant color algorithm. In the asynchronous setting, there exist two algorithms, one optimal in color, in time, but asymptotic to root n in colors, and the next one optimal in color, but log n time complexity. Right now, we propose optimal algorithm both in time and in color. Moreover, we minimize the computational SIC. What is it? It is the smallest circle touched by the swarm during the evolution of the algorithm. Okay, as usual in the literature, we split this problem into three phases. First, our swarm form a convex hull, then they form a circle formation. After that, they uniformly distribute on such a circle. And we focus on the last step right now. Okay, we cite one of the main techniques used in this algorithm, which is called the beacon-directed curve positioning, which allows a group of the black robots, okay, which are opaque and asynchronous, to reach a curve given a proper number of right and left beacons, the green and the orange beacons, in constant time. Okay, let's start from our circle where robots are in such a pattern, and we split the circle into k uniform sectors, such that they have the same length, they have the same number of robots, and they are oriented. So right now, the orientation is given by the blue and the green robots. Okay, and right now, within each sector, the robots will run independently each other. Okay, so we have the black robots, and they have to reach the uniform positions, which are the pink stars. So we elect one robot, and it moves to the median point of the block, and all the other robots are moved to the chord of this block, without colliding, of course. After then, they travel along these trajectories, using the median robot as the lighthouse, and they stop to this small circle inside the block. Okay. And after then, all the robots on the east side of the small circle migrate, okay, to the west side of the small circle. Using alternating colors, they split into two teams. And the yellow team migrate to the east side of the small circle, forming a mirror symmetric pattern in this way. Okay, right now, using the green robot as a reference robot for the others, the blue robots on the west side encode their rank using a mutual distance with the reference robot in order to encode their rank. Okay, and this rank encoding allows both the yellow robots to reach their uniform positions, okay, as well as for the blue robots on the west side. Okay, we have our uniform arc, and so it is repeated along each section, and so we have reached our regular polygon. And so further works may consider non-rigid robots or robots without lights or minimize the number of colors. Now I can breathe. Thank you very much.
Thank you. Maybe time for one quick question? Or we can just take it to the coffee break as well. Right, thanks again to all the speakers.
already be familiar with most of the words in the title, but maybe not so much with programmable matter. So I'll start there. And by the term programmable matter, we refer to a very large set of very small and limited computational entities that need to work together. And those computational entities, we assume that have constant memory and work in a geometric environment. And they can also change their physical properties in a programmable way. And the goal with this type of systems is to eventually be able to create large and complicated structures out of those small building blocks. So, for example, we would like eventually to be able to construct cars like the one in the picture. But today I'm going to speak about something much simpler. And what you need to know about programmable matter for our results today is that I will be calling the computational entities particles. They will have constant memory, and the geometric environment that they're going to operate in is a regular triangular grid. And the specific problem that we study is self-stabilizing leader election. And in general, in leader election, we have a well-initialized system where all the particles are initially in the same state. And after executing an algorithm, the goal is to get just one particle that is in a distinct state called the leader. And after that, that particle remains the leader and no other particle joins that state. And in general, it's not necessary that all other particles are in the same state, just that we have the one distinct one. In self-stabilizing leader election, the goal remains the same. We still want to have a leader. But what happens this time is that we don't start from a state where all the particles are in the same state, but instead every particle may be in a different state that is not even a valid state for the algorithm. So the goal this time is to detect that the system as a whole is not in a valid state, return to a valid state, and also elect a leader eventually. And our motivation for studying this problem was that it is important to have fault-tolerant approaches when we talk about very large systems. And there also weren't any self-stabilizing algorithms for programmable matter at all. And it sort of made sense that there weren't any algorithms because in self-stabilizing leader election in general, we can't do much with just constant memory. However, our question was, now that we have geometry, is it possible to get something that works? And the answer to that was immediately yes, we can get something good. So imagine that we have the class of rings in the classical setting and the class of hexagons on the triangular grid. And all the processors in the ring know that they are in a ring, and they know the orientation in the ring, so they can tell which direction is clockwise and which is counterclockwise. And similarly, assume that we have the class of hexagons in the grid, and all the particles agree on all the directions of the grid, and they also have constant memory. And for the rings, it is known that we can't solve self-stabilizing leader election without assuming something additional or having memory. But for the class of hexagons, there are 6 distinct particles, the ones in the corner, so here, here, here. And those particles are also different to each other because of the agreement on directions. So immediately it is easy to see that we can get an algorithm that looks at these directions and decides a leader, and all other particles know that they are not the leaders, regardless of the size of the hexagon. So good for us, but this isn't very interesting because it's just hexagons and with a lot of assumptions. So the question then becomes, can we do something for more general cases? Which properties would be enough? And we see that immediately if we take away the assumptions of agreement on direction, we get something that resembles a lot more the difficult case of the ring in the classical setting. And to give you some intuition about the difficulty of the problem, there were already quite well-known results about the memory that we need to have. So it's been known since 1999 that for silent self-stabilizing leader election, we need at least log n bits of memory. And here silent means that eventually the particles do not change the values in their internal variables. And more recently, there was another result that said even if we don't want the algorithm to be silent, we still cannot solve deterministic synchronous self-stabilizing leader election with less than log n bits of memory. And I told you before that in programmable matter, nothing had been done, which wasn't completely true. There aren't any dedicated papers on self-stabilization. However, there is one paper that comments on self-stabilization, and the authors there managed to give a self-stabilizing algorithm with log-star n bits of memory. However, this still doesn't answer the question of whether we can do something with the actual constant memory that we want programmable matter systems to have. And here we managed to solve that problem. We managed to give the first self-stabilizing leader election algorithm, assuming that the system is simply connected and that the particles are activated in a good fair way, which I will explain in a moment. And we also managed to respect the constraint of having constant memory per particle. And to do that, we come up with 4 rules that can be locally checked by every particle. And those rules have to do with giving an orientation to edges incident to particles. And what they guarantee is that if all rules are satisfied for every particle, then there exists a unique sink in the system. And we define that sink in the system to be the leader. And in addition to that, we give an algorithm about how to get an orientation of all the edges. And some experienced people between you might be thinking that it is already known that if we have a proof labeling scheme, which is basically what the 4 local properties are, then we can always get also a silent self-stabilizing algorithm. However, to use that technique, still log and memory is needed, and we wanted to have something constant. So in fact, the algorithm that we have is not something that we got for free because of the certificate, but something extra. So the particular model that we worked with, in addition to the triangular grid and the constant memory that we have, assumes that the particle system is simply connected. And what this means is that the particles occupy a simply connected set of nodes on the triangular grid, or even more simply, we can assume that there is a boundary between our set of particles, and inside that boundary, every node is occupied by a particle. We further assume that the particles are activated one by one by a sequential scheduler, and in a good or fair way, which means that every configuration with respect to the edges that appears infinite, for every configuration that appears infinitely often, every possible successor of the configuration also appears infinitely often. So very simply, if there is a particle that could be activated and that would be good for our algorithm, it will be activated. And in addition to that, we define that particles have visible port numbers. So here between particles P and Q here are just names for the presentation. The particles don't actually have any names or identifiers. If P knows that it is connected to Q through port 0, P also knows that it is connected to Q, that Q is connected to it through port 5. They don't need to communicate about that, they know. And finally, we assume that particles have chirality, so this means that they have a common sense of rotational orientation. So they agree on which direction is clockwise, which is counterclockwise, but they don't agree on where those directions are on the grid. So here, direction 0 might be this one, and for the other particle, it might be the other one. But the direction clockwise to direction 0 is always going to be direction 1. And here I have those 2 properties, sequential scheduler and chirality in brackets, because I'm going to use them for the purposes of the presentation. But in our paper, we don't actually use them. We give a way to get a detection of chirality in a self-stabilizing way. And in the full version of our paper on arXiv, we also have a sequential, we show how to solve the problem without the extra assumption of a sequential scheduler. Our basis for what we did was the well-known erosion algorithm in programmable matter. And the basic idea for that is that we have a system, and we want every particle is initially a candidate, and the goal is for particles to stop being candidates from the outside, moving towards the inside. And there are 2 simple rules to stop being a candidate. The particles check whether they are on a strictly convex angle, and if they are, they might be able to stop being candidates. In addition to that, they also have to not disconnect their neighbors that are still candidates when they stop being candidates. So in what we do, it's this simple method that we're trying to emulate, basically. So the 4 rules that we have to check whether the system is well-oriented are that we want every edge to be oriented. which every particle can check locally. We want each particle to have at most 3 outgoing edges, and we use this condition to emulate the fact that in erosion, particles have in order to erode, they have to be on strictly convex angles. We say that particles, that outgoing edges of particles have to be consecutive, and we use that so that the outgoing neighborhoods of particles are not disconnected when a particle erodes. And finally, we want particles to not form cycles of size 3, directed cycles of size 3. And this is just to make sure that there will be a unique leader. So briefly again, this is a system where the first rule is broken, so there are some directed edges, but there are particles incident to the orange edges that know that undirected edges exist. This is a system where the second rule is broken, so the orange particle here is incident to 4 outgoing edges, and this is again something very local. Here the third rule is broken, so the orange particle has outgoing edges, but they're not all consecutive around it. And finally, here there is a directed triangle. And this rule is a bit different because in the previous one, the particle could immediately look at their edges and know. But this time it needs to somehow gather information about edges between its neighbors. And in fact, this is why we have the visible port numbers and the chirality. It's just to be able to compute these kinds of triangles. And although we avoid the cycles of size 3, we don't avoid any of the larger cycles. And this is important because in a general setting, detecting triangles is one of the hardest things to do without constant memory, with constant memory. And for us, this is not a problem because what we care the most about is having edges that point towards the inside of the system. So cycles are not a big problem, so we don't avoid them. Okay, so I don't have time to give you proof, but maybe you believe me that if the rules are locally satisfied, we can get a unique sync. The next question is, how do we make sure that the rules will be satisfied? And for this, we have a surprisingly simple algorithm. We were expecting something much more complicated with a lot of cases, but it turns out we can solve the problem with 2 simple rules. So every time a particle is activated, it executes both lines of the algorithm. And the algorithm just says that if the particle has edges that are not oriented, it marks them as outgoing. And if that orientation breaks any rules, it removes all its outgoing edges. And surprisingly, this is enough. And here I have an example of the algorithm. So initially, particles may be incident to no edges that they know break some of the rules. And all of those particles are potentially activable. There is no rule on which particle is going to be selected. And I paint those particles that are incident to a rule that is broken by pink. So let's suppose that one of the pink particles is selected for activation. It becomes activated. It sees that it is incident to undirected edges, this one, and it immediately directs them. And when it directs them, the third rule is broken. The outgoing edges are not consecutive around the particle. So the particle detects it and it removes all its outgoing edges, not just the new ones that it added before, but also the outgoing edge that it had before its activation. And continuing like that, we prove in the paper that we get a unique sync in the system. And again, I don't have time to show you the actual proofs, but it's interesting that everything complicated about our algorithm is hidden in the proof, but the algorithm itself is very simple. So to sum up, we give the first self-stabilizing leader election algorithm for programmable matter. We provide a proof labeling scheme composed of just 4 rules, and we give a simple and silent algorithm to get a unique leader in a self-stabilizing way. And some possibly interesting directions in addition to that would be to consider different schedulers because CUDA fairness is already very strong. So it's interesting to see if we can do something with a less strong scheduler. And another, in my opinion, more interesting problem is to see what can we do if the system is not simply connected, so if it is allowed to contain holes. So this is it. Thank you.
All right, so I think we have time for a few questions. Any questions? I'll start here.
Can you give me some idea why these holes are a problem?
Basically because erosion doesn't immediately work, and it depends on what you also need to assume about the system, because locally everything can look very, very similar. Like in the case of hexagons, it was nice because we had the 6 convex angles, but in general you can have something very complicated with that's very symmetrical, and it's hard to see locally that something unique happens there in order to decide on a leader. And in the non-self-stabilizing algorithms that exist, they also have to exchange information up to some distance. It's not local.
Right. I think there were a few more questions. I see 2 hands, so I'll start here.
Thank you. So you talked about like you want to avoid triangles.
Yes.
And you said like your algorithm is simple and avoids triangle with only like 2 steps. And this like problem is hard in general. So what can you do? What can you say like about that you like from a graph theoretical point of view like?
Not much, but since we say that we know the port numbers and we know the chirality, each particle can compute the edges of its neighbors. So it's not hard. If you assume you know enough things, it's not hard here. In general, yes, but it's a bit engineered.
All right, can the next speaker start setting things up? So I think Robert had a question.
Yeah. Does your algorithm ensures that the leader is at the center, or can it be at the border for some initialization?
It can be on the border as well. It depends on the order in which the particles are activated. The idea is to go inside, but if they're not activated in a good order, then you can get a leader on the boundary.
All right. Any more quick questions? If not, let's thank the speaker again. And we should have Ben somewhere here. And he will talk about the computational power of chemical reaction networks with bounded executions. So please go ahead.
Thank you. So thank you. This is a joint work with Professor David Doty from the University of California, Davis. And in this talk, I would briefly like to give an introduction to chemical reaction networks, or CRNs. Next, I would give our definition of what it means for a CRN to be execution bounded. And next up, I will go into our positive results and then finally go over the limitations section of our paper. So chemical reaction networks are systems where you have a finite set of species. You can call them something like A, B, C, D, or whatever you want. You have a set of reactions where, for example, A and B can react together and they produce one A and one C. And for those familiar with population protocols, it is very similar, since a population protocol is a CRN where it has 2 reactants and 2 products. Just we have a different terminology, and an execution is a sequence where we can apply some reaction to C of I minus 1, and then this gets us to the next one. And the configuration is what we call the counts of molecules, and we typically use a vector to represent this. So if we have all of this, we can compute functions. To do that, we need to interpret counts of molecules as inputs and outputs. In this case, we interpret the counts of X molecules as the input, and then by adding a single reaction where 2 X can react together and produce a Y, this will compute a function that is division by 2. So as long as we have X more than 1, it will be applicable. And once this reaction runs, we end up with 2Y, and then it is stable as the reaction is not applicable anymore. And since we interpret Y as our output, we see that it gives us the correct output value of 2. A more common thing that we compute are predicates, so decision problems. And in this case, we need a different interpretation where we say each molecule can have a vote, and it is either a yes voter or a no voter. And then once the configuration is stable in the end, we will look at all of the molecules and we will want them to have a unanimous vote that says either yes or no. In this case, we compute the predicate, is there at least one B present in the initial configuration? We need a single reaction that says B can react with A to produce two Bs, and A will be no voter, B will be a yes voter, meaning if we have only A's present initially, then the reaction is not applicable and it is stable and says no. But if there's at least one B, then this B will spread like an epidemic, and finally we end up with only B's, so voting yes to our final answer. In general, we know that these CRNs can compute semi-linear predicates. Now, what does it mean for a predicate to be semi-linear? One characterization of this is that they are Boolean combinations of threshold and mod predicates. And these in turn are, we take a weighted sum of the input, where each species has some constant weight, and then about that sum we can ask a question such as, is that sum greater than some threshold? Is that congruent to some constant C, mod n? And in total we can decide something like majority or parity, but what we couldn't decide would be some quadratic function or whether A is prime. So to give a more realistic example of predicate computation, we take that parity example and show how we would typically compute that. The way we do it is we have an input species, and now we have a subscript that will tell us the parity of what we have already gathered. So we say that the input species is A, O meaning odd, and then we need to add reactions where two odds can react together and make two evens. And you might also notice that we have upper script and lower script characters here, and the reason being that we of course need to keep track of whose information we have already stored. So that results in some sort of a leader election where we start out with only uppercase and then we end up with lowercase ones. So here's a small example, these reacting together, and finally the last leader will say it is even. And since we required a unanimous output vote, we can also have reactions that will let the leader go around and persuade the followers of its decision. But as you might notice in the last two reactions, if we had two leaders present of different votes, they could hypothetically persuade some follower back and forth. An adversary could create an execution sequence that would go on forever, meaning that this is not execution bounded. Bringing us to our definition. In general, a CRN is execution bounded from a configuration X if all executions starting at X are finite. Why would we care about this? The first reason is that they are slightly easier to reason about, since at every step we make some progress towards our final stable output. And second of all, in a real-life implementation, in a wet lab implementation, we might use some fuel. And since we know how many reactions can happen, we also would know how much fuel we need. Now, the question, of course, is what can we do with these, or do we still have the same computational power if we have this requirement? Now, how would we check for this, or how do we check for this in the paper? Is recall that we characterize semi-linear as a Boolean combination of threshold and mod. So we check three conditions. Can we decide the mod predicates? Can we decide the threshold predicates? And can we decide any combination of the both? So I would give for each of these cases an example. The first example is mod predicates. We are asking, is 2a plus 3b congruent to 4 mod 5? In this case, we have inputs A and B, and crucially, we need to also add another molecule in the initial configuration, which is called L0. So it is leader driven in this way. And the subscript here actually stores the sum under a mod. So what we can do is that the leader consumes the input molecules and the constant weights will get added to the subscript. So here, if we had only one of each input, the leader could react with A and produce one L2, since 2 gets added to the subscript, and it could also react with B, and then we add 3 to the subscript, bringing us to L0. And to check the last condition, whether it's congruent to 4, we just say L4 is our yes voter, and everyone else votes no. Again, it's unanimous because we end up with only one molecule. For threshold, we have a similar leader-driven system where we now have the example with 3 different input species. Is 2x1 plus 3x2 minus 5x3, is that smaller or equal to 4? We again need to start with one leader. This time the leader will just have a subscript indicating yes or no vote. And we also need to start with 4 n molecules. N here represents some sort of negative unit, which is allowed since it's a constant. And first we convert the inputs to positive or negative units, which we define reactions for. The x can split up into 2p, the x2 can split up into 3p, and x3 can split up into 5n. And then we add 2 reactions where the leader can consume a p and create a leader with a different subscript, ln, which can then in turn only consume an n. So what will happen is that we consume the p and n in an alternating fashion, which means if we go on with this, they will eventually cancel out, and we can read the final result of the state of the leader. In this case, it's a yes vote. Now, how can we combine these? We essentially know already that we have a combination of mod and threshold predicates, so we split up that computation. We split up the input molecule X, and then we let 2 CRNs run in separate, and we define some sort of global voter as a layer on top. In this case, it's called V with 2 subscripts, which represent the answer of one of the downstream CRNs. And we can then see that if we have our reactions that let the answers of the downstream CRNs override the respecting subscript, then what we notice is that even though we can persuade the global voter yes to yes or no and back, it is still execution bounded, because what is important here is that the count of the voting leaders of each of the downstream CRNs is always equal to 1. So we know that both of these are already execution bounded. There's only ever one at a time. So the global voter can also only switch back and forth a finite amount of times. So let's recap. It turns out we can actually still compute all of the semi-linear predicates. However, this hinges on some assumptions. Specifically, not all species are required to vote. In the combination, we can start with an initial leader, and the CRNs can be collapsing. Collapsing here means we can start from a big number of inputs and end up with potentially only 1, or generally O of 1 output size. And now we can, of course, ask what happens if this is not allowed, bringing us to the limitations section. So to introduce the limitations, we first need to establish some tools, first of which is self-covering execution. A self-covering execution is one where we start off with some state X. We have reactions that can lead us to Y, and then when we look at the molecular counts, we see that Y has at least as many of every species as X. And since we know that these systems are additive, we could design some execution sequence where we start off in this case with 2 red molecules. We apply some reactions, we get the 2 original red ones plus an extra gray one, and since we can still apply all of the same reactions to the original two red ones, we can make that go on forever and have an infinite path. Second up are linear potential functions. A linear potential function you can think of sort of as the mass in a system. So this function maps a configuration to a number. And the way we compute this is we find constants for each of the species, and then we take the weighted sum of a configuration. And what we additionally require of these constants is that each reaction in our system, they would decrease this number. So why does this help us? It turns out that CRN has a linear potential function if and only if it is execution bounded. And this helps us because whereas before we had execution boundedness as a global and hard to decide condition, it is now a much more local checkable condition because it comes down to simply solving a system of equations to find the coefficients that meet the requirements. Next, we have the non-collapsing criterion. As stated, it just means that as our input grows, we require the output to also grow in some way. So we wouldn't allow something like the parity example here, where we can start up with any number in the input and then just produce a single output molecule. And lastly, the eventually constant predicates are those where if we go sufficiently far from the boundary of the positive orthant, the output never changes. In this case, the question is x greater than 3,3? And if we go far away from this boundary, the answer is always yes. Of course, many interesting predicates do not meet this requirement. So bringing us to our main limitation theorem, which is stating that a CRN stably computing phi that is meeting these requirements, specifically it is non-collapsing, it is execution bounded, and it is leaderless, can only compute phi if it is eventually constant. A smaller proof or a smaller example for the non-general proof, where the general proof is in the paper, but we can already show that it could not compute parity by showing that we know in parity, once we add only one more input, the whole output needs to change. So let's say we start with only one input, then of course the answer is the input is odd. So we get some configuration with that vote. If we add a single more input, then the whole output has to change and we have to say, no, now it is even. So we can design this sequence of configurations where at each step, our output size grows due to the non-collapsing requirement, but the amount of energy that we put into the system, as measured by the linear potential function, stays constant. So we know adding a single A needs to change the whole output, adding another A needs to change it again, and we can see that as we go on with this, eventually the amount of energy required to do these reactions will surpass the amount that we put in with an additional A. Wrapping up, what you should know from this talk is that we can characterize an execution-bounded CRN by a linear potential function. Execution-bounded CRNs still can compute all of the semi-linear predicates in O n log n time with a leader, but if we remove that leader, they can only compute eventually constant predicates. Thank you.
All right. Thank you. Questions? We have some time for questions. All right. So what happens if I say I'm interested in bounded execution, but let's say almost all executions can be bounded, but just like epsilon fraction of, or like a small probability I can still fail. Does everything, the whole theory change?
So there is a small probability that is not execution bounded.
Yeah.
Then, so I guess typically when like previous constructions, they already asymptotically reached a result. And we can see that if that's the case, such as in a paper, I think, of 2004 of Angwin, the computation is much faster. So it's polylog of n time, but execution bounded by definition, we want to rule out all of the possibility that the computation will keep on going. So yes, that is our definition. And an open question would be, if we leave that possibility, then will it be faster? So in other words, is there a lower bound on the speed that we can do with execution boundedness?
All right. Any questions now? All right. If not, then let's thank the speaker again.
Thanks.
And next we have a brief announcement, I believe. Yes, so we switch to population protocols. So the expressive power of uniform population protocols with logarithmic space, and the talk is given by Vincent. So go ahead.
Yeah. Good afternoon. My name is Vincent. I'll be presenting on the expressive power of uniform population protocols with logarithmic space. This is joint work with Philipp Czerner and Roland Guttenberg. I should be sharing.
What happened?
It worked when I checked it before.
Let's try again.
Now? Yes. Okay, let's try this again. Yeah, I'm presenting on the expressive power of uniform population protocols with logarithmic space. And this is co-authored by Philipp and Roland Guttenberg, who is not here. So, population protocols are a model of distributed computation, very similar to the CRNs you just saw. We have a finite number of agents with finite states that try to collectively decide some property of the initial distribution of states, such as, are there more red agents than blue agents? To do this, they repeatedly randomly interact with each other, and during each interaction, both of the involved agents can change their state according to a global transition function. We do a computation by consensus, meaning that eventually all of the agents need to agree on what the outcome is and also not be able to change their state again. The expressive power of this model was studied by Angloin et al. In a 2004 paper, which is the same paper that also introduced population protocols. And they showed that they can decide precisely those predicates which can be defined in Pressburger arithmetic, the first order theory of addition. This is also the same as semilinear that was mentioned in the previous talk. And yeah, examples of such predicates are threshold predicates, are there at least k agents, and divisibility by a natural number. While the model as originally proposed assumed a finite state space, more recent work on the subject has been using a more relaxed model where we can have a possibly infinite state space, but we assume that the number of states reachable with n agents from an initial configuration is bounded by some function f of n. As an example, I'll give the binary counting construction, which can be used as part of a larger protocol. Here, the state space consists of the powers of 2 and 0. The initial state is 1, and we have a single transition rule, namely if two agents with the same counter meet, then one of them gets the sum, so the next higher power of 2, and the other agent gets counter 0. And as this preserves the total sum of all counters, it's clear that the number of states that is reachable with n agents is bounded. There's a special interest in population protocols that use a sublinear amount of space, because some of the proposed applications would have a very, very large number of agents and make even linear growth infeasible. And so all of these papers you see here describe different protocols with sublinear state growth. And the expressive power of this more relaxed model has also been studied by Hatzigiannakis et al. In 2011. Specifically, they studied the case of less than log n states, where they showed that if the bound is less than log n, then actually the number of reachable states is already bounded by a constant. And so those can also only decide Pressburger arithmetic. But if we allow at least linear growth, then we can start simulating Turing machines, which leads to the expressive power of a symmetric n space of n times log f of n. Symmetric just meaning that the language is closed under permutation, since we cannot differentiate between the order of the agents. They are just represented as a set. But as you can see, they left open this very large gap between logarithmic and linear state growth, and that has remained open until the beginning of this year, which is a bit surprising considering that a lot of research has gone into finding protocols that fall within this sublinear space. And so our contribution to the topic has been closing that gap by showing that we can construct a protocol that simulates a Turing machine with a slightly lower space bound of f of n times log n. We do this by simulating a counter machine with the equivalent space bound. We also showed that it is an upper bound, so there's no room for improvement anymore. And while I would like to tell you all how we do the simulation, I unfortunately don't have the time to do that, but you're welcome to ask me during the lunch break. Thank you for your attention.
Right. Any questions?
Yeah, so as I mentioned, if you have a protocol where the number of reachable states is bounded by a function in little o of log n, then it is actually already bound by a constant. So the reality is there are no protocols in this region, or no uniform protocols, I should say. There are further relaxations to the model you could make where you could find protocols in that region, and we propose that we can further improve on the expressive model in that case, but we are still working on it.
All right, thank you. And is the next speaker around? So the next talk will be about, I believe, ants. Single bridge formation in self-organizing particle systems. And let's see if we get the slides. So Dana will give the talk. Right.
Okay, hi everyone. This is a work between Georgia Tech. Shunhao Oh is my grad student. He did the lion's share of this work. And Jacob Calvert, Noah Egan, and at Arizona State, Joseph Brion and Andrea Risha. So we're interested in programmable matter is our main interest right now, where we want to know what distributed computation is possible to get, taking local computation and getting some global outcome that's useful for the set of robots, the set of ants, and or any kind of collective. So we're going to take inspiration from nature. And, we know that many of these complex behaviors happen a lot in nature. The one that we're going to look at today is bridging. So the setup, and these are experiments being done at the University of Georgia by Zengin Sasaki. I think I'm missing an S. So what they did is they took a large dish, and there's water and food in the middle, and there are ants on the outside that are eager to get to the food, but the ants can't swim. So they start moving in towards the water. You know, you've seen ant rafting and things like that. But eventually, if they're lucky, a bridge forms. And once the bridge is there, other ants climb over them and can reach the food and bring it back to the nest. So in particular, they're interested in why many experiments, they went through many experiments, and there's always a single bridge that's formed. So how do the bridges form, and why is there at most one? So we came about this thinking we could probably explain this with trying to understand a distributed algorithm that has much less capability than the ants and still can form these bridges. And the explanation for why one bridge forms seems to come from statistical physics, where particles self-organize and form these very minimal contours. And so we want to apply all of this kind of thinking to try to understand the ant problem. So in terms of trying to understand how the bridges form, we're going to just make two basic assumptions and see if they're enough. The first is that ants prefer to be next to as many other ants as possible. This gives them stability. So I don't really know what their reason is, but certainly clumping together seems like a good idea. So an ant that has 4 neighbors is happier than an ant with 2 neighbors. And being closer to the food seems useful to the ants. So we're going to assume in this model that almost everything is local, except for the scent gradient. So there's some scent from far away that the ants are sensing, and as they get closer, it gets stronger. Okay, so we're going to just make some basic assumptions that they can recognize the direction the food is coming from. So the first thing, saying that you want to be close to other ants, is similar to work that we did previously, showing that you can get a group to compress to form a low perimeter boundary region. And that's what's telling us that this idea of preferring more ants might be useful, but now we're adding the scent gradient. Okay, so, they've done a lot of experiments at the University of Georgia. Our colleagues in physics have done agent-based simulations, trying to understand what usually local rules can get these bridges to form, and they're trying to match. And so we're not doing that. What we want to understand is really to have a clean theoretical model that replicates this behavior. So rather than being on this dish with the ants on the outside and the food on the inside, we're moving to the triangular lattice with periodic boundary conditions in the horizontal direction, food on the top and ants on the bottom, and they're going to start growing. Okay, so ants enter and they start forming some region, maybe some go away, and then over time you get this larger region. And we're going to assume that ants fully occupy the bottom layer. I didn't draw it there. And that subject to the fact that, except for the fact that it's on the cylinder, the set of ants is going to stay simply connected. Okay, so we heard all the reasons that you might want simply connected in Maria's talk, the first talk of this session. In this case, what they find experimentally is sort of doesn't really fit the model we were hoping for, which is that ants actually start climbing on each other. You might even have many layers of ants. So this complicates the behavior and the analysis. But what we're going to do is we're going to introduce what we call a bridging occupancy chain, which is there might be many layers of ants, but we just want to understand how this projection, the simply connected projection, changes over time. So I'm just going to be looking at this red boundary, which is the contour of sites that are occupied by at least one ant, and I want to see what happens over time. Okay, so we're going to represent the set of ants just by this single contour. We lose a lot of information. And this would be a configuration where the ants were reaching the food. And here you could see the outline. And I'll go back. What I'm showing here is that if a new ant goes into that particular spot, then the contour changes. All right, so we're going to be looking at these changes to the contour. And here's another example where I'm going to take one away where an ant leaves. So two things. The occupancy chain is not local, even though the ant movements are, or the particle movements or agents, whatever you want to call them. So we're looking at how this profile is changing, and we're just speeding things up in between times that an ant might take to get there. So we're just looking at that projection. It's no longer local, but it's coming from a distributed local algorithm. And second, you might ask, how do we keep it simply connected? And I'm just going to refer you to the compression paper, which says you can use constant memory and local rules and keep this configuration simply connected just by rejecting any ambiguous moves. So any move that locally could, in fact, disconnect, we're going to ignore that. And you still have connectivity of the state space. So recall that we're driving this with two preferences. Ants prefer to have more neighbors, and they prefer to be closer to the food. Okay? So we're encoding the ants' happiness, their preference, by two parameters, lambda and gamma. Lambda is going to be raised to the boundary length of that contour. So we said that ants prefer to have more neighbors that are ants. That is negatively correlated with the length of the contour. There's a linear relationship between the number of ant-ant edges and the number of ant-no-ant edges, which is the boundary, the length of the boundary. So B sigma V is the length of the contour in the occupancy chain, and S of V is going to be related to the scent. So in particular, we're going to think about the different levels and say that the strongest scent is at the top. And so we're going to parameterize the effect of the scent on some particular row according to its level. And now we're taking the product over all of the ants. Okay? So the probability of a configuration is the total happiness over all of the ants or particles of their particular happiness, and their happiness is parameterized by the length of the number of neighbors they have and the scent. Okay, and so this is really hard to see.
All right, so I think the projector died because the screens are still working.
So I'm just going to continue if you can all see this or this. Oh, that's facing the wrong way.
We can wait a couple of minutes.
Sure. This is electricity bridging.
Yeah, around the same time.
Okay, great. Thank you.
All right.
Okay, so if you're in discrete math or computer science, the top row is probably more familiar to you, which is just saying that where the total weight of a configuration is the product over the individual particle's happiness. If you're a physicist, the bottom two lines are much more natural, which is there's a Hamiltonian, which is capturing the energy of the system, and it's the exponent. So it's, if you look at the bottom equation, the probability of a configuration is e to the minus beta times this Hamiltonian, which is the energy. Beta is inverse temperature, typically, and H of sigma is this line in the middle, which is a sum over the effect of the scent and the effect of the boundary. So it's just a parallel way of thinking about it. These are completely equivalent. And in fact, in this case, it's very awkward putting it into the statistical physics notation, but it's useful to think of it that way. So now, going back to the original formulation, we have that the probability of a configuration is related to the product over all of the particles. There's a really natural Markov chain. So I showed you pictures where the occupancy chain changes a little bit. Either a new particle got added or a particle got removed, right? So locally, to figure out the probability of accepting that move, this is a completely local calculation. So a particle can figure out how many neighbors it has, and it, from the scent, can determine how strong the scent is. However, it's also changing the contribution from all of its neighbors. So each of its neighbors now has one more neighbor if we add that particle, or one less if we take it away. But again, this could be updated through local information. And so we're able to apply a Metropolis filter that says to add a particle or remove a particle, we look at the ratio between the new configuration and the old configuration and take the minimum of that and 1. This is local, and you could calculate this with constant memory. Okay, so this is the chain that we want to analyze. That, it took us a long time to get there. And here are the main results that we have, finally, is that for sufficiently low temperatures, that's large beta, beta's inverse temperature, we will never get multiple bridges. That was really what we set out to understand, if you remember. And the second is that we could somewhat characterize whether a single bridge forms or not. So the only option is at most one bridge. And our main result is showing that with very simple techniques, we could show that you really will never get 2 bridges, which is what we set out to understand. Why isn't this it? Oh, whoops. Okay. So I say that there's no multiple bridges. What do I even mean by multiple bridges? So here are 3 ant configurations. It's really not obvious what I even mean by multiple bridges reaching the food. So I think the first one you'd agree, yes. I think the second one, you have 2 different components reaching, but there's just a couple of things missing. So probably you would agree, no. For this third one, maybe, it's not clear. So this is how we define multiple bridges. Is we define them parameterized by 2, an A and a B, which are between 0 and 1. And we say that there are multiple AB bridges if you go from the 8th way up to the Bth way up, back down to the 8th way up, back up to the Bth way up, and then down again. Okay? So if you go twice between the A and the B levels, then we're going to say there are multiple bridges. And I do want to point out that you could have something starting on the right and then swooping around that actually crosses the 2 red lines that really is just a single component kind of swirling around. So to really formalize it, we want to truncate at the AH level and say, are there 2 different components that exceed the B level? And that seems to be the right definition. Okay, so this is the formalization. So here I have something which looks like 2 bridges are forming, but I would only say 1 bridge because the second thing doesn't reach the BH level, all right? And so our theorem says that for any constant epsilon, there is some very large beta, so some low temperature that depends on epsilon, so that anything drawn from the stationary distribution will never have an AB bridge if B minus A is equal to epsilon. Okay, so for any constant gap, I can find a large enough temperature precluding any kind of bridge that goes between these 2 levels. So we get things that are increasingly monotonic, going up and down, and we don't have these deep retreats, and that precludes getting the bridges. So this to us really gives the insight into what's going on with the ants. While ants definitely possess higher intelligence than I'm giving them credit for, they could be really dumb particles, just interacting perfectly locally, and still they're going to have this behavior where they find, in some sense, this minimal length contour. That's going to happen automatically. And that really isn't in the biological way of thinking. And looking at it through these randomized distributed algorithms seems to give that insight. Our second result is a little more subtle, and it says that under simple assumptions, which I'll state in a second, about the scent intensity function, we can show that there's a phase change, that when the ratio between the scent and the boundary effects, the preference for more neighbors, when that's large, we get a bridge. When it's small, we won't get a bridge, provably. Okay, and the assumptions are a little weird. It says that the scent has an increasing gradient towards the food, so the strength at which you're increasing gets stronger as you get closer to the food. You are much more aware of it. And the one that's weird is saying that the sum of the effects of the scent in any column on the lattice is a constant. So that second one is weird, and the reason it's there is that if it weren't true, then this problem becomes trivial. So if the sum of the effects of the scent is greater than a constant in a column, you will always reach the food. If it's little o of constant, you will never reach the food. And it's only when it's constant that you see this phase change as you change this, this ratio of parameters. So we fully understand when you're going to get a bridge and when you're not, and you'll never get two bridges, you know, for very large systems and very low temperature. Okay, so just two short slides about the main techniques. These are techniques that are used all the time in statistical physics in order to show that you have phase changes. We've used them a lot in computer science to understand convergence rates of Markov chains jumping from polynomial time to exponential time. And the main idea here is called a Piles argument. So we want to preclude some probability, some events from stationarity by showing that they have exponentially small probability. So in this case, I'm going to show that having two bridges or more is exponentially unlikely. I'm going to do that by taking the set of things with two bridges and mapping them into much more favorable configurations that have at most one bridge. Okay, and we show that there aren't too many inverse images, and then from a count, you could show that the increase in energy exceeds the entropy of the number of configurations. So this is fairly standard. And second, in this case, we use layer sequences. So rather than, so this is motivated by typical statistical physics, it gets much harder because the effects depend on how close you are to the food. And so what Schoenhow figured out is that if you just count the number of particles in each row and take the most favorable way that those could be aligned, you can push through the proofs. So I'm just going to end now with just a couple of open problems. We look at the occupancy chain to simplify the projection of what is changing over time with these ants. Could we go back and analyze the original ant model directly, maybe by having, some number of levels, layers of ants. So that would be nice. Does ant rafting speed up bridge construction? You see these ants actually not being simply connected, but shooting rafts off to speed things up. Is that favorable? Similar results on a disk, pointing out the pun here. But, originally the biological example was on a dish, and we moved this to a cylinder to make the food and the ants have the same size. It actually, the combinatorics gets complicated on the disk, which is why we didn't do it. The convergence rates of these algorithms, we don't know. And we believe that this idea of reducing problems to their occupancy chains, these projections, will be useful for other problems. So, thank you.
Right, time for one quick question. Okay.
When you define things like real-time probability, what do you actually mean? Because this is a system that runs up to infinity, and during this infinite
time, you will observe also very low probability events. So is it more like you run it for a very long time and take a snapshot and see if there is a bridge or not? Or
Exactly.
Okay.
Exactly. So yeah, you could temporarily form these multiple bridges, but we're saying that the chance is exponentially unlikely at stationarity for any finite size system.
Right. Okay. Okay. Thanks.
Thanks.
All right, let's thank the speaker again. And Philip. All right, so the next talk will be again about population protocols and breaking through the linear space barrier. So please go ahead.
Right, thank you. So hi, I'm Philip. Very excited to be here and to tell you something about space complexity of population protocols. So what are we talking about? Population protocols. That's a model where you have a large population of agents. Those are the participants of the computation. They are computationally very limited, so that we model them as finite state machines. They have no identities, they have no memory, they can't really do anything except from being in a state. The computation proceeds via random interactions. So we pick two agents at random, and those agents move to new states. And then we repeat that how long as we want. The goal of the computation is to decide whether the initial configuration satisfies a given property. We do that by consensus. So at every point throughout the computation, each agent has an opinion of the output, and that opinion can change any number of times throughout the computation. But we require that eventually all agents have the same opinion, so we have a consensus, and it must not be possible anymore for any agent to change their opinion after that, so it's stable. All right, so formally we have some finite set of states, we have a pairwise transition function, we have a set of initial states, and we have a set of accepting states. It is known, as also Vincent mentioned, that population protocols decide exactly the semi-linear or Pressburger predicates. Not really important what exactly those are for this talk. I'm just going to talk about threshold predicates. So what do we have here? Here we have some constant k, and the goal is to decide whether the one input x exceeds k. So since we have only one input, all agents are in exactly that input. And since the total number of agents doesn't change throughout the computation, this is just the same as asking, do we have at least k agents? Okay, so the goal which we are trying to decide is, do we have at least k agents for some constant k? Okay, let's look at an example for how we might do that. So again, we want to decide whether x is at least k. The general idea will be that every agent holds some number of tokens. So the set of states will be just the numbers from 0 to k, indicating how many tokens that agent has. At the beginning of the computation, all agents should have exactly one token, so the initial state is going to be 1. Then, when two agents meet in an interaction, one of them takes all of the tokens that the two have, and the other one, well, has no tokens anymore. So if one agent has I tokens, the other agent has J tokens, then after the interaction, one agent will have I plus J tokens, and the other one will have 0 tokens. Okay, we do that if the number of tokens those two agents have does not exceed k. So if they're less than k, to be precise. Otherwise, both agents will end up with k tokens. Okay, so same interaction, then both just go away with k. Okay, and the one accepting state will be the one with k tokens. So how does this work? Well, if you have fewer than k agents, then you will also initially have fewer than k tokens in the computation, and then you're just executing the first transition. And that transition keeps the number of tokens constant. It doesn't change the total number of tokens. So you will always have fewer than k tokens. At the end, one agent will have all of the tokens, less than k still, so no one will be accepting, and we're done. We are have a stably rejecting consensus. Conversely, if you have at least k tokens, then eventually two agents will meet, and they will together have at least k tokens, and then the second transition will execute, and then you have an agent in state k, and that will spread then throughout the computation, right? Once you have an agent in state k, whenever that agent meets another agent, they will have more than k tokens together, or at least k. So that's what we call an epidemic. Everyone should be familiar with those by now. Very quickly, all agents will be accepting. Okay, so that's a nice protocol. It works. And it has k plus 1 states. Okay, is that a good number of states? Well, let's look at the kinds of applications we're interested in particular in the area of natural computing. So chemical reactions, where we also just saw a nice talk. The agents correspond to individual molecules that participate in the computation. So roughly the number of agents that you would have is something like 10 to the 23. Right? That's a good number of atoms. However, the number of states, so the number of different kinds of molecules that participate in such a computation, would be much lower. You can't have 10 to the 23 different molecules, which, right, you still have to synthesize them somehow so that they execute your protocol. That's completely infeasible. So actually, this is too many states. We would like to find protocols with fewer states than that. Okay, and that brings us to state complexity of population protocols. So the general question we are considering is, I give you a predicate, and I ask you, what's the smallest protocol you can design for that predicate? So what's the smallest number of states you need to decide this predicate phi? Okay, let me make a brief remark here. So there's a different model of population protocols, 2 talks ago, where you have the set of states, and it's allowed to change with the number of agents. So then the state space is no longer just a fixed, constant thing, but it depends on the number of agents you have. And there's been also lots of research into time-space trade-offs in particular in that model. And there you're asking the question, how quickly does the set of states grow relative to the number of agents, right? So you have kind of a family of different protocols depending on the size of the population. And for this talk, we are not doing that. We have one fixed protocol for all sizes of n, so for all possible sizes of the population. And instead, we are varying the predicate that we are deciding. So we still have a family of protocols, one for each predicate that we are considering. And then we are asking how quickly does the set of states grow for this family of predicates that we are considering. Okay, so there has been much progress on this specific question in recent years. In particular, in 2020 and 2022, we've seen succinct constructions for arbitrary predicates. So you take any Pressburger predicate, so any predicate that can be decided by a population protocol, and you try to create a protocol that is small relative to the size of the predicate. Okay, and as it turns out, that works. I'm not going to go into any detail in this talk, but if you're interested, you can come tomorrow to my other talk. Then in this talk, I'm just going to talk about threshold predicates. So here we have seen both upper and lower bounds, which I'm now going to illustrate in more detail. But first, why am I so fascinated by these threshold predicates? So I would say this is the simplest way you can take a number and encode it in a protocol. So this predicate obviously depends on k. It's kind of the simplest family of predicates you can construct where you have such a constant k in them. So in a sense, this is the most fundamental question if you're asking about the state complexity of population protocols, because there you need some infinite family of predicates. Also, as it turns out, if you have results about these threshold predicates, then they're not just about threshold predicates. They also very often extend to other kinds of predicates. So generalizations of the constructions can then be used for example, for arbitrary predicates. And also the lower bounds often extend to different kinds of predicates as well. One thing I want to highlight in particular in ongoing research, we are trying to use these very small threshold predicates to make statements about the decision power of the non-constant space model. So as Vincent showed, there's still, in the variant of the model, if you have very few states, there's still something open. And we think we can use the results for threshold predicates here in this talk to say something about that. Okay, so what's the question? I give you m states, and I'm asking you to decide to construct some kind of population protocol which decides a threshold predicate for as large a threshold as possible. So you have a fixed budget of states. What's the largest threshold you can do? Okay. In a sense, this is the busy beaver problem of population protocols. So if you know the busy beaver problem just in general is I give you a Turing machine with n states, how long can you make it run without and then still terminate? And that's a very fundamental question about the computational power of a model. How succinctly can you encode numbers in that model? And well, it shouldn't be a surprise that population protocols are not quite as powerful as Turing machines, but it's still interesting to look at how powerful exactly they are. Okay, what do we have? So first construction is in 2004 by Engler et al. And essentially, they show that you can do linear thresholds if you have, so linear in the number of states. This is also what you get if you look at the first example back from the beginning of the talk. You can do linear thresholds. So I'm not trying to make them look bad, right? This is just the very first construction. They weren't worrying about constructing small protocols. They were just worrying about introducing the model at all. So that's kind of the simplest thing you get. Also in this table, I list both the model without leaders, which is the model I talked about, and the example was also in that model. But I also have a column for the model with leaders. That's a common extension where you have one designated agent in the beginning, which is kind of unique and can help synchronize the computation. But feel free not to worry about that. Okay, then 2018, it was improved. So in the leaderless model, you can also do exponential thresholds. That's in fact not that difficult to see. And if you're more interested, come to my talk tomorrow. Then in the model with leaders, you can even do double exponential thresholds. Okay, maybe that's also not that surprising because leaders are quite powerful. The first lower bound is appears in 2021, showing that in particular in the leaderless model, triple exponential is an upper bound. So you cannot do better than triple exponential for any threshold. Okay, and that was then improved in 2023 to double exponential in the leaderless model, and then later in 2022 to double exponential for the model with leaders. Don't worry about the years, it's just that was a journal and took longer. Okay, now there's the case with leaders is closed, so we are double exponential precisely. The case without leaders still has a gap, right? So we know that exponential is possible, and we know that more than double exponential is not possible. So the open question is where exactly is it? And as it turns out, it's double exponential as well. So now with our results, in both cases, the gap is closed, and we know that we can do double exponential threshold predicates with and without leaders. Okay. More formally, this is the precise theorem we prove. I give you some number, and then there's a population protocol with a linear number of states, so O of m states, and it decides the threshold whether x is at least 2 to the 2 to the n. All right. Why is that hard? I mean, we already did it with leaders. Why can't we just use something very similar without leaders? Okay, so let's talk about one-aware protocols. We say that a population protocol is one-aware if at some point during the computation, some agent knows that the computation is accepting. Or more formally, there's some state Q that's where it's true that you can reach the state Q if and only if the computation is accepting. If you think back to the example at the beginning, there we had such a state. That was state K. As soon as one agent reaches that state, the protocol will accept. And that's an if and only if. Okay, so that's a nice property to have. And in fact, all prior constructions are one-aware. So that includes the double exponential constructions for leader. That was also one-aware. Okay, so far so good. However, there's this conditional impossibility result telling you that if you have the leaderless construction that's one-aware, then you can only decide thresholds up to exponential. So it's not possible to do better as long as you're one-aware. And again, all prior constructions were one-aware. It's a very natural property to have if you're deciding a threshold predicate. So then clearly we give the first construction that is not one-aware, enabling us to break this conditional impossibility result. And this is also the difficult part. Okay, what do we do? So just very few words about our technical contributions. First one is something you might be interested in if you work on population protocols and you want to construct small ones. We have a kind of a small, simple programming language for a certain kind of register machine. And in that language, you have the standard control flow constructs like branches, loops, and procedure calls. And then it's possible to convert these kinds of programs back to population protocols without a huge overhead in terms of states. However, there's one drawback. I mean, it would be very nice to have that, but unfortunately, to make the conversion work, we have to give a very weak guarantee in terms of the registers. In particular, all the registers that appear at any point in your computation can be initialized to arbitrary values. So you can have any kind of rubbish in them, and you still need to somehow compute the thing you want to compute. Okay, that makes it kind of difficult, but still, I think it's a nice model, perhaps helpful in some cases. Okay, the second thing we do, we look at this classic result by Lipton, where you use a register machine with 4m counters, which runs for a double exponential number of steps. So if you want, that's kind of the simplest way to get to double exponential in these kinds of settings. However, very sensibly, it requires that the counters are initialized to 0, and otherwise it doesn't work. Now, as I just mentioned, in our population program model, that is not the case. So the counters can be initialized to arbitrary values. So our second contribution is that we adapt Lipton's construction and make it self-stabilizing in a sense. So we make it work regardless of the initial values of the registers. Okay, and then, that is also the most difficult part. And then we take this adapted construction and implement this in the population program model. We can then convert those to population protocols and get the result we want. All right, so to sum up, we've proven that you can, with a linear number of states, decide double exponential thresholds in the leaderless population protocol model. This closes the gap to the known upper bound in the same model. This is the first construction that's not one-aware. So we invade this conditional impossibility result. We also get some nice robustness benefits. Then we introduce, to do that, we introduce population programs, a new kind of model for writing small population protocols. And in particular, we adapt Litton's double exponential counting routine, make it self-stabilizing, and then implement it in that model. All right, this brings me to the end of my talk. I thank you for your attention, and I'm happy to take any questions.
Questions? Right?
So you considered special predicates. Can you also say things about modulo predicates with these kind of techniques?
Yeah, so deciding modulo predicates in the same way, so in the same model seems very, in the population program model seems very difficult. I can tell you that the lower bound very likely applies to modulo predicates as well, so you're unlikely to find something that's better than double exponential, but at this point we don't know how to well, okay, you can actually use one of the constructions, one of the general constructions, to kind of construct specific modulo predicates by just combining. So if you have an AND of many modulos, and the modulos are, for example, prime numbers, then you can also get up to very high numbers. Okay, so you can use that construction to also get kind of succinct things, but it's not. It would be a different approach.
Any other questions? Here.
So what he asked, or you answered about the lower bounds, but what about the positive results? So do you think this could also, like this not one-aware approach, could this also apply for stuff that are not threshold?
So, well, this one-aware really is a problem if you have, specifically for threshold predicates, because once you have exceeded a certain number of agents, it doesn't matter how many additional agents exist, the answer will still be true. So in a sense, one-aware protocols only really make sense for these kinds of predicates. And well, yeah, as I just said, you can use the general construction also to make very succinct modulo ones, but it would be a different approach.
Like from first glance, it kind of would look like if it works for threshold, this should also work for any monotone policy function. But
sorry, for what function?
For any monotone policy, like anything that's only ors and ends and without negation.
Well, as long as the coefficients are small enough, then likely yes.
Okay, great, thanks.
I had a quick question, maybe this is a silly question. So if you take the stochastic schedule, what's the running time of these protocols usually?
Yeah, so the running time for threshold protocols is always a bit weird because asymptotically, the number of agents will exceed the threshold. So the only answer is yes, asymptotically. So if you do some, if you just default to answering yes, then you will be very fast. Also, okay, in the specific construction we have lots of non-deterministic guessing, but that's mostly to make the proof simpler. You can also adapt this construction to be with high probability correct. So then, and then also then also with probability 1 correct but slower, and then the combination will give you a relatively fast protocol. But okay, but this construction as it is, I wouldn't recommend implementing it.
All right, let's thank the speaker again. And I believe we will have the last talk of the session, which is a brief announcement by Yuichi on self-stabilizing graph exploration by a single agent.
Thank you, and hello everybody. I'm Yuichi Sudo from Host University, Tokyo, Japan. This is joint work with Fukuhito Shita and Saiga Kamei. Today I'm going to talk about self-stabilizing graph exploration by a single agent. And as I explained in the previous session, mobile agents are computational entity that autonomously migrates from node to node. Okay. And for this problem, we assume there exists exactly one agent, but a single agent. And the goal of this problem is to ensure that this single agent eventually visits all nodes. A very simple problem. And we have three metrics for algorithms. The first one is cover time, the number of agents moved before all nodes are visited, and the memory space of the agent. And in this case, the agent uses also nodes memory, the memory of nodes. So we also evaluate memory space of nodes. We sometimes call this memory space whiteboards. Okay. And in this paper, we consider a much more challenging version of exploration problem. Specifically, we consider self-stabilizing version of graph exploration problem. The goal here is starting from any configuration with exactly one agent on a graph. The agent must eventually visit all nodes. Okay, and any configuration means every variable in the agent memory has an arbitrary value in its domain, and every variable in the memory of every node has an arbitrary value in its domain at the beginning of the execution. So we do not require termination for this problem because no self-stabilizing algorithm can terminate by definition. Okay. Thus, any solution for this problem lets the agent visit all nodes repeatedly. Okay. And we also the same metrics, cover time, the required space of agent memory and nodes memory. And the challenge for this problem is that, when the agent visits a node V for the first time, the content of the whiteboard at V is arbitrary by the definition of self-stabilizing problem. Thus, the content may contains fake information. For example, suppose consider naive DFS algorithm. This algorithm, of course, does not work for this self-stabilizing graph exploration because, in DFS algorithm, the agent must somehow mark the already visited node in the node memory. But however, the agent cannot verify the correctness of the marks. For example, look at the right figure. And the agent visits this node, this node, this node, this node, but they didn't visit these nodes, but these nodes are already marked visited. In this case, the agent cannot visit these nodes. Okay. And but if randomization is available, somewhat straightforward solution works effectively. We can choose a random color periodically and execute DFS using this random color as a visited mark. Then, when we use C colors, we can achieve if we use linear number of colors, we can achieve optimal cover time, or the M. This algorithm is a little bit straightforward, but we analyze in detail how the cover time changes depending on the parameter, the number of colors C. Okay. But if we consider deterministic version, then the situation becomes much more complicated. And actually, this is the main dish of this paper. Okay, But yeah, this algorithm is complicated. So, and this is a brief announcement. So let me skip the detail of this algorithm. But our algorithm has the shortest cover time, or the m plus nd, where m is the number of edges and n is the number of nodes and d is the diameter. In the literature. This algorithm is BFS based and rapidly resolves the inconsistencies from arbitrary initial configuration. And but the agent must know upper bound on the diameter and the maximum degree in advance. And the open problem is, this cover time is not optimal. Trivial lower bound is omega m. So is there any optimal algorithm, deterministic or optimal time optimal algorithm? This is interesting open problem. Anyway, thank you so much.
All right, thank you. In sake of keeping time, I think we have lunch now. So if you can, we can take the questions for the lunch break. But let's thank Jussi and all the speakers again.
Thank you.
final speaker is present. And you have Zoom links, and you are able to connect to Zoom and share. You have tested.
Not that we are counting, but we are starting in 10 seconds. Okay, my phone is beeping, so I guess it's time to get started with this session. And our first talk here is self-stabilizing MIS computation, and Isabella is giving the talk. Please.
Hi. So I will talk about self-stabilizing MIS computation in the BP model, and this is a joint work with George Jacobis and Volker Turov. Okay. Okay, so first of all, what is an MIS? So we have a graph G. An MIS is for maximal independent set. It is a set of vertices with two properties. The independent property, that means that no two nodes in the set are connected by an edge. And the maximality property. That means that we cannot add another vertex to the set without violating the independence property. So the MIS is a fundamental distributed computing problem with many applications. So in this talk, maybe the more related are application in wireless network and biological network. So we consider the beeping model, which is a model that models weak communication framework, such biological cellular network or restricted radio network environment, or in general environment where the single entities are very simple and they are just able to send signal and not messages. So in this case, we consider the model where we have a network of anonymous processor, so they doesn't have IDs. We consider synchronous round, and in each of these round, each node send a signal and then receive the signal. So first, they decide if they want to broadcast a signal to all its neighbors. In this case, they will beep, or if they want to remain silent. So then the node receives messages, and they can just distinguish between two different situations. So if they receive some signal, or if they don't receive any signal. So the vertices cannot detect which node sent the signal or how many nodes. So they just have no signal or at least one. Okay, so since we are looking at large-scale system and biological system with limited communication, we want this system to be able to manage faults. So we focus on self-stabilizing algorithms that are algorithms that are guaranteed to converge from any initial configuration. So that means that if our algorithm starts and then at some point we have some faults in some node in the network, the algorithm is still able to self-recover. And also, one thing is that the nodes doesn't need to agree on a single initial, on the same initial configuration. They can have any arbitrary initial configuration. Okay, so there are many works on this problem. So Afek et al. 10 years ago proposed a self-stabilizing algorithm for the MIS in this model that is fast, it's polylogarithmic, and the nodes require to know an upper bound on the graph size. And then later, Imek et al. Proposed a self-stabilizing algorithm when the nodes need to know an upper bound on the diameter of the graph. In this case, the termination time is quasi-linear in the diameter. Then Afek proposed also a variant of the algorithm, which is not self-stabilizing. The node require no knowledge of any kind, and the termination time is polylogarithmic. And then later, Gibbons et al. Improved the Afek algorithm with some modification, and they obtained termination time of log n. So the aim of this work is to design a self-stabilizing algorithm with knowledge as limited as possible that have a termination time which is optimal. Okay, so our starting point is the Gibbons algorithm, so we'll explain how this algorithm works. So in each round, each node has a state which can be inside the MIS, outside, or active. That means that it's still deciding if we want to be inside or outside. And also each node is associated with the probability of beeping in a round. So in the first round, each node needs to be in the active states, and the probability must be at 1/2 for every node. So then the algorithm works in phases of 2 rounds. In the first round of a phases, every active node beep with probability P, and then the states are updated according to this following rules. So if a node is beeping and it doesn't receive any signal, it puts itself inside the MIS. If a node is silent without a beeping neighbor, it doubles the probability of beeping in the next round. And if a node is hearing some signal, it halves the probability of beeping. The second round of a phase is just for detecting who of your neighbors are joined the MIS. So the node that just joined the MIS beep, and all the nodes that hear beep put themselves in the out state, so they are out the MIS. So this algorithm is not self-stabilizing for 2 reasons. First is that we need a fixed initial configuration. If we change this configuration, the algorithm can be slow. And the second reason is that we have 2 phases, so this requires the nodes to be synchronized modulo 2, and this is not self-stabilizing. Okay, so they prove that the algorithm terminates in long n round. So we propose this variant of the algorithm. So instead of a probability, we associate each vertex with a level, which is in some sense connected to the beeping probability. In the first round, the level can be arbitrary. So the level can be in this interval, so it's up to minus L max to the value L max. And so our algorithm relies on the ability of each node to compute this quantity. So the algorithm works as follows. So it has no phases, and in each round, each node beep with this probability P, which is 1 if the level is negative, and then decrease exponentially with the level, and is 0 when the level is maximal. So the update of the levels is as follows. So if a node is beeping without beeping neighbors, put the level to minus L max. And this is connected to the joining of the MIS, and we'll see. And if a node is silent without beeping a neighbor, it decreases its level. That means that we increase its probability of beeping in the next round. And if he hears some beep, he increase the level. That means that will decrease the probability of beeping. So in this setting, the nodes that are in the MIS and are stable are the nodes that have level, which is minus L max. That means that they will beep with probability 1. And that have all the neighbors in the maximal level, that means that they will beep with probability 0. So when we are in this configuration will never change, and the node inside the MIS will keep beeping with probability 1, and all the neighbors will be silent. Okay, so let's see what happened in the situation where a node is beeping without beeping neighbors. So it updates its level to minus L max, and that means that it will beep with probability 1 for many rounds. So let's see an example. So here we have that the node V has level 3, and some of the neighbors have maximal level, some don't. So in this case, V is beeping without beeping neighbors, so it updates its level to minus 5, which is minus L max in this example. So some of its neighbors are in the maximal level. Those will beep with probability 0, so will be silent, but there is a node that has not maximal level, so may happen that it beep as well. So what happened in this situation is that this is the main difference with Gibbons algorithm. So V is not immediately give up its attempt to join the MIS, but keep beeping for many other rounds. So let's see what happened in this case. So since V has negative level, it will beep with probability 1. Since he heard a beep, increase its level, but now all its neighbors reach maximal level. So in the next round, V will beep without beeping neighbors again. Now all the levels are in the maximal value, and V reach again the minus maximal level. So we reach here a stable configuration, and V joins the MIS. Okay, so I will explain our results. So as I already said, the algorithm relies on the ability of each vertex to compute this quantity. So we consider 3 different variants. In the first variant, the knowledge of the nodes must be the maximum degree of the graph. So in this case, if we assume that Lmax is logarithmic in the maximum degree, we have that this algorithm terminates with time log n, so as the Gibbons algorithm. So if the knowledge of the nodes is more weak, so if a node is required to know its own degree, we can put Lmax to the logarithm of the degree, and in this case we prove that the algorithm has termination times log n times log, so it's a bit slow. And in the last case, we assumed that each node knows the maximum degree of its neighborhood, so you have to look at distance 2. In this case, Lmax is the logarithm of this quantity. In this case, we assume 2 beeping channels, so we assume that the nodes can distinguish between 2 different types of signals, so this helps to implement the phase part. And in this time, we prove that the termination times is log n. So this assumption may be easy, like the computing on the degree, but actually in this model, these are very complicated tasks. So okay, so I will talk a bit about the analysis. So let's consider IT as a set of the nodes in the independent set that are stable, and ST, the nodes stable, so inside the MIS and outside and their neighbors. Okay, so I first review how works the Gibbons algorithm analysis and explain why we cannot use this type of analysis. So they consider a type of round that they call golden. So we say that a round T is golden for the node V if V or one of its neighbors are beeping with probability, are beeping without beeping neighbor with constant probability. So in the Gibbons case, this means that with constant probability, the node in the next round will be stable because or him or one of its neighbors will join the MIS. Then they prove also that if we look at a consecutive interval of rounds of length at least log n, this contains at least a constant number of golden rounds with high probability. So these 2 properties with a Newton bound show that the algorithm terminates in times log n with high probability, because at least one of these golden rounds will lead to stabilization, and then we just do a Newton bound for the nodes. Okay, so in our case, we have that the golden round may lead to stabilization, but may also not. So we introduce a new type of round, which we call platinum. So a round T is platinum if one node between V and its neighbors has negative level, so will beep with probability 1. Okay, so in this case, a golden round for T leads with constant probability to a platinum round. And then the platinum round may lead or to destabilization or to a not platinum round. So what happened is that a round interval for a node looks like this. So we will have some interval or not platinum and golden rounds, then some consecutive interval of platinum, and again some not platinum and golden, and so on until we reach stabilization. So let's see what happened in a simplest case. So when we have the knowledge of the maximum degree. So we assume that the Lmax is the same for every node and is at least log delta plus 15 and at most log n. So in that case, platinum round will lead for sure to stabilization, because that means that in some round V update its level to minus Lmax and will beep for at least Lmax round. So all the neighbors have enough time to increase their level until they reach maximum value. So if T is platinum, then V is stable in round T plus Lmax. So what happened in this case is that we have a consecutive number of platinum rounds, and if this interval is large enough, it will contain at least a constant number of golden with high with probability exponentially larger in the length of the interval. So one of these golden round would lead to a platinum round. In this case, we have that this interval has a length at most Lmax, and will lead for sure to stabilization. So in this case, we have the stabilization in times log n. But what happened in the general case? So if we have just the knowledge of the degree, is the following. So we have that round interval looks like this. So we have the same property of before. So some golden rounds, some of these rounds will lead to stabilization, so to a platinum. So that means that some node U in the neighborhood of V have a negative level. So in this case, if we have this property on the level of U, it happens that this platinum round will lead to stabilization with probability which is at most 1 minus 1 over the degree of V. And if it doesn't lead to stabilization, that means that it will have a length which is at most Lmax plus Y, where Y is a geometric random variable. So we iterate this argument, but in this case, we need to split the vertices in log n sets because we need to verify this condition on the level. So before analyzing the stabilization of a set B, we need to analyze the stabilization of all the previous set. So this is what gives the blowout of log n in the running time. So in this case, we prove that the algorithm stabilizes in times log n times log. Okay, so for concluding, we consider 3 different variants of the same algorithm that differ in the knowledge of the nodes about the topology of the graph. And some open question could be if we can delete this log in the running time, or if we can achieve self-stabilization in this kind of model without requiring any type of knowledge. Okay, so that's all. Thank you.
Thanks. Questions?
Hi, I just wanted to ask, is there a lower bound in this model?
Yeah, I think log n is lower bound in this case. I'm not sure, but I think in one of the other paper there is one proof. In our paper, no.
So my question is somehow similar. So is it possible to get log D?
Yes, but with high probability in that case means proportional to the degree, not in n.
Okay.
You can get log D plus some other number with probability 1 minus 2 at the power of that number.
I was wondering this, you mentioned that in this self-stabilizing setting you have basically 2 challenges in some sense, like you have garbage initial state and you have kind of like lack of common clock that could synchronize these things. So can you somehow kind of like characterize or quantify which of these is the big challenge? Like for instance, if you had access to an oracle that is giving you a common clock even in this self-stabilizing setting, how much easier it would make your life?
Yeah, so this is the third result, because in the third result we assume 2 types of channel, and in this case these 2 types of channel give you the idea of the phases. So I think the most hard part is just the initial configuration, because this gives you some information about the graph.
Okay, thanks. Any further questions? Because we have time, I also wanted to know, if I got it right, you have basically the same number of these negative levels as the positive levels. Is there any magic regarding this, or could this, like the number of negative levels, differ from the number of positive levels? And
yeah, I think that should be at least the number of positive. No, should be the same in asymptotically, because you both need to, like it's a MIS thing, so you need to have like log of your degree of trying to break the symmetry.
Okay, thanks. Let's thank our speaker again. And our next speaker, please. Let me. Yes. And our next talk in this session is about speed up of distributed algorithms for power graphs in the context model. Uri is giving the talk, and at least if I understood right, this is somewhat connected to these things of virtual graphs that we saw on Tuesday. Let's see. Please.
So, as I said, I'm going to talk to you about speed up of distributed algorithms for power graphs, and this is a joint work with Leonid Barenboim. Okay, so again, we're talking about graph coloring, which is a label which labeling the vertices, and proper coloring is where each two adjacent vertices are having different colors. We're talking about the congest model, where each node is a processor and the communication is done over the edges. We care about communication rounds. We neglect local computations and memory, and the message size is bounded. Regarding two similar problems, one is k-proper coloring, where two vertices with distance at most k have different colors, and coloring a power graph properly. The power graph is the case where if two vertices are having at most k hops, then it is marked by a virtual edge, actually. So one motivation, first we handle the case of k equals 2. One example for motivation for k equals 2 is when we want to schedule assignments. Now, we want each vertex to listen to his neighbors, but we don't want two neighbors to communicate at the same time, so two distance coloring can solve this. Another motivation is when we have tasks and resources, so we use biparty graph. So the tasks are in one side and the resources are on the other sides, and each resource the task needs is marked by an edge. Two distance coloring also solve this problem where a resource can't be used by two different tasks. Known issues, known results. One by Halderson, Maus, and Kuhn 4 years ago was coloring delta square plus one coloring within older delta square plus the log star n, and one randomized within log to the power of 6. Our results, we get delta to the power of 4 within log delta plus log star n, order delta square coloring within delta log delta, and all delta square plus 1 within delta to the power of 1/2 log delta plus the inevitable log star n. So we are going to generalize a linear version to work on two distance coloring. Using this, we can achieve delta to the power of 4 proper coloring, and in another round, we can achieve order delta defective, order delta square coloring. Just a reminder, defective coloring is like proper coloring, only we have a threshold of how many adjacent vertices we allow to have with the same color. So how lineals work? If someone don't remember, it uses set system. One of the ways to achieve set system is by using polynomials that intersect little in a prime field, while set system is where we have sets and they have little or non-common objects in them. So our technique have two phases. One phase, every vertex aggregate information from all its neighbors, and in the next phase, it propagates its action. And we do it by looking for a place in the polynomial where there is no intersection. So the best way to look, we know so far, is binary search to look for an index without. So every vertex is proposing the interval and it looks for the left side and on the right side. In our case, the orange a polynomial has two intersections on the right side and one intersection on the left side. So at first, every vertex build an array for all its neighbors of how many intersections they have on the left and how many intersections they have on the right. And then he waits to receive, then he notifies all his neighbors, he waits to receive all the results from his neighbors, and then he decides, he summarizes the results and decides whether he will pick the left or the right. Another optimization is instead of using summarize, we use bit mask when the interval size is less than log n. We use this afterward. So again, the results, if we look for zero intersections, we have delta to the power of 4 proper coloring. And if we allow defective coloring, we reach order delta intersections. So the running time analysis, the first round of lineal have n colors. Every vertex use label with its ID. And it generates order delta log square n possible colors, which means the square root of it is order delta log n indexes. So how many bisections we need after log n intersections, after log delta intersections, we can get to the log n and send the bit mask. So this simulates a single round of lineal, but we need log star n rounds of lineal. So the naive analysis would be log delta plus log star n rounds. But there is Titan analysis that say that if delta is big, after a constant number of rounds, we reach order delta to the power of 8 coloring, and then we need only a single round to reach order delta to the power of 4 coloring. And if delta is small, then every round can, besides the 2 or 3 rounds, can be accomplished within a constant number of rounds. Another additional results we achieve in the paper, a 1-bit model delta square proper coloring with delta square running time, ARB defective coloring, which is similar to defective coloring, just that we count only the out edges, and ARB lineal, which is lineal that works in a ARB defective setting that can produce order delta square proper coloring within delta log delta rounds, and delta square plus 1 coloring within delta to the power of 1.5 log delta rounds. Another issue we handle is k-distance coloring. Just most of the time, we assume that k-distance power graph has delta to the power of k neighbors, but this isn't true. It works in the case k equals 2, but eventually we can say that it has at most delta minus 1 to the power of k vertices, but it doesn't really matter. What matters is that it exponentially gets bigger. Now, what's the problem with k-distance coloring? In the local model, we don't have a problem. After k iterations, we can know information about the whole k-distance neighborhood, including edges, vertices. But in congest model, we can only pass log n times k times delta bits. But the network size is order delta to the power of k. We assume it's smaller than number of the vertices. So one motivation for k-distance coloring is the question whether we can properly color a graph without even knowing the environment. And in our case, we show that for delta to the power of 2k, it's quite easy. And there's still remaining question whether we can do it with delta to the power of k. Current results we found is only by simulating local algorithms. And this is talking about deterministic results. So how our technique works? We are used to types of functions. One are idempotent functions, which are functions that f of x equals f of x. Examples of it are logical OR, logical AND, minimum and maximum. And the aggregative functions we also use are like sum or prod. And we use proxy nodes. The proxy nodes receives information from all its k hops distance. Now, as you can see, P1 and P2 both connected to N6. So in case we use idempotent function, it doesn't matter. But if we use aggregation function, it could matter. That depends of how we allow duplications of messages. And after each vertex receives its k and a half hops distance information, it does the propagation. For example, let's say U1 and U2 are more than k half distance, but vertex V is between them, and they both have the orange colors, and vertex V would know about it, and he could inform them both. This is the basic of our k-distance technique work, and for future work, we would like to ask whether we can solve some additional problem using this technique. I think the most important question is to ask whether we can use this, we can change, modify the state-of-the-art polylog n delta done by, I think, Kuhn and Jafari. And this use MaxCut. Additional problems, we ask whether we can apply this technique in the congest model in the ruling set, aggregation set, maybe delta coloring and edge coloring. And maybe we can use it also for the random settings. There's also some work in this field. And another question is whether this is the most efficient pipelining, or there is a better way for pipelining distance problems. That's it. Questions?
Thanks. Excellent. Plenty of time for questions. So, who wants to start? So I'll definitely have something. So if you go back to this, it was distance 2 coloring where you were dealing with these polynomials and looking for intersections and whatnot. So if I'm not mistaken, this, let's say, the usual lineals algorithm is basically something that works with any cover-free family, and to construct a cover-free family of sets, you can have any set system that has small intersections, and to have a set system that has small intersections, you can use any functions that have few intersections, and one concrete way of doing that is to use polynomials.
Okay.
So I'm kind of like wondering where on this spectrum your technique is. So for instance, like how heavily you are using specifically this idea of polynomials. If I had some other nice functions that have few intersections, can I plug it in here? If I had some arbitrary set system that has little small intersections, can I plug it in?
So basically, the set must be sortable. Like polynomial are sortable by A6x, and an arbitrary set won't work because two vertices won't know how to communicate, counting how many intersections they are. In the polynomial, we use this feature to define an interval. If you can somehow sort it, so I guess it's possible, but I don't see how much you would gain.
Right. So you basically need to have these kinds of sets that are kind of like two-dimensional plots of some function, if I get it right, so that you have X dimension and Y dimension.
No,
and
you just have to, it have to be sortable so you can have a binary search.
Right, right. Good. Okay, makes sense. Other questions, thoughts, comments? I'd of course like to hear your thoughts on because here you're basically doing coloring in power graphs, and 2 days ago we had this presentation that was doing coloring in virtual graphs, and one virtual graph is a power graph. So can you say some words on this?
So I ignore the fact that the virtual graph is power graph, but if you try to change it like for somewhat the problem of edge coloring, then you would somehow have to adjust the problem and have much more information. This technique won't work. As I've shown in the first slide, a distance k proper coloring is equivalent to power k graph. So actually in my technique, I'm ignoring the power k graph and trying to handle specifically the distance k proper coloring. So I am not using virtual edges in this technique. I think that power graph is problematic in case of congestion because you just have two additional information. And you, in congestion, you always want to reduce the amount of information you need.
Thanks. Any more questions? Okay, let's thank our speaker. And the final talk in this session is faster cycle detection in the congested click, and Tomer is giving the talk. Please.
Hi everyone, my name is Tomer Even. I'm a PhD student at the... Okay. Can you hear me now? Great. I'm a PhD student at the Technion. I'll be presenting a paper, Fast Cycle Detection in the Congested Click. This is joint work with my advisor, Keren Sensor-Hillel, and also with Virginia Vasilevska-Williams. So we consider the problem of finding an H cycle in a graph in the congested click model. For the special case of finding a triangle, we present a randomized algorithm that succeeds with high probability. Its round complexity is n over t to the power of 2.5 raised to the power of roughly 1 over 6, where t is the number of triangles in the graph. And we generalize this result for H cycles. The constants come from matrix multiplication. I will address this later, but we will focus on triangles for this talk. Okay, so basically, we want to find the triangles, and we don't know how to do it faster than matrix multiplication, so we add another assumption. Let's assume there are a lot of triangles, and then we hope to be able to find a triangle faster, and we show that this is indeed the case. And we also generalize it for each cycle. Great question. Thank you for the question. So if the graph has at least n to the power of 0.4 triangles, we can find one in constant time. So basically, in the congested click, we want everything to happen in constant time. There's no lower bounds. I'm like skipping 5 slides, but we'll get into that. Great. Okay, so let's overview the model real quick. We start with the congest model and then talk about the congested click. So in the congest model, we have an input graph seen here in red, and we have rounds. In each round, each vertex computes something locally, sends log n bits to all of its neighbors, and then receives log n bits from all of its neighbors. And the goal of the algorithm is to minimize the number of rounds. This is the congest model. I guess everybody know it. And in the congested click, the input graph and the communication graph are not the same. The communication graph is the complete graph. So our life are easier in some sense, and every 2 vertices can exchange log n bits messages, even if they are not adjacent in the input graph. Okay. So before presenting some related work, I think I have to apologize. The field of subgraph detection and listing is huge, and I probably forgot someone, and probably someone in this room, so I apologize. Honest mistake. And okay, let me start with a problem which is better understood, the listing problem. For example, triangle listing, we want to find all triangles in the graph. So every vertex has to output a set of triangles, and the union of the set should contain all triangles in the graph. Okay, so every triangle is output by some vertex. So there's a tight upper and lower bound for listing H cycles in the congested click, and there is also a listing algorithm which is sensitive to the number of edges in the graph. So if the graph is sparse, we can do it faster than in the general case. Okay. For finding triangles, there are many techniques, but the most simple one and the one we are based on are using sampling and matrix multiplication. There's a sampling algorithm which takes n over t squared to the power of 1 over 3. T is the number of triangles, so if there are many triangles, this algorithm is faster. And there is a matrix multiplication-based algorithm which doesn't care about t and takes n to the power of 1 minus 2 over omega, where omega is the matrix multiplication exponent. And as you can see, the listing problem has a lower bound. The triangle finding problem does not have a lower bound. And in general, in the congested click, we have lower bounds for problem with big output. For example, if we want to list all triangles, it's possible that the number of triangles is n cubed. So the output is very big, so we can use some tools to get a lower bound in this case. For finding a triangle, the output is of size log n bits. So we have to use different techniques, and basically we don't have a super constant lower bound in the congested click for problem with small output. And there's a result which roughly states that if you get some lower bound for problem with small output, a super constant lower bound, then it will imply a new second new circuit complexity lower bound. Okay. So the two techniques of sampling and matrix multiplication are used also in centralized computation. Basically, this is the only way we know how to find a triangle. If anyone has a new idea, I'd be happy to hear about it. And sampling is probably the most simple graph algorithm thing that you can do. You sample a subgraph and you try to solve the problem on the smaller subgraph, hoping that because it's smaller, it would be faster. Okay? The second technique is matrix multiplication. We could use matrix multiplication to detect special types of graphs, such as triangles. For example, we can detect triangles in the graph by computing the third power of the adjacency matrix and testing whether the diagonal contains non-zero entry. And if it does, then the graph contains the triangle, and otherwise it does not. So a bit about the exponents of matrix multiplication. Omega is the matrix multiplication exponent in centralized computation. It's at most 2.37 something. And we use rho to denote the matrix multiplication exponent in the congested click model, where this is at most 1 minus 2 over omega and roughly 1 over 6 for this talk. Okay, so one of the main questions that we ask in this paper is, can we combine the sampling approach and the matrix multiplication approach? What do I mean by that? We want an algorithm which is fast when the number of triangles is large, and we also want to benefit the matrix multiplication algorithm. And we answer this question in the affirmative. We get the green line, which I hope you can see that it's green. It's the best of both worlds. We combine both techniques, the sampling and the matrix multiplication, and more specifically, we sample fewer and larger induced subgraph compared to the sampling approach, and use matrix multiplication on every sample to detect whether it contains a triangle or not. Other than that, we have two extra algorithms. One of them seen here is always slower than the green algorithm. It uses rectangular matrix multiplication. It's even simpler than the green line algorithm. It basically samples one set of vertices and tests whether there's at least one vertex that participates in a triangle using rectangular matrix multiplication. And although this algorithm is always slower than the green line algorithm, we managed to combine those two algorithms into an even faster algorithm in here. Okay. And I think I was a bit surprised by this because we have a fast algorithm, the green line algorithm, and the slower algorithm, which is the purple line, and we managed to combine them into a faster algorithm, seen here in blue. And we do so by taking a closer look on the worst case instances of each one of those algorithms. So for the 10 minutes I have left, I'll try to highlight the tools that we use to get each of one of those algorithms. Okay. So I'm going to explain how to get the green line algorithm. It's an n over t squared to the power of rho algorithm. T is the number of triangles. Rho is roughly 1/6. We use the following notation. VP denotes a random independent subset of vertices where every vertex is sampled independently with probability P. And we define very general family of algorithms, which we call find a triangle. It works as follows. It samples R vertex sets UI, where each UI is sampled according to VP. And then for every sample, we test whether the graph induced by the set UI contains a triangle using matrix multiplication. Basically, the most simple thing you can do. And this is a family of algorithm and not an algorithm because I have to specify R and P to give you a concrete algorithm. R, the number of samples, and P, the sampling probability. So using the second moment method, we show that if you set P to be 1/t and R to be t squared, then you find a triangle with constant probability. And to complete this description of the algorithm, I have to explain how can we compute the product of t-square matrices of size n/t by n/t. Okay, so this is the hardest slide in this talk. I will go slow, but if you don't understand something in the slide, it's okay. You don't have to understand everything in this slide. So instead of solving the previous problem, we solve a more general problem of computing the product of R pairs of k by k matrices. We denote by SMM or square matrix multiplication KR the deterministic round complexity of computing the product of R pairs of k by k matrices. And we do so for k between square root n and n, and every R such that k squared times R is at most n squared. So before talking about the upper bound, let's talk about the input and the parameters. So the quantity k squared times R is the number of entries of the input matrices. We have R pair of matrices, each one is of size k by k, each entry contains log n bits. So we assume that the input is of size at most n squared. This is the parameter for our theorem. And before I talk about the upper bound, I want to talk about the term time route. This is basically an overhead that you have to pay in case your input is not evenly distributed among the vertices. Okay, we are in the congested clique, not centralized computation, so I didn't even specify what is the input, which vertex gets which matrix, how, it's not clear. So an example of an unevenly distributed input is two matrices, A and B of size n by n, where one vertex gets the entire matrix A and the other vertex gets the entire matrix B. In this case, almost all vertices don't get any part of the input, but one vertex gets half of the input and another vertex gets another half of the input. So we call this type of input unbalanced, uneven, and in this case, the overhead would be very big, to be of size linear. Luckily, in our case, where we sample the matrices are induced by the samples and the adjacency matrix of the induced graph, the time route is small. It's O of log n with high probability. So basically, we sample something, and then we get the input by this sample. Okay? Okay, now let's talk about the running time. There are two parameters, and it's not clear what I should try to do. Should I choose k to be smaller, the size of the matrices, or should I try to minimize the number of matrices that I'm trying to multiply? And basically, if you want to use this tool, which I think, let's talk about the application, you don't really have a choice. You have this sampling and then running an algorithm, and you want it to succeed with a constant probability. So you use some probabilistic algorithm, probabilistic analysis, and get two parameters, R and P, and then you plug it into this theorem to get to get some running time. And this is what we do. We get the green line algorithm by setting R, the number of samples, to be t squared, and k to be n/t. And we do need these two parameters. We get other results with different choice of parameters, so that's why I show you this complex theorem. Okay. So there are other works on matrix multiplication, computing the product of one pair of matrices, R pair of square matrices of size n, and also R pairs of rectangular matrices, but the input is assumed to be evenly distributed and not They don't get the input by sampling something and then doing something on it. Okay, back to the easy stuff. Let's talk about how I get the purple and the blue line. So the blue line is very, very simple. You sample a single vertex at VP, test whether VP contains a vertex in a triangle using rectangular matrix multiplication. The cost of this operation of testing whether a vertex is in a triangle requires computing the product of a square matrix of size n by n and a rectangular matrix with n rows and np columns. This takes roughly np to the power of 2.9 raised to the power of 4 rounds. And it's an easy exercise to see that if p is at least 1 over the cubic root of t, a triangle is detected with constant probability. Okay. Now I take this slower algorithm and the previous faster algorithm and I combine them into a new algorithm which is faster. And to do that, we show that the two algorithms complement each other. When one is fast, the other one is slow, and vice versa. And we introduce a new parameter to show this. This new parameter is the number of vertices that participates in a triangle. We denote the set of vertices that participates in a triangle by V delta and its cardinality by X. And we analyze each one of those algorithms with respect to X. So analyzing the second algorithm, the purple one, the find vertex in triangle, is relatively easy with respect to X. We simply have to set the sampling probability to be 1 over X, and then there's a constant probability that we find a vertex in a triangle. The running time is faster, and it's faster than the green line algorithm when X is at least 1.45. Okay? So we get we see that we have an algorithm which is faster than the green line algorithm when X is sufficiently large. But this does not complete the case because we need to have an algorithm which is faster when X is smaller than T. And for that, we use the other algorithm, the find triangle algorithm. We again choose the parameter a bit differently. We set P to be 1 over X and R the number of samples that we make to be X cubed over T. Using the second moment method, we show that you can detect an algorithm. This will detect an algorithm with constant probability. Ignore for a second the running time. We get an algorithm which is faster than the green line algorithm when X is asymptotically smaller than T. And this algorithm is slower as X increases, while the other algorithm is faster as X increases. So they complement each other. And in any case, we get an algorithm which is faster than the green line algorithm. So to get the blue line algorithm, we have to set, is the worst case when X is, when the two algorithms have the same running time. Okay, you just have to massage the equation a bit and get this running time. Okay. Let me summarize and show you another graph real quick. So we compute the product of R square matrices of size k by k that are sampled at random. We use this to get a faster congested click algorithm for finding an 8 cycle using sampling when the number of copies is big. And we also show a quantum congested click algorithm for finding a triangle, which is faster than all known algorithm, even if T, the number of triangles, is either 0 or 1. Okay, let me show you the graph for the quantum algorithm, and with that I complete my talk. The gray line is the quantum algorithm. It's faster than the classical algorithm, even if the number of triangles is 0. This is the first quantum improvement for triangle detection. There are quantum improvements in the congested click for other types of graph, but not for triangles.
Thanks. Questions?
So all the algorithms are randomized. Do you think there is like hope to get to these results with a deterministic type of technique?
I think it's a good question. I think there's a chance to get all algorithms with deterministic algorithm because basically we only use the second moment method, so the dependency is limited. So I think it's possible. It's a good question. I don't know.
Hey, thank you for the talk. So you take P to be 1 over T initially, then 1 over X, but you don't know the value of this, like you don't know these values.
Yeah, I really appreciate the question. It's a great question. So you can solve it using doubling. Let's assume that I have an algorithm which gets as input this parameter, and then you run it, and if you believe the analysis, you get the right algorithm. Now you can simulate this parameter. You start with an underestimate or an overestimate, and you just double it by a factor of 2. And when you find a triangle, you know, I start with a p very, very small because I want a fast running time, and then I won't find a triangle. And eventually, by doubling the value, I will find a triangle. Even if I have 2 parameters, I can do this doubling, and I have to pay an overhead of log n factors or something like that.
So you mentioned kind of different kinds of matrix multiplication flavors in your talk, like rectangle one and matrix multiplication and so on. So I'm kind of wondering, like, if you get an improvement for some specific flavor of matrix multiplication, so maybe not the general version, but just the sparse version, or is it only if you have an improvement for the full matrix multiplication that you would get an automatic improvement in your algorithm? So
yes. Yeah. Okay. Okay. So. The simple answer is for almost all algorithms, if you improve omega, if someone will get a new algorithm for omega, which is slightly faster, then we get a faster algorithm. There is a problem in congested click where rectangular matrix is not a convex function. I don't know if it tells you anything or not. It is convex in centralized computation. It's not convex in congested click algorithm. This is why we don't have a quantum version for the blue line. So this is one open question in matrix multiplication field with respect to congested click. And to answer your question, most of our algorithm will benefit from every improvement to the constant of matrix multiplication.
Could you combine your algorithm to find the shortest or longest cycle? Would there be any benefit of this?
I know Keren and some other people have a paper where they do 1 plus 1 approximation for Girth for the shortest cycle in the congested click in constant time. We can find a triangle or a cycle if there's many, but if there's only one,
okay.
Other than the quantum case, we don't have any improvement for that.
And at one point, you defined the set VP to be a random independent set. How do you find a random?
It's just like every vertex samples it uniformly at random, or one leader sample it and notify all vertices. We have the the communication graph is complete, so we don't have a problem of sampling each vertex independently.
Oh, so it's not an independent set?
No. It's not an MIS. No. Yeah.
So the choice is independent.
Yeah. Sorry.
I'm wondering if you think it is possible to extend your quantum results to H cycle?
Okay, so well, the technique that we use doesn't work for H cycles. I can explain why. I think it's very simple, but maybe you can extend something. I'm not saying you cannot do it, just like this straightforward thing doesn't work. So basically you have one matrix and you want to do matrix multiplication on it to say if there's a triangle in the graph or not. And you split it into smaller matrices, which are small on one side and big enough to minimize the number of times you have to repeat this algorithm. And the exact choice would be such that every multiplication would take constant number of rounds. And then you have to do some like 1 over p cubed repetitions. And the cubed is because of the triangle has 3 vertices. And if you want to do an H cycle, it won't be cubed, it would be to the power of H. And then the Grover search that we use will not give something better than what is already known.
Can you still show quickly this general result that you had for H cycles? Like you had a slide where you mentioned some kind of expression.
Okay.
I missed that.
So basically you're asking, I'll tell you, maybe it's not the thing that you're interested about, but this trade-off between the two algorithms is true even for H cycles. As long as the number of vertices that participates in an H cycle is x to the power of whatever is written here, this is the worst case for both algorithms, independent of H in some sense.
Right. So the main reason I'm wondering this is that I think if you don't have this parameter t here, we at least suspect that, like, let's say triangle detection is kind of like multiplication hard in some sense, but detecting 4 cycles is all of a sudden easy.
Detection, directed 4 cycles or undirected?
Sorry?
Are you talking about 4 cycle? Even cycle is easy in the undirected case.
Yes.
As hard in the directed case.
Okay, so this is also for directed
Right.
cycles. Okay, that was exactly what I wanted to ask. Thanks. Any further questions before we conclude and head for the coffee break? I guess no. So let's thank all speakers of this session. There's now a coffee break, and we will continue at 4 o'clock sharp here. speaker of the conference around. There.
Welcome back, everyone. So our next session is going to be on parallel graph algorithms. And for the first talk, Kuba is going to be telling us about parallel set cover and hypergraph matching using uniform random sampling.
Thank you. And this is joint work with Lakshman, Michael, and Slobodan. All right, so this is going to be about set cover. Let me start by defining the problem. I'm sure most of you have seen it in some form, but let's define how we think about it. So we have a set T of elements that we would like to cover. And to cover those elements, we have a family of sets S. So each set in the family S is a subset of T. We would like to find as few as possible of those sets such that they collectively cover T. So we will represent an instance of this problem with a bipartite graph. We have elements on the right side, sets on the left side, and each set is collected to all the elements that they cover. So in this example, an optimal solution has size 2. You can see that every vertex on the T side is connected to some set in the chosen subset. And there is no way to cover everybody using just a single set. Because a set cover is computationally hard, we consider an approximate version of the problem. And so if opt is an optimal solution, then we say that the correct solution C is an alpha approximation if its size is at most alpha times the size of opt. Here in the picture we have 3/2 approximate solution. Its size is 3. The optimum size is 2. In this work, we present new algorithms for approximating set cover in multiple parallel models. Now, I think the cool thing about the paper is not necessarily the results that we obtain, but the technique and the algorithms themselves. Specifically, the algorithms are extremely simple to the point that I will be able to provide you with the whole pseudocode. And because they're so simple, they're very easy to instantiate in multiple models. We give 2 concrete examples, but you would see how the algorithms map to many more models very easily. The models that we consider in the paper, and because I will not go into the details of implementation, I'm only giving a high-level definitions of those models. The models that we use are MPCs with a massively parallel computation model and a PRAM model or work depth model. So in both models, we have synchronous computation steps. In MPC, we have multiple machines, each having separate memory, and then the space or the memory of each machine is sublinear in the input size. And then the machines communicate by sending messages. Each machine can send or receive messages in size proportional to its local space at the end of every round. In PRAM, the story is a little different. We have shared memory. Each processor can access the entire memory and modify a constant number of words in memory at each step. The goal in both models is to minimize the number of computation steps. If this sounds too vague, don't worry, we will not really be using those definitions later on. And if you're curious about how MPC is defined, I know Jeff in the next talk will be defining this with more detail. Okay, so what are the results that we obtain? So we actually obtain multiple results. Here is just a subset of those that I simplified slightly for the simplicity of the presentation. So for example, an MPC with sublinear space per machine, and we can obtain log n approximate set cover in log to 3/2n rounds compared to log squared n from prior work. And then for F approximate set cover, F is the maximum number of sets covering any given element. So it's, in other words, is the maximum degree of any vertex on the T side of the graph that I defined. We obtain root log n round algorithm compared to roughly log n round algorithm that was known before. And in PRAM, we improve the depth of the algorithm for F approximate set cover from roughly log squared n all the way down to log n. I'm not giving the precise constant factors here, but actually they're pretty good. So for example, the O of F is actually 1 plus epsilon times F, but I'm just presenting it this way for uniformity. Okay, so the plan for the rest of this talk is I will first give you a high-level overview of the F approximate parallel algorithm. Then we will talk about hypergraph matching. It turns out that our techniques also extend to that problem. and then log n approximate set cover is going to come up towards the end. All right, so let's start by reviewing the following textbook algorithm for F approximate set cover. Again, F is the maximum number of sets that can contain a given element. So a very simple algorithm. We start with an empty solution, no sets added to the solution yet. And then as long as some element is not covered, we pick any uncovered element and we add to the solution all sets covering it. And we call this element a chosen element. It may seem that adding all sets covering that element is wasteful, and indeed to cover just that element, one would suffice, but the intuition is that we do not know which of the sets covering it's good to add, so we just add all of them. And the analysis just fits on the remaining part of the slide. So if we look at the chosen elements, let's assume that there are k steps of this algorithm, so we chose k elements in total. We can see that by the construction, no set covers more than one of them. This is immediate from the way we build the solution. So because no set can cover any two elements, it means that any solution must have size at least k, which is the number of steps of this algorithm. On the other hand, in each step we add at most f sets to the solution, so immediately we get that this algorithm gives us an F approximation. Okay, so that was simple. Now, how do we make this parallel? And it turns out that, and this is actually the part that I find extremely surprising, the most straightforward way of making this algorithm parallel actually turns out to work. And so what I mean by that, this is our parallel algorithm. We start with an empty cover. We start with a sampling probability, which is epsilon, which is a small constant divided by n. And then as long as we have not covered everything, we would simply sample every element independently with probability p. We would take all of the sets covering the sampled elements, we add them to the solution, and we increase the sampling probability by a small constant factor. So instead of making sequential choices of elements, we sample potentially many of them in parallel independently. So you can see probably pretty easily that this algorithm runs in log n steps. P increases by a small constant factor. I mean, it's bounded away from 1 because epsilon is assumed to be a constant. And then the output is a proper set cover because at some point we reach a step where P becomes 1. So we sample all uncovered elements, add all sets covering them to the solution, and then we're done. The only tricky part is how to prove the approximation ratio. And for that, I will provide a high-level idea of the argument in the next slide. Okay, so if S is any set, and then we denote by chosen of S the number of chosen elements contained in that set, then in the sequential algorithm, we show that chosen of S has size at most 1. In our parallel algorithm, we're going to show something slightly weaker. We're going to say that the expected number of chosen elements in any set is at most 1 plus epsilon. Once we have this fact, the rest of the analysis is actually a mechanical rewrite of the analysis that I showed you in one of the previous slides. So now the question is, how do we prove this fact? How do we show that the expected number of chosen elements in each set is at most 1 plus epsilon? We define the following random process. And this is actually the core of the technical contribution in the paper. So let's say we have a set A that has size n. And we define a sequence of probabilities where pi is epsilon times 1 plus epsilon squared to the power of I divided by n. So this is basically what we had before. We start with epsilon over n. In each step, we multiply it by a factor of 1 plus epsilon squared. And now let's consider the following process. We started with our set A, and then we proceed in log n rounds. In each round, we sample from our current set every element independently with probability pi. If we sample anything, that's the return value of the process. Otherwise, we continue, and then an adversary may delete some of the elements from our set, with the restriction that they cannot delete everything. At least one element has to stay. So because of this restriction, this process always terminates. At some point, we will get to the point that something is sampled and returned. And then for the purpose of analyzing the algorithm, we analyze this process. Now, in the algorithm for the f-approximate set cover, the set A is going to be the set of elements that are contained in one set. And you can see that if you plug in some of the facts that we show, they would give exactly what we need. So we show two things. One is that the expected size of the returned set Z is at most 1 plus epsilon. And this is actually the only thing we need to show the approximation guarantee of f-approximate and log n approximate set cover later on. And then we show also the second fact that for any element of the set, if it's part of the returned set Z, with pretty good probability, it is the only set that we return. So the probability that we return A plus something else is at most epsilon. And this fact is actually only needed for the matching part of our result. It's not even used for the set cover results. Any questions on this slide? This is the most technical, so it's a good one to make a quick pause. Yes. Oh, the second one is not needed for set cover. It's needed for maximum matching, which is coming up on the next slide. All right. How do we? Oh, sorry, not yet. Next slide. There is something else in between. How do we do it in MPC? Well, in MPC, and if you're not into MPC, I'm sorry, this may be a bit cryptic, but I'll be fast so that the pain does not last too long. We apply round compression, and we actually apply it sort of the most standard way possible. So we would like to simulate the root log n rounds of that algorithm in log n MPC rounds, and to that end, we can pre-sample the elements that would be chosen in the next root log n rounds. Those random choices can be made upfront. And then if we look at our graph representation, you can show that the graph becomes very sparse when we do that. And on that sparse graph, we would like to simulate some number of rounds of the algorithm. Well, in order to do that, we will use graph exponentiation to compute a ball of radius root log n around each vertex. And then if we know the root log n neighborhood around each vertex, we can actually simulate root log n rounds of the algorithm. And assembling this root log n neighborhood around each vertex takes log n rounds due to graph exponentiation. That's the high level sketch. All right, now on to the next problem. I also mentioned we do maximum matching, and this is our algorithm. Again, it's very simple. So here we have an input, which is a graph G, and then we do as follows. We proceed in log n rounds. In each round, we sample each edge of the graph with probability pi. Pi is defined as before. And then we add those sampled edges to our solution, to our matching. We remove all the matched vertices. If we just do that, some vertices clearly may be incident to more than one matched edge. So we fix it again the most naive way. We simply say that in the final solution, we only add the final matching the edges which are isolated in the set C that we built. So only the edges that don't have any incident edge in C. And this is exactly where we need the second property of the set sampling process. We are able to show that actually the probability that an edge added to the solution C is incident to some other edge is actually also bounded by epsilon. Now, this leads to a very simple MPC algorithm for matching that runs in root log n rounds. That was known before. Maybe the benefit of this algorithm is that it's arguably simpler than the previous one. It's actually very simple to again apply the round compression technique. The main benefit of this algorithm is that it also extends to hypergraph matching. And actually for hypergraph matching, we improve upon a previous bound quite significantly. We go from log n to root log n round complexity, at the same time reducing space per machine from linear to sublinear. So we improve along 2 dimensions at the same time. And then finally, how do we do log n approximate set cover? Again, this is the textbook algorithm for log n approximate set cover. It simply says at every step, add to the solution a set that covers the largest number of yet uncovered elements. So it's a very greedy process and also very sequential. Try to cover as much as possible with each set you add to the solution. And similarly to the F approximation, we have also a very simple parallelization. Now we have a nested loop. The outer loop is going through the set sizes. So if delta is the maximum set size, we're first going to be looking at sets of size at least delta over 2, then delta over 4, and so on. And then the inner loop is very similar to what we've seen before. We proceed in log n steps, and then in each step, we now will sample each set of size at least I, or any set that covers at least I yet uncovered elements with probability P, again independently. And then we add those sets to the solution. We slightly increase P by a constant factor. And the same kinds of properties apply. It's easy to apply round compression. It leads to better bounds. And then the interesting thing is that the very same set sampling process and its analysis allow us to analyze the approximation ratio of this algorithm. I find this also a bit surprising because in the first algorithm we were sampling elements. Here we're sampling sets. Turns out the same technical lemmas suffice to prove the approximation ratio of both algorithms. And this is actually, in terms of results, this is it. So let me summarize. So we give simple and parallel algorithms for both set cover and hypergraph matching. And the algorithms lead to improved bounds in MPC and PRAM. But in terms of the future direction, I think the most exciting questions are whether the technical tools that we developed for those algorithms may be applied for other problems in the parallel setting, and also whether the algorithms themselves can be implemented in other models than MPC or PRAM. I have an intuition that potentially in the dynamic setting, because of the simplicity of the algorithm, we may be able to get something by applying those techniques. Thank you very much.
Thank you for the presentation. So we have about 2 minutes for questions. So yeah, feel free to ask any if you have them. Okay, so in the meantime, I had a question. It looks like one of the tricky parts about the sampling process is deciding how fast to scale up the sampling probability. Here it's 1 plus epsilon squared. Is there a reason that this is picked? If we picked other scaling up factors, would it change the analysis?
Yeah, so I said it's 1 plus epsilon squared. There's probably some constant missing there, but I omitted this for simplicity. I think this is the fastest growth for which we were able to show that it works. We tried for quite some time to show it for 1 plus epsilon, and we failed. And there are technical reasons down there in the proof that for us what made us go all the way down to 1 plus epsilon squared. And I'm happy to talk offline more about the details and give you a proof sketch, but maybe more than the 2 minutes that I have here.
Does it help here in any way? Does it give you insight to look at the tool, like for what you did? Because it seems like no, but maybe you have an insight.
So for which part? Like in the... Yeah, so we used it to analyze the both actually variants. We used like the standard dual fitting analysis, and then some previous algorithms for set cover that were known in those models. They were also, I believe, inspired by looking at duals. The challenge with those is that they were slightly more complicated. And for example, in MPC, it was not possible, or it was not clear how to apply the round compression to those algorithms, because there was some decision points within the algorithms, and you couldn't say something like, I can pre-sample the elements that would be chosen in the next T rounds. There was some decision points in between that actually affected what was happening. We have a simpler approach, I would say, that does not go through the dual, and actually it's also amenable to round compression. And the dual is used for the proof. Yeah. It's a good question. I suspect that the results may, for the log and approximate set cover, I suspect that the results may also carry over. I'm not certain as I say this, but I do not see a reason why the weighted part would be harder. Yeah, exactly. So that's why it intuitively feels this should also apply, and potentially. And at this point, I'm not 100% certain whether this is like a simple technical extension, so we did not bother writing it down, or at some point we saw an issue and that's why we didn't write it down. I feel like it's the former. The approximation ratio holds an expectation. You get a feasible set cover. Yes, it's always the correct set cover. The running time is always the same, but the approximation ratio holds an expectation.
Thanks for the questions. Unfortunately, we don't have time for any more, but I would encourage you guys to continue the discussion offline. So let's welcome our next speaker. So for the next talk, Jeff will be telling us about massively parallel ruling set made deterministic.
Hi, everyone. Sorry, my voice is a bit low today. This is joint work with Zara Parsayan. And okay, let's get started. So we are in the MPC model. I'll give more or less full details about the model. So in input, we have a graph G with n vertices, m edges, and whose maximum degree is delta. So in this model, there are m machines, each with memory S, usually S words. The global memory, therefore, is S times m, which is usually up to polylog n factor the size of the input, so n plus m. Initially, the graph is distributed arbitrarily among machines, and the computation proceeds in rounds. In each round, the machine receives messages from previous rounds, if any. Then they are allowed to do arbitrary local computation, often polynomial, but not necessarily. In this case, would be polynomial. And then they will send messages up to size S. Both data center received is always up to size S. The goal is to optimize the round complexity. This is the primary goal. A secondary goal are global space, so to respect the global space, and then randomness. So does randomness, is it needed at all? This paper actually focuses on whether we need randomness or not. There are three memory regimes. Superlinear, where the memory is n to the 1 plus delta for some constant delta. This is somewhat easier than the other models. Near linear and sublinear, where again the constant, like delta is a constant. Some of the most interesting problems are symmetry breaking ones, where you try to find some, like to break the symmetries. One of the maybe most fundamental, the maximally independent set, and two ruling set is a relaxation of these, in the sense that you find a subset S of non-adjacent vertices. So in some sense, this subset S is independent, and every vertex in the graph is a distance at most 2 from some vertex in S. Does the problem make sense to everyone? Okay, we're interested in the question, what is the deterministic round complexity of two ruling set in MPC? Let me start with linear MPC. It is known that it can be solved randomly in a constant number of rounds. This was a paper at last year DISC. And deterministic, there is a log n round complexity algorithm. For maximal independent set, it is interesting to compare the complexity of two ruling set to maximal independent set, because two ruling set is a relaxation of the latter. So for randomized, there is log log delta and deterministic log delta plus log log star n. We match the constant round complexity of CKPU. In this sublinear model, the fastest randomized one is order of log 1/6 delta plus log log n. And for maximal independent set is square root log delta plus log log n. For the deterministic case, in both, there is log delta plus log log star n, because MIS, as you saw, is strictly harder, so ruling set is easier, and any algorithm for MIS works for two ruling set as well. We give algorithm that runs in square root log delta plus log log star n rounds deterministically. This is a de-randomization of the randomized local algorithm. It's another distributed computing model that I think most of you know. And we match the complexity, and we'll see the similarities of these algorithms. I'll outline some de-randomization tools that are what we mostly use in the paper. So one of the most important tools is k-wise independence. We have a family of hash functions that map, say, n, the vertices, to some bit string of length L. And this family is, each hash function is specified by a string of this length, k times log n plus log L. It can be improved when the kind of dependency are somewhat limited in sense of neighborhood of a vertex. So if the random choice of each node depends on neighbors at distance, almost L, then we can compute a coloring that maps each vertex to a color that is at most poly delta. And with that, we can replace the labeling of n with poly delta. So eventually the seed length will be k times log delta. Then the randomization is as follows. There is some random x that we are interested in and we want to compute. And when is it the case that we can get this x in order of 1 MPC rounds? So there are two conditions. The first one is that the expectation is good when the k is order of log n base delta of n. And the second condition is that this hash function, this picture perhaps illustrated better. So you can decompose the computation of this expectation across machines, so that each machine will compute a part of the expectation. So there's some. No, it's very thin, sorry. So yeah, you see the two summations. So we decompose it across machine, and then we aggregate all these numbers and pick the best age. Why this works in a constant number of rounds? Because k times log delta, the length of the seed, is log n, and in MPC we can randomize log n bits, order of log n bits, in a constant number of rounds. Okay, let's look at the algorithms. I present first the one in sublinear MPC. So a common approach for two ruling set is to compute an MIS on a subgraph that is incident to every vertex in the original graph. So some subset of vertices V prime whose neighborhood covers the whole graph, condition number 2. And the smaller the degree of this subgraph, the algorithm will run, the faster the algorithm will run. So usually in this case, we get maximum degree 2 to the order of root log delta. So if you plug in the algorithm we saw before, the MIS will be computed in root log delta plus log log star n time. This is the outline of the algorithm. I give you some more details about the finding V prime. We have root log delta many phases. In each phase, we want to compute a subset of vertices that rule the class Vi, where the class Vi consists of all the vertices with degree between delta I and delta I plus 1. This Vi should have two properties. The first one as we saw before, the degree to be bounded by 2 order of root log delta, and the second property that covers all the vertices vi. Then we will eliminate this from the graph under consideration, and we will merge all these subgraphs together on which we compute the final MIS. And this will be a two-ruling set by construction. Okay, I'll show you a slow approach that doesn't work, and then the one that we use. Look at this graph as a bipartite graph. On one side, you have the vertices that you want to cover, and the other side, all the neighbors of them that you want to subsample. At the beginning, all vertices are considered, and then we subsample them. In this case, consider of subsampling them in a single step. So if you want to subsample them in a single step to get that probability, I think it should be, 2 to the root log delta, and then the expected degree will be something order of 2 to the root log delta. But there is a problem. Here, to achieve concentration and then randomize, we need a large seed that is that k, and then the total length of the seed will be k times log delta, which takes order of root log delta MPC rounds to the randomize. This yields a round complexity of log delta when combined with the MIS as well, which is way too high. Okay, one way to do it faster is as follows. Rather than doing in one shot, we do in log delta steps. In each step, we use a subsampling probability that is roughly 1 over root delta. Well, it's actually root delta prime being the maximum current degree. As the graph shrinks, this delta prime also will decrease. And there is a max 1 over n epsilon because we need to deal with machines that have limited memory, but this can be dealt with easily. So then the degree will shrink by this factor, and once you repeat it for log delta, you will get a graph where the maximum induced degree is 2 to the root log delta, order of that. Okay, overview of the analysis. Concentration here requires only log delta n. So in this case, k is short enough, so we can randomize it in order of 1 MPC rounds. When you repeat it for log delta steps, you incur only a log delta overhead. And there is also the deviation to control, but we make sure that each degree falls between 1 over 3 times root delta prime and 1 over root delta prime, so that at the end, this is off only by a log delta factor at the denominator. And this is good, give us what we want, so we can then compute the MIS. Now I'll tell you a little bit about the linear MPC. Here, the overall idea is to randomize CKPU, and consists of 3 steps: sample, gather, and solve. Sampling each node with probability DAG 1 over degree root square of the degree, using k-wise independence again. Then we gather all the sample nodes plus some sort of bad behaving nodes in a certain sense that is explained in detail in the paper. And then we solve again MIS. In this case, we need some care. So we will first compute a certain independent set on the gather graph, and then we extend this to an MIS locally. Good. Why is this a two-ruling set? Because as we will see, each node with a sample neighbor will be ruled, and we will make sure that the number of non-cover nodes actually shrinks proportionally to the degree, so d to the omega of 1, and then will allow you to gather all the nodes, because here we have linear memory, so in a constant number of repetitions, the problem will be solved. A node is said to be good if it is expecting many neighbors, many sample neighbors. As you see, the summation is over the neighbors, and that will give you an expectation, at least its degree to the epsilon, for epsilon some small constant. And this is somewhat stronger so that you can allow for the randomization. In the original paper, they were using, I believe, something like polylogarithmic, maybe even only log. So this node will be good and will be covered easily. Otherwise, a node is bad, and we have, however, some lucky bad nodes. So now, if a vertex is bad, it will have few neighbors. So if you have many bad nodes in your 2-hop, it is expected that you have some of them in the MIS. And if they themselves are in the MIS, they are distance at most 2 from V, which is good, will give us the desired solution. So the analysis is a bit more involved, but this is the main idea. And then the argument that the number of nodes decreases like that is pretty similar to the randomized paper. Good. In summary, we improved the complexity for 2 ruling set, matching the constant round complexity in linear MPC and getting root log delta plus log star n in sublinear MPC. There is still a gap between the randomized and deterministic in sublinear MPC, which is an interesting direction. And then one can also extend this to beta ruling set. We worked on 2 ruling set because it's somewhat the hardest case. Thanks for listening.
Okay, thank you for the presentation. So let's open the floor up for any questions.
Here? Okay. Here the approach is a bit different. So this condition ensures that this good node will have a sample neighbor, and that this will not be like kind of have different iterations, or I mean, will have different iterations, but it will be just one gathering. Then you solve it, you compute the MIS. Instead, in the sublinear one, you compute a subset of the vertices, you put it aside, you compute another subset, and you merge them. In that sense. Oh, but the standard MIS in congested click is log delta rounds. Yes, this is constant. No, this is not a degree reduction. It's a reduction in the number of nodes in each degree class. So instead of really reducing the degree, we reduce the number of nodes in each degree class. I hope this answers it.
Okay, we have time for one more question. Okay, so I was wondering whether this technique would generalize to other problems as well. And
good question. So our idea, when you derandomize, it's helpful definitely to have some randomized algorithms to look at, and then you try to use little independence, right? That is what we try to do, and it worked out. And the challenge is kind of more technical. When it comes to the design, I think it would be the first goal to improve the randomized complexity, and then you may be able to get something better deterministic. In this case, you see that there is often this square root log delta in sublinear MPC that comes from this round compression that we haven't managed to derandomize. That can be an interesting challenge.
Okay. Yeah, thanks for your answer. And let's thank the speaker again.
And we will now move on to the final session of the conference, which is about checking, verifying, certifying, proving in a distributed setting. So, the first talk in this session is about distributed model checking on graphs of bounded tree depth. And Johan is going to be giving the talk. Please.
Yes, thank you. So this is a joint work with Fedor Fomin, Pierre Fregnault, Pedro Montealegre, and Ivan Rapaport. So as you see, the gender balance of the group is terrible, but at least we have quite a diversity of locations from the northern part of Europe to the southern half of South America. So that being said, what's the purpose? So if you are familiar with sequential algorithms and especially so-called fixed parameter tractable algorithms, there are a series, a bunch of so-called algorithmic meta-theorems or model checking theorems, which are all stated something like, for all problems expressible in this type of logic, well, there is an efficient algorithm solving them for this specific class of graphs. So this is a kind of very general way of expressing that you can solve large families of problems efficiently on some graph classes, and we would like to bring some of these results into distributed algorithms. So first order logic on graphs is something very natural. So you have a graph which is expressed by a adjacency predicate. In the first order logic, typically you're allowed to write formula where variables correspond to vertices of the graph. So you can express things like to x and y are equal. You can express adjacency, and of course you can combine formula using ands, ors, negations, and also existential and universal quantifiers over variables. So with this kind of formula, you can express something like the graph does not contain a triangle, which is, okay, there are no three vertices, x1, x2, x3, pairwise different and pairwise adjacent. You can also express other things like the graph has an independent set of size 10 or a dominating set of size 3 or things of that flavor. So this is a quite small fragment of logic. Now, a very popular fragment of logic, which is much bigger, is the so-called monadic second order logic. So here, as before, you can use all the first logic formulae, but you are also allowed to use set variables that correspond to vertex subsets, so denoted here by S. And you can check if a vertex is in the set, and you can quantify over sets. So there exists a set doing that, or for all sets doing that. And in this framework, so you can express many things. As an exercise, you can try to express, for example, the fact that the graph is tricolorable. Here on the slide, you have an example that expressing the fact that the graph has no cycle, which is stated in there is no subset of vertices such that any vertex in the subset has at least two neighbors in the subset. But this is very powerful. And it becomes even more powerful if you think of formulae where you have three variables, and in particular, three vertex set variables. For example, you can express something like formula phi of S, saying that S is an independent set or a dominating set or things like that. And why is this interesting? So I'm still in the sequential algorithms and sequential model checking. So this is probably the most famous meta-theorem, which goes back to the 1990s by Bruno Courcelle, stating that, okay, I skipped one technicality. I said that usually with this logic, you're allowed to quantify over vertex sets. You can enrich this logic to be allowed to quantify even over edge sets. So that's MSO2. Okay, just a technicality. So Courcelle's theorem says, okay, every MSO2 formula can be checked in linear time, in O of n time, on graphs of bounded tree width. So I do not intend to define tree width, but I guess most of you are familiar with such things. So graphs of bounded tree width are kind of chubby trees, but not too chubby in some sense. And what is nice with this theorem is that it also extends to counting and optimization. So with this, you can, again, in graphs of bounded tree width, solve problems like tree coloring, or find the maximum size independent set, or count triangles in O of n time. And of course, there is a drawback. The big O notation here hides very high dependencies in tree width and formula phi. So it's typically a tower of exponentials depending on the tree width and the quantification height of the formula. But it's still O of n for fixed tree width and a fixed formula phi. Okay, so now let's get to distributed model checking. So what do we want to do? So here we want to verify a graph predicate, for example, triangle freeness, and we place ourselves in the congest model. And it was mentioned before several times at this disk, what would be an algorithm, a distributed algorithm deciding this predicate. So if the predicate is true at the end of the algorithm, all nodes must accept. And if the predicate is false, if the property is false, at least one node should express a veto, should reject. And that's what we mean by decision. And of course, in congest, we only allow log n, order of log n bits messages per round. Good. So what can we decide efficiently, at least in which graph classes? So let me start with bad news. For example, very simple first-order properties cannot be decided efficiently. You need at least diameter, even in trees. The number of rounds might be of order of diameter. So here you have an easy example. You want to decide the property like the graph has at most one node of degree 3. You see there on the right-hand side 2 yes instances, and on the left-hand side a no instance. But you can easily check that if you only allow a number of rounds, which is roughly diameter over 2, a bit less, then every node on the left-hand side has the same view, even in the local model, as one of the graphs on the right-hand side. So the node must take the same decision, so it cannot be coherent. I mean, if it says yes on the right-hand side, that it will say yes on the left-hand side, which is not consistent with the fact that it's a no instance. So this tells that we cannot decide first-order properties even in trees because of locality issues. But even if you think of properties which are obviously local, like deciding C4 freeness in a graph, well, it's known that C4 freeness requires roughly square root of n rounds in congest, and that's not related to locality but to congestion. And this even holds for graphs that are very sparse, for graphs of degeneracy 2. I recall that the degeneracy of a graph is the minimum number k, such that by repeatedly removing vertices of degree at most k, you end up with the empty graph. Okay, so that's bad news, but of course, fortunately, there are some good news. But for that, I need to introduce tree depth. So what is the tree depth of a graph G? It's the minimum number, let's call it D, such that we can arrange the vertices of the graph in a tree structure depicted in blue on my screen, such that for any edge of the initial graph, one of the nodes becomes an ancestor of the other in a tree. Okay, so the tree does not need to be a subgraph of my original graph. And if you have arbitrary graphs, the tree is actually a forest, but since we deal with connected graphs, I can state it in terms of trees. Maybe just a very easy observation, one tree that would fit would be any depth first search tree if the tree is not too tall in some sense. Okay, so what is our result? Actually, we show that if you have a graph which can be embedded in such a tree of depth at most d, a class of graphs that can be embedded in trees of constant depth, so the graphs of bounded tree depth, then any MSO2 predicate can be decided in a constant number of rounds in congest. And I mean, this extends to optimization problems. So you can find, for example, a maximum independent set, and at the end of the algorithm, all vertices belonging to a maximum independent set would be marked. We can also do things like counting solutions, for example, counting triangles in the graph. And okay, we believe this is the first meta theorem for distributed model checking, and actually it's related to a PODC paper 2 years ago, where Bousquet, Feuillet, and Pierron showed that on the same class of graphs, we can do certification with certificates of size big O of log n. So, I mean, you don't need to do certification. You can really solve the problems in congest in a constant number of rounds. I guess I have time to give you some hints why this works. So the first ingredient is that graphs of small tree depth have no long paths. You can even think, actually, a class of graphs is of bounded tree depth if and only if the graphs do not contain long paths. Actually, the longest path in the graph of tree depth D has a maximum of 2 to the D vertices. And this is nice because since all paths are short, I mean, if we are in a graph of small tree depth, then we can perform depth first search quite efficiently. The second ingredient is, again, a kind of easy observation, but I haven't defined a bounded tree width graph. So basically, if you know what tree decompositions are and what tree width is, when you have a DFS tree, if you want to come and with this property that every edge of the initial graph goes from a node to an ancestor, then you can transform this DFS tree into a tree decomposition like that. For every node, you just put it in all bags in the subtree below. You can easily check that this gives a tree decomposition, and then the size of the bags, the maximum size of the bag is, I mean, it happens in the leaves, and it's like the number of vertices of the longest path, which is at most 2 to the D, as I said before. And then the third ingredient, which is a bit more technical that it seems on that slide, is that with these tools, we can perform Courcell's theorem in a distributed way. And basically, why is that? So I'm just hand waving. So when you do, in the sequential algorithms, when you want to decide a property on bounded tree with graphs, what you do is you do dynamic programming. And Courcell's theorem says that actually all you need to compute at each node I is a table of constant size. The constant depends on the formula and on the size of the bags, but since both, I mean, the formula is fixed, the size of the bag is fixed, the table is of constant size. And moreover, when you compute the table at node I, all you need is basically the table at children nodes and some information about the bags that you can, again, encode in a constant size message. So basically, the model checking algorithm just takes like 2 to the D rounds, which is the depth of the tree, and at each round, it just sends from the bottom to the top some constant size information along the tree. And since the tree has the nice property of being a subgraph, you can easily do this in congest. And actually, if you want to do a bit more, like counting or optimization, you need to send a bit longer messages, but it's still O of log n with the same drawback that constants hidden there depend on the formula and on the size of the bags. Okay, so you can say, why would you mind about this rather tiny graphs of a tiny class of graphs of bounded tree depth? Well, it turns that these are often used as a tool for decomposing much larger classes of graphs. So there is a kind of, I will not define it either, the class of graphs of bounded expansion, but I will simply say that this contains all planar graphs, this contains all graphs of bounded degree, it also contains all graphs excluding a minor and so on. So this is a rather large class of graphs. So in particular, they are of bounded degeneracy, but they are much more structured than that. And actually, we can decide H-freeness in such graphs in big O of log n rounds in congest. And that holds for any connected H. For example, you can decide C6 freeness for these graphs. I mean, if you want to do an exercise to try to come up with an algorithm deciding C6 freeness in planar graphs, might not, I don't know, might not be completely trivial. So in order to obtain this, we rely on the powerful result of Nechetril and Osona de Mendez, the two people who introduced bounded expansion. Roughly what it says is that if you want to check if your whole graph has a copy of some small graph H of p vertices, what you can do is to color your graph with some f of p colors, which is still a constant, such that any copy of H would be, so of course we use at most p colors, but these vertices would appear together in a subgraph of bounded tree depth. So then we only need to express this H freeness as you saw before, it's trivial an FO property, so we can do this model checking by after we have this coloring, which is a bit surprising, but actually the algorithm, the distributed algorithm computing this coloring is rather natural and easy to understand. Of course, the whole proofs are complicated, but basically it's an algorithm based on degeneracy arguments. So you approximate degeneracy and you redo it again, you augment a bit the graph, you reapproximate degeneracy and so on and so forth for a fixed number of times. So everything goes smoothly, and I'm done. Basically, so I restate our theorem that there is a distributed algorithm checking MSO predicates or optimizing over bounded tree-depth graphs and constant number of rounds. This generalizes the result of Bousquet, Feuillet, and Pierron. And actually, in a recent work, the same authors plus Peter Golovash, we can do first order in bounded expansion graphs, but of course, as you saw in my example, you need to pay diameter, and it's actually diameter plus log n rounds. And if you want some questions to work on, of course, there are many directions where you can think of extending these things, but one question that is, at least to me, very interesting is, could we in this large class of, say, let's think of planar graphs, could we, for example, mark all vertices x such that a small radius, a bounded radius around x satisfies some first order formula. So we can do it if the formula is x belongs to a triangle, but we don't know how to do it in the general case. Now I'm really done. Thank you.
Thanks. Questions, comments, thoughts?
So you mentioned the C4 and C6, and you just said something about triangle, but can you say if the graph has a triangle or not in case it has a bounded expansion?
Yes, yes. Yes. The point is that if it's bounded expansion, one guy would see that it's in a triangle or in a C6 or whatever. Not everybody, unless you. Okay, if you pay diameter, you can tell everyone the whole story.
I think I'm asking about the negation of the property. Like if there is a triangle, then at least one vertex has to say so, and if there's no triangle, then all vertices.
So triangle freeness, for example, goes like that. If there is no triangle, all vertices must accept, and if there is a triangle, at least one vertex must reject. Sorry, and so that's why we usually express it like that, like triangle freeness, and not there exists a triangle, because, okay, if you want to do it something in a constant number of rounds, the existence of a triangle in a part of a graph, you usually need to pay diameter. In bounded tree-depth graph, this is not an issue because they are of small diameter, they don't even have long paths. But if you want to do it in planar graphs, for example, if you want to count the number of triangles, you need to pay diameter. But doing that, you can even count triangles, yes.
Thanks. Any other questions? Yes.
Hi, so you mentioned the previous work on certification, and obviously this was originally motivated by self-stabilizing algorithms. So could you combine your work with the previous work to get like a self-stabilizing algorithm?
We need to think about it, but
Okay.
it's part of the plan, yes.
All right, thank you.
Okay, let's thank our speaker now. And the second talk in this session is going to be fully local, succinct, distributed arguments. And I think we were also promised some pandas. Can you get it working?
Okay. Oh, not yet.
Good. Okay. And Eden's giving the talk, please.
Thank you for the introduction. So this is fully local distributed arguments. It's a joint work with Rotem Oshman done in Tel Aviv University. So I'll start by presenting the model that we work with. So it's a synchronous distributed network where each node has an individual input, and in distributed algorithm, nodes exchange messages across the network's edges, and eventually each node obtains its individual output. Now, unfortunately, some distributed algorithms are pretty expensive, and we would not like, for that reason, to run them multiple times. So what we would like is to only run them once and then use their outputs over a long course of time. But networks may be dynamic. So after some time goes by, it may be that the networks itself changes its topology or some of the inputs change, and we do not know whether we can still use our outputs or do we have to actually run the algorithm all over again. So we would like to have some mechanism that will allow us to verify this in a much more efficient manner than the original distributed algorithm. So for that goal, we have distributed certification schemes, which is like a more general term that includes many different perspectives, many different versions. But some of the more famous ones are proof labeling schemes by Korman, Kuten, and Peleg, and locally checkable proofs by Rus and Somola. And in these schemes, we have a prover that assigns certificates to the network nodes, and we have a local verification mechanism where nodes exchange messages, and each node decides whether to accept or reject using the message and the certificate. Now, we say that the network configuration is accepted if and only if all nodes accept it. Now, these schemes are required to guarantee us perfect soundness, which means that if the network configuration is invalid, then there is no certification assignment whatsoever that will cause the entire network to accept. Now, what are our complexity measures for these kind of schemes? So first, we care about the verifier locality. So I said it should be much more efficient than the original algorithm. And we usually think of one round mandatory. Some works extended it to a little bit more rounds to achieve better things in other measures. But here we only consider one round verification. And we also want the certificates to be short, here preferably polylogarithmic in the network size, and also would like the verification message to be short as well. Now, what about the prover? So most works really care much more about verification, and they don't really mind paying a lot more in the proving side, but we still think about the prover as some mechanism that runs alongside the original distributed algorithm and does not hopefully add too much overhead to that algorithm. And it often uses this algorithm's transcript documented at the nodes. Now, I will already jump ahead and say that in this work, we care more about the prover than usually, and we're going to do some efforts to improve that. Okay, so unfortunately, again, some problems require long certificates. So, for example, we have the graph symmetry problem, which is the question of whether the network's topology has some non-trivial automorphism. And Ursa and Somola showed that there is a lower bound and you actually have to use n squared long certificates to certify this problem. This means that you cannot do better than the trivial solution, which would be given each node as the certificate, the entire network topology. So luckily, we do have arguments to the rescue. So last year in TCC, Ilet Boyle, Ran Cohen, Tal Moran, Rotem Oshman, and myself showed that you could actually verify any polytime distributed algorithm in one round using polygen size certificates and messages. Now, how could that be possible? I just showed you a lower bound that should contradict this. So the catch is that we actually relax our soundness requirement to what is called computational soundness. So what's computational soundness? So in crypto, we have SNARKs. Some of you may have heard about them. So they are succinct non-interactive arguments. Arguments are computationally sound proofs, and computational soundness means that soundness is only guaranteed to hold against bounded adversaries under some hardness assumptions. So most common are decisional Diffie-Hellman assumption and learning with errors, but there are more. And this means that we only guarantee to be sound against someone who cannot solve these problems. And if we believe that no one can solve these problems, we're good. So distributed SNARKs are distributed certification schemes relaxed to being only computationally sound. And some of you may ask, why is that enough? Or like, why is that good for our distributed motivation we showed earlier of using the outputs of a distributed algorithm after a long time? And my answer is that it should capture anything that we imagine, and more importantly, anything that we can simulate. So for example, if I want to be secured against random hardware faults, then if I can simulate a network and then simulate some random hardware faults, then I shouldn't be able by this method solve the learning with errors problem. Okay, so because I can't also destroy the computational soundness. So I am satisfied by this. Of course, it is less than actual perfect soundness, but this could be satisfying for many applications. So let's go back to our complexity measures. So we had verify locality, short certificate, short verification message, and we also care about the prover's overhead. And in the last paper I mentioned, the ABCMO showed locally verifiable distributed SNARKs, where all of the three first measures are satisfied, but the prover algorithm actually adds all of the diameter rounds to the original algorithm. And in this work, our main result is that we construct fully local distributed SNARK, which is what we call distributed SNARKs, where the prover overhead is only polylogarithmic. Okay. So to show you a little bit how it's done, I'll first dive into the methods used for the earlier distributed SNARKs. So this paradigm called distributed hashing SNARK, the recipe goes as follows. So first you hash the transcript all over the network. And this should take you all of the diameter rounds. This makes sense because this is information that lies all around the network. So it takes diameter time to collect and hash it. And then at each node, we use a SNARK to prove the statement that the underlying transcript of that hash value makes sense to me, where me is the node. And what making sense means, it means that I would really send these messages documented in the transcript, and I would actually output this output if I am sent these messages. And in verification, each node verifies that the hash value it has is the same as its neighbors, and also that, the SNARK proof is accepted. Now let's revisit this hash of the entire transcript thing, which is this part that took us off diameter rounds, which we wanted to get rid of. So the logic of why we need that is that if everyone has the same hash value, then we don't have any consistency issues with the transcript. So, for example, we cannot have a situation where my transcript says that in round 3, I said hello to my neighbor, but my neighbor's transcript says that in round 3, I said what's going on. So these kind of consistency issues cannot happen if we all have the same hash value, because the hash function has some collision resistance properties. And if there is no consistency issues and the proof is accepted, the snark proof is accepted, then it means that the overall statement is correct. So this is like the main logic that is behind the construction. But as we said, we have O diameter rounds to construct this one hash value of the information that lies in the entire network. And here we ask, do we really need one hash to rule them all? And let's revisit that. So let's look at this example and specifically look at nodes A and B, which are pretty far apart. And we ask whether these two nodes really need to check any consistency between them. So really, they don't, because they never even discussed anything during the distributed algorithm. So there's no consistency guarantees that their transcript should be satisfying. So our observation is that we don't really need one hash for everyone. What we need is only that each pair of neighbors share a hash value. And for that, we construct something we call low diameter edge cover. So we divide the network into low diameter clusters, and we want that edges are covered by these clusters. This means that each node is in the same cluster with each of its neighbors, and to achieve both that and low diameter, clusters, of course, overlap. So we don't mind. So nodes may be in more than one cluster, and then now we can hash the transcript at each such cluster without spending too much time. So our new recipe is first cover the network's edges with clusters of diameter lowercase d, then hash the transcript of each cluster, and this should take you O of lowercase d rounds. Then we use snarks to prove at each node that the underlying transcript of all of my cluster's hash values makes sense to me. So now each node may have more than one hash value, and the transcript that underline all of these hash values should make sense. And then in verification, we verify that these hash values are the same across cluster neighbors. So for each cluster, we check that the hash value that we have of that cluster is the same as the neighbors we have from that cluster. And as well, we verify that the snark proof is accepted as before. And now let's see what we're required to construct to actually cook this recipe. So first, we cover the network's edges as part of the prover algorithm. So we want this cover to only take polylog n rounds because we wanted the prover to only use polylog n rounds. Then we hash the transcript, and this takes O of lowercase d rounds, so lowercase d should also be polylog n. And finally, each node now holds hash values for each of its clusters. And because we don't want the certificate to be too long and all of these hash values are becoming parts of the certificate, then each node should not participate in more than polylog n clusters. So clusters do overlap, but not too much. Okay. So to sum up what we wanted from our edge cover, which we now call succinct low diameter edge cover, we wanted it to be computed in polylog n rounds. We wanted each cluster to be of diameter at most polylog n. We wanted all edges to be covered, and we wanted that each node is in at most polylog n clusters. Now, luckily, we already have low diameter graph decompositions, which are more familiar to most of you, I think. And specifically, we use the ones of Rojan and Jafari and Cheng and Jafari. And this is a decomposition of the network into disjoint clusters, which is computed in polylog n rounds. Each cluster is of diameter at most polylog n, and the cluster graph is polylog n colorable. And now I'm going to show you how we use the lower diameter graph decomposition to construct the low diameter edge cover. So let's take this graph, for example, and the first thing we do is take G squared. So we've talked about power graphs throughout this conference. So G squared is this simple graph where you add all edges between nodes of distance at most 2. And then we use low diameter decomposition on G squared. And now we observe that if the cluster graph is k-colorable, then each node is connected by original edges, which are here the pink edges, to at most k clusters. The reason for that is that if one node is connected to 2 different clusters of the same color by original edges, then in G squared, those 2 clusters have edge between them, so they cannot be in the same color. So this limits the amount of different clusters each node sees by original edges. And this means that now we can expand the clusters to also include neighbors. And now each node is not in more than polylog n clusters, and all edges are covered, which is exactly what we wanted. And the diameter only grew by like 2. The constant added 2, so it's fine. Okay, so in polylog n rounds, we compute edge cover with polylog n diameter clusters, polylog n clusters per node, and we know that distributed hash computing, which is, by the way, a separate distributed algorithm, which I haven't shown you, on polylog n diameter cluster would take us polylog n rounds. And by that, we get our fully local distributed SNARK. So summing up, distributed arguments are distributed certification, relaxed to computational soundness. Our certificate and message size is polylog n. We say it's fully local because we verify in 1 round while proving with only polylog n overhead. It's a black box use of decomposition, which I think it's nice because I haven't mentioned here the exact polynomials of the logarithm that we use, but this actually means that if any of you develop new decomposition algorithms which are faster, then this immediately implies faster prover for our construction. And I'm going to mention here our upcoming work where we also reduce the space complexity used by each node here. And eventually we want to have incrementally provable distributed SNARK, which are SNARKs that lies in the nodes, and you could really update the proof after each round without a lot of overhead, and that way you could certify and verify every algorithm quite easily. This is our long-term goal, and thank you for listening. I'd love to take questions.
Thanks. Questions?
Just to get a flavor, thank you very much, by the way, very nice talk. So to get a flavor of the hashing, so you said you take these 2 nodes, A and B, very far away. So let's say the algorithm is Borufska for MST construction, for instance. What does it mean? I agree that these 2 nodes do not interact directly, but what would it mean? You would encode, you would hash only the beginning of the algorithm? And could you give an intuition?
No, okay, so I'm assuming that everyone ran the algorithm and that each node documented the transcript of the messages that it received and sent. Actually, here only the sent messages are required for each node. And then so each node have all of the rounds that this node participated in. And now I would like to create this one hash value, which is a Merkle tree. I haven't mentioned it here, but we do require that this is a Merkle tree. We have an algorithm called distributed Merkle trees. It's from the the first paper. And we then compute separate Merkle trees for each such cluster. And this cluster is going to contain the transcript of all the conversation happened on the edges that are in this cluster.
By the way, do you really need this like full transcript to be saved on each of the nodes? Or I'm wondering what is the memory complexity of this certification?
Yes, yeah.
here?
So this, like, in our upcoming work, we really do not want to have to like document the entire algorithm, at least not in the same time. Actually, what I said earlier, like the kind of wavy argument about consistent hashing mean there's no consistency issues between nodes, then like for that I do need all of the messages currently, because I am saying something like this now proves something about a hash that includes this message, and I'm using the fact that both of the nodes on the two edges and the two sides of the same edge like are talking about the same message that was sent, and it's used to prove that the soundness of the snark is actually enough to claim what we want. But in the future, we could also like have these snarks that you update after each round, and then you don't have to have the entire documentation of everything that happened before.
Thanks. Let's thank our speaker now. And it's time for the very final talk of this conference. So we have a brief announcement: decreasing verification radius in local certification. And
okay,
and we have Matthias giving the talk, please.
Thank you for the introduction. So I will be presenting joint work with Eric Sedlacek, and we will be coming from the point of view of asking which graph properties can be verified using only local information of each node. So first, let me start off with an example. So suppose that the property which we want to verify is that each node has a red node within its neighborhood. Now, in our setting, we have a verifier algorithm that is executed on each node, and no communication is happening. The verifier can only observe its neighborhood, and based on it, it must decide whether the property may hold or whether it cannot hold. So it returns its output, and then we take as a global decision that if every node says OK, then the property does indeed hold. If the property does not hold, then at least one node must report that it does not hold. So the model that we study is the previously mentioned local checkable proofs by Goss and Suomela. And additionally, what I have not shown now is that if some property is too difficult to certify in this way, we may allow an additional information on each node in form of certificates, which is like a bit string placed on each node. On each node, it can be different. So you can imagine that we have a prover, sort of an oracle that sees the whole graph, and it may assign like helpful certificates on each graph, on each vertex. For example, if we want to certify that a graph is tree-colorable, the certificates could be exactly the colors, then the verifier can locally see that the certificates are indeed the correct coloring. At the same time, the verifier must not be fooled by some false certificates. Let's imagine some adversary pastes them, then the verifier must recognize that and reject on at least one node. We are interested usually in the maximum size of the certificate that appears on a vertex. For example, if it's like a logarithm of n, then that is usually considered as an effective locally checkable proof. And another concept we consider is the visibility radius, that is how far the verifier can see. So it may not be necessarily immediate neighborhood, but some large distance. Now you can imagine that this can affect how hard it is to certify something. If our property is that a node is always within distance 10 from a red node, then if we actually see to distance 10, it is trivial. If we see only to distance 1, it must require some certificates. And so we ask the question, what is the actual effect? And the first result is that we can decrease the verification radius at the cost of increasing the certificates. So the idea here is simple. We essentially take the neighborhood that we have and encode it into the certificates. We also do some additional small work of like verifying that this is that the neighborhood is correct. What is perhaps more interesting is that this basic approach is very close to optimal up to so we have a matching lower bound with a gap of roughly maximum degree. So our large delta here is maximum degree. And we show that by considering an artificial property, a graph holds this property if it looks basically like this binary tree. And we have some strings spelled out in the labels of the least in the left subtree and right subtree. And for the property to hold, those two strings must be the same. Now the intuition is that the information from the left subtree must somehow reach the other subtree, and naturally this will meet in the root. So root will be the one that decides whether the strings are the same or not. And based on this idea, we build up a proof where we show what is the optimal size of certificates on this property for a given radius. And then from that follows that we cannot decrease the radius below the lower bound that we prove here. So the idea of the proof is sort of a standard technique where we consider if the verifier used small certificates, then we can find two instances which can be cut up and glued into something that the verifier would still accept because it looks like the original instances, but actually does not hold the property anymore. So to summarize, we have shown how to decrease the visibility radius of proof labeling schemes at the cost of increasing certificates using a basic approach. And we show that the basic approach cannot be improved much in general. We show that, for example, in PAS, we can have some improvements there. And one important open question is sort of dual but quite different. If we can decrease the certificates in exchange for larger radius. So there are already some known results for that. So this is everything for me. Thank you for your attention.
Thanks. Questions? I would at least like to know more about this kind of like, you mentioned these specific graph classes. So if your graph class is simply something like graphs of bounded growth, like you have polynomial growth in the number of nodes as a function of your neighborhood size, do you get something trivial in those cases?
So in that case, we are able to do slightly better, yes, because we essentially encode the neighborhood, which is now smaller. So in that case, it is better. Another case where we are close to the optimal is when like the maximum degree is constant and our matching lower bound is essentially tight asymptotically.
Right. And for those cases of, let's say, polynomial growth, do you have also a matching lower bound for those cases? Like
for those cases, no, we do not.
Okay, so that's open. I guess now it's time to thank all speakers in this session. And I guess it's time for our PC chair to say the closing words of the conference.
All right. So yeah, thanks all for still being here. Thanks a lot to Yuka for helping so much this afternoon. So it's been a pleasure to be sort of putting together the program, and I was actually pleasantly impressed by the quality of talks this year. I don't think it was this much fun when I was sort of 15 years ago when I was at the first disc. So yeah, I guess that's it for the main conference, and see you tomorrow at the workshops.